Welcome to Practical Machine Learning by Example in Python. I'm your instructor, Madhu Siddhalingaya. In this course, you're going to learn about machine learning using Python. As you know, Python is one of the most widely used languages today, and it's very popular for building machine learning models. You're going to learn how to build machine learning models that learn from data using TensorFlow, which is a very popular machine learning library developed by Google. As you know, machine learning is used in self-driving cars, recommendation engines, smart speakers, and many other applications today. Modern machine learning models can solve a number of problems that were once considered extremely difficult. One of the important steps in developing machine learning models is to prepare data. So we're going to use two popular libraries to do just that. You're going to learn Pandas and NumPy. Pandas is used to read and manipulate structured data, and NumPy is used to perform sophisticated math transformations that are often needed in machine learning models. You're also going to learn to visualize data using Matplotlib. Matplotlib is a powerful and easy-to-use visualization library that's capable of producing high-quality charts and graphs with just a few lines of code. And we're going to train and test our models using Jupyter Notebooks. And Jupyter Notebooks are an open source web-based platform that are widely used by machine learning practitioners and data scientists. We're going to run these notebooks in Google Colab, which is a free cloud-based service. So you don't have to install any software. Google Colab also supports GPU hardware acceleration, so we can train a number of our models more efficiently. Throughout this course, you're going to learn by example, and examples are a great way to learn. In each example, you'll learn step by step what the problem statement is, how to analyze the data, how to prepare the data, how to develop and test models, how to select the right model, and of course, you're going to learn where to go next. Don't be afraid to try things out. It's the best way to learn. And in my experience, there are three keys to success in machine learning: experiment, experiment, and experiment. It's the best way to understand what your data is telling you and to get a feel for how a machine learning model works. There are a number of foundational sections in this course, and these foundations are important. You're going to learn a number of libraries and APIs, as we mentioned, such as TensorFlow, NumPy, and so on. You're also going to learn machine learning concepts, such as neural networks, deep learning, gradient descent, regularization, and so on. I've also included a Python quick start if you're not familiar with Python. But if you're an experienced Python developer, you can use this section as a reference. You will also need some math fundamentals, some basic linear algebra, statistics, and a little calculus. Don't worry if you don't think you're great at math. We're going to learn these as we go. We're going to take it one step at a time, and you'll find it's not as difficult as it seems. All of the code used in this course is available in my GitHub repository, and I'll provide a link to it in the resources section. And finally, if you have any questions or concerns, don't be afraid to ask. Remember, there are no dumb questions, only dumb answers. Machine learning can be very challenging, so I'm here to help. And often, if you're confused, others probably are as well. You can post a public question or message me directly if you prefer. In general, I try to be very responsive and get back to you as soon as possible. So are you ready? Machine learning is a rapidly growing field full of possibilities. I'm sure you're excited, so let's get started. Throughout this course, we're going to use Jupyter Notebooks as our development environment. Jupyter Notebooks are widely used by machine learning practitioners and data scientists to visualize data, to analyze data, and to create machine learning models. It's also a great way to document your work and share it with others in the cloud. Jupyter is a web-based platform. You can install it and run it locally, or you can access it through a cloud hosting service remotely. We're going to use a free cloud hosting service known as Google Colab. You can easily get to Google Colab by first navigating to the Google homepage and just searching for Google Colab, C-O-L-A-B, just like that. And usually the first link that comes up is what you want. And the URL is colab.research.google.com. So if I click on that link, I'm presented with this dialog that lists a number of different notebooks. There are example notebooks, there are recent notebooks that I've opened, there are notebooks that are stored in Google Drive, and there are notebooks that I can load from GitHub. I'm going to enter my GitHub repository here to load a notebook from my repository. And I'll provide a link to this repository in the resources section for easy access. So we want to select the name of the repository here, which is machine learning. That's the one we're going to be working on throughout this course. So if I scroll down, the one I'm looking for is notebooks/Jupyter Notebook. So let me click on that to open that notebook. So this is what Jupyter Notebook looks like. And the nice thing about it, it has a rich user interface. You can create formatted text, add images, add high-quality math markup, as well as live code in a variety of languages. We're going to do a lot of our work in Python, but you could work in other languages as well. And code inside of a notebook can produce rich, high-quality output, such as images, video, audio, or many other data types. Jupyter is designed to be interactive, which is particularly useful for machine learning and data science. Because developing a machine learning model is an iterative process. It's an experimental process. Many times we'll develop an initial model, we'll test it, and then we'll adjust some parameters, test it again, and so on and so on. And we iterate until we come up with a high-quality model that meets the accuracy that we're looking for. As mentioned, Jupyter can be installed locally or accessed through a number of cloud services. Some of the cloud services include Google Colab, which is the one we're using, or maybe Amazon SageMaker, Microsoft Azure, IBM Watson, and many others. I'll provide some links to other cloud services in the resources section. Jupyter Notebooks are made up of a number of cells, and we can see a couple of cells right here. And these happen to be text cells. We can also include code cells, which we'll look at in the next lecture. If you look at this cell right here, it has some formatted text, it has italics, bold, and it has formatted code, and it has images. To add all this content, or to add a cell, I can do it in a number of ways. I can click on one of these buttons up here to add a code cell or a text cell. I can also use the menu item up here to insert a code or text cell. Or I could go to the bottom of a cell and select one of these buttons to insert code or text. So to edit a text cell, this happens to be a text cell right here. To edit that, I can double click on it. And this brings up the markup that's inside of this cell. This uses, or markdown as it's called. So this markdown has a very easy to learn syntax, and it looks like this. These are headings. 2 hash signs, that refers to a level 2 heading. And you see a link right here. You can see some highlighting such as italics, bold, strike through. You can see syntax highlighting with these 3 tick marks, and you can specify a language for syntax highlighting. You can add images, lists, tables, and so on. So the nice thing about Google Colab is that it shows you the markdown on the left and what it looks like on the right. If I want to get out of edit mode, I can just click on any other cell and it renders that cell very nicely. So if you want to know more about Markdown and how to use it, I provided a link here to a Markdown cheat sheet. And this is the Markdown cheat sheet, and it gives you examples of how to create headers, as you see here, how to create different kinds of emphasis to format text, how to create different lists, ordered lists, unordered lists, links in many different ways, images, different ways of presenting images, code and syntax highlighting, and you can specify different languages. Here's JavaScript and Python and others. How to format tables, block quotes, inline HTML, and so on. So there's quite a bit you can do with text formatting inside of a Jupyter Notebook. In the next section, we're going to look at code cells and how we can add code and work with it interactively. As mentioned, we can add code cells to a Jupyter Notebook, and this is where a lot of the power really comes in. So these are some code cells as you see right here, and a code cell has this icon right here to run that cell. All right. So I've included some Python code, and before I go any further, let me go up here and I'll clear all the output. All right, so I can run each of these cells and you can see what the output looks like. So here's a cell. So if I click this run button, the first thing that's going to pop up is a warning that's saying this notebook was not authored by Google and it came from GitHub. It's okay, there's nothing dangerous about this notebook, so let me go ahead and run it. And once it consents to a remote runtime, it executes that cell. Of course, I can run it as many times if I'd like. Here's another cell, and in this cell, I'm defining a Python function. And it takes two parameters, a start and an end. And what it's going to do is generate a multiplication table with a starting number and an ending number. And if I run this cell, notice it doesn't produce any output because this defines a function. In another cell, I can refer to other functions that have been defined earlier in the notebook, say in this cell over here. So this all represents one Python module, if you will. So I'm going to call this multiplication table with these two parameters right here, the starting value and the ending value. And if I click run, notice it produces some nice output. All right. So everything that I printed, and whenever I used a print here, it produces this output like that. Our programs can produce nice visualizations. So in this example here, I'm going to use matplotlib to plot a couple of graphs. We're going to learn a lot more about matplotlib in future lectures. The point here is just to show some of the capabilities. So if you look at it, I plotted both a sine curve and a cosine curve, formatted very nicely. And if I want, I can change some of the parameters here. So let me change this to green and rerun it. And you see it changes the graph color to green, right? Or maybe change the line width. Oops, a little syntax error there. Let me try again. This is kind of neat. When it plots an error, it brings up a link where you can search for search for that error in Stack Overflow. So there you go. Very easy to use, very powerful, and it's actually a lot of fun to use. And that's what I like about it. Next section, we're going to talk a little bit about math notation and some magic commands. Another nice feature of Jupyter is its ability to render high-quality math notation using LaTeX syntax. And if you're familiar with LaTeX, you know how you can create math notation using this particular syntax like this. And the way you do that is use these two $signs to delimit the beginning and the end of a math equation. I'm not going to get into all the details of LaTeX. I provided a link here that gives you more details on the syntax and how it works. This just shows you the quality of the output that you can produce. And there are even some Python libraries that produce math output in LaTeX format that can display as an output of a cell. We're going to use math notation in a few places. This isn't a math course specifically, but there is, of course, some math involved whenever we do any kind of machine learning. So in those cases, we're going to use this math notation to explain what a model is doing or how it's producing certain results. In addition to text cells and code cells and math notation, Jupyter has a number of magic commands, and I've just listed a few of them here. These magic commands start with a % sign. They're really code cells, but they start with a % sign. So here's one where you can run a system command. So you would write %system and then a command. Or you can also use the exclamation point. That's another way to run a system command. So I could run a system command by creating another cell here. Let me create a code cell. And I will type ls, which lists the current directory. And it turns out in Google Colab there happens to be a sample directory here. And if I go over here to Google Colab, it has a section where I can look at all the files, and you notice that there is a directory called sample data. And if I look inside there, there's some more files. So if I type ls sample data, rerun that cell, you see it lists all the files in that directory. We'll talk more about files and how to upload files and download data in later lectures. So here are a few other magic commands. %run, if I want to run a Python program, I can run that and supply arguments. I can add this %time in the beginning of a cell, and that will time the output. So let's see if I try that, what happens. %time. And if I run that cell, it will execute, and it says it took 2 microseconds CPU time, and so on, wall time, 5.8 microseconds. So that's helpful if you're running a long-running process and you want to see how long it takes. This whos is kind of convenient. It lists all interactive variables. I'm not sure if we have any here, but let me try. All right. So these happen to be some modules that we imported. All right, and there are some variables here. The sine and cosine variable that we created, there were lists, and it tells you the type. If you want to install Jupyter on your local machine, there are a few ways to do that. You can use pip install if you happen to already have Python installed. Pip install notebook from a command prompt will install Jupyter. Once it's installed, you can run just this command, Jupyter notebook, from the command prompt, and that will start a local server and open up a browser that gives you access to all your Jupyter notebooks. Another way to do that is to install Anaconda Python, which is a complete environment, and that includes a number of libraries, including Jupyter Notebook. And that's what I often do whenever I'm installing it locally. Next, you're going to have an opportunity to experiment with Jupyter Notebooks. Google Colab allows you to share your notebook with others, and there are a couple of different ways to do that, and I'll show you each of these techniques. So one way is to share the notebook given a link or with a certain number of people. And the way I can do that is to go up here to this upper right, and you'll see this button that says Share. So if I click on that link, it's going to bring up this dialog. It says you can share with people in groups, and I could list specific people that I want to allow access to this group. Of course, those people need to have a Google account to do that. Another way I can do this is allow anyone with a link to access this notebook. So right now my notebook happens to be restricted. Or what I can do is I can change this, and let me click change. Instead of being restricted, I can change it to anyone with the link. Anyone with the link. So that means that anyone that has this link can now access this notebook. So let me try that. I've changed it to anyone with the link, and then I'll go over here and say copy link. So this is the link. I've copied it. Now let me see if I can access it as an anonymous user. So what I'll do is I'll create a Cognito window. So I'm not logged in as any specific user. And then let me paste that link here. And as you can see, I can access that notebook, and I can view the notebook and save it in Google Drive. So that's how you share a notebook. So remember, when you share it, and if you want anyone to have access, you need to change the restriction. By default, notebooks are restricted, and they are only accessible by the person who created it. Another way I can share my notebook is to save it on GitHub. I can commit my notebook to GitHub. Now, I could just download this notebook to my local machine, and the way I would do that is go down here to File, and I can download a copy of the notebook like this, download IPYNB, and that's going to download it, and I can save it, and then I can use local git commands or a git application to commit that to GitHub. That's one way to do it. Another way to do it is directly in Google Colab. So in order to do that, I can use save a copy in GitHub. Right? Now, before I do that, of course, I have to have a GitHub repository. Here's my GitHub repository here, my GitHub account, I should say, and I can create a repository. And of course, you need to have a repository created initially, and the way you do that if you're not familiar with GitHub, is to go up here to this plus sign up here and say create new repository. And you can create as many repositories as you like, public repositories that is. And as you know, my machine learning repository has a number of notebooks in it organized by directory. So I happen to have a notebook here. So let me make a small change to this notebook. And I'll just change the text here. Something like this includes some visualizations as well. All right, a small change, and now I want to commit this to GitHub. So what I'll do is I'll go over here and click File and save a copy in GitHub. Save a copy in GitHub. And the first time you do this, it's going to ask you to authorize Collaboratory in GitHub. So now you can save things in GitHub. This only happens one time. So you can select whether you want gists and repositories, public repositories, and I'm going to just allow both of them. So first I'll say authorize Google Colab, and you'll get this only one time. And now once you do that, you're going to have this next dialog that says copy to GitHub, and it will allow you to select the repository. And I'm going to select machine learning. I have multiple repositories. I'm going to select machine learning, and then the file path. This is very important. If you don't, now it's going to have the name of the notebook here, but if I don't put in a directory name, it's going to save it in the root of my repository. And so what I want to do is I want to save it under my regression directory, right? Under the machine learning, I have multiple directories in here, and I specifically want to use the regression directory, and that was already created. So let me copy that, and that's one thing I like to do so I don't make a mistake when I'm typing, is I'll copy it, paste it in front, and then put in a slash. And I'll also include a link to Collaboratory, which is very, very nice. And you'll see that in a second. It's going to create a link in GitHub so you can open it. And I can change the commit message. I'll change it to add visualization comment, for example. So let me click OK. So it's going to create a copy, and then it's going to register it in GitHub, and then it's going to show me what it looks like. So you notice it includes this new text that I've added. This includes some visualizations as well. And also it has a link up here that says open in Colab, which is very convenient. So anyone that clicks on this link will open this notebook directly in Colab. It's a very convenient way to open notebooks. Also, I'll also include a link to this notebook, which gives you more detailed instructions on how to save a copy in Drive or save a copy in GitHub. So remember, if you're going to share your notebook using the share method, using a link, you do need to change the restriction to anyone that has this link. Anyone that has this link. Let's go through some quick definitions of artificial intelligence, machine learning, and deep learning. These are probably some terms you've already heard. If so, this may be a quick review, but let's just go through those definitions so that we're all on the same page. So each of these three, like in the case of artificial intelligence, it's intelligence demonstrated by machines. And that's a pretty broad definition, and it's hard to define intelligence specifically, but generally it's considered a capacity for logic, self-awareness, reasoning, problem solving. There's also another term known as artificial general intelligence, which means do everything a human can do. And I'll tell you right now, we're not there yet. Machines are nowhere near the point where they can think like humans can. Next, we have machine learning. And as you see here, machine learning, it's a subset of artificial intelligence. And what that means is to perform a specific task by training models that learn from data. And we don't give these models any specific instructions. What we do is we supply it lots of training data or training samples, and the model will learn from that. Maybe we give it lots of samples of images or sound or text, and it'll learn from that. And once we've trained that model, we can give it some new input and then make some kind of a prediction. Maybe recognize a face or get some understanding of natural language text. And finally, we have deep learning, which is yet again another subset, and it's a subset of machine learning. And this is a recent advancement. Deep learning models, they're based on neural networks or multi-layer neural networks, and they're inspired by human biology and animal biology by looking at brains of animals and understanding how they're connected. And if you look inside of a brain of an animal, you'll see that there are all these neurons that are connected together in this very complex network. Now, this doesn't mean we understand how the human brain works. It's still very much an open question. But some of these ideas are inspired, meaning that there are different neurons or units that are connected together in this kind of network. And there are many different types of networks, and we'll learn more about that as we go through the lectures. Now, the advantage of these deep learning networks or these deep learning models is that they tend to outperform all other methods or all other machine learning methods, given enough training data. They do require a lot of training data to solve these complex problems. And a lot could mean in the order of thousands of samples or so. In some cases, there may be millions of samples. But the advantage of these deep learning models is that the more data you give them, the more sophisticated they become. This is an advantage over simpler machine learning models that were developed, or classic machine learning models developed historically, where they tend to level out. At a certain point, you give it more data and it just doesn't learn anything more. So to solve more complex problems, deep learning is largely what people are focused on today when they mention machine learning. So a lot of times you'll see these terms somewhat synonymously. Deep learning does distinguish itself from classic machine learning, but I'm not going to make a significant distinction here. Throughout the course, we're going to go through a lot of deep learning models and deep learning techniques because that's where a lot of the advances are coming, and some of the really interesting work that's being done and the problems that are being solved by these deep learning models. I will mention some of the classic machine learning techniques and machine learning models because that's a good place to start and understand how these more sophisticated models work. Welcome to the Python Quick Start Foundation section. What you're going to learn in this section are basic Python concepts. It's meant for developers that have experience in other languages, such as Java or JavaScript. If you're an experienced Python developer, you can move on to another section and maybe come back to this section and use it as a reference. But for everybody else, we're going to learn the syntax, data types, conversions, and you get to try it out interactively in a Jupyter notebook. You're also going to learn flow control and data structures, such as if statements, for loops, while loops, dictionaries, lists, and so on. You're also going to learn about functions, methods, and classes. But keep in mind, this is not a comprehensive Python course. We could have an entire course just on Python itself, so we're going to learn just enough to understand the examples that are used in this course. As many of you know, Python is one of the most popular programming languages in use today. It's used for many different applications, but interestingly, it's widely used for machine learning and data science as well. And this is due in part because of its simple syntax. People just like to use it. Simple things are simple. It's interactive in nature, and it has numerous machine learning libraries. It's easy to test things out, which is very important during data analysis or model development. We're going to focus on Python 3 because Python 2 is no longer supported. And the example here is all within a Jupyter notebook, which you can find on my GitHub page. I'll provide a link to that. And the nice thing about it is you can refer back to this from the web and use it as a quick reference. And I often go back here because I often forget some of the esoteric syntax. So to work with this notebook, we're going to go to Google Colab. We can get there by navigating to the Google homepage and just searching for Google Colab. And it's the first link, collab.research.google.com. And we'll go to my GitHub repo, type in my GitHub URL, and I'll provide a link to that in the resources section for easy reference. We want to select the machine learning repository, and we want to scroll down to notebooks. Python quickstart.ipynb. Notebooks Python quickstart.ipynb. So here it is. And let me just clear all the output just so that we can work with it interactively. So in the beginning, we just have some basic syntax like data types and operators. And this is similar to a number of different languages. But the one difference is Python is interactive, so we can try things out just by typing them in and entering them. So obviously there are numbers like integers, floating points, booleans, and complex. So here's an integer. And of course we get our normal warning from Google Colab, which we can safely ignore. Takes a second for the runtime to connect, but there we go. And since we're in a Jupyter notebook, it works interactively. So we just print out the number 11. So here's a floating point number, right? And here's a Boolean value true, and notice it's capitalized. Similarly, there's a false. Right? If you use lowercase, that's going to be treated as a variable. So remember that Python is case sensitive. One interesting difference between Python and many, many other languages, with the exception of maybe Fortran years and years ago, is it has built-in support for complex or imaginary numbers. So here's a number that has both a real and an imaginary component, 1 plus 2j. And j is used as the square root of -1, or the imaginary constant. So this is useful for engineering, and it follows the engineering practice of using j for the imaginary constant rather than I. So there's a value called none, which is kind of like null if you're a SQL person, or null in Java or JavaScript. So if you assign a variable to none and print it out, it's just going to come out as none. Now Python is a dynamically typed language, so we don't declare data types in Python. Variables take on the value of whatever type they hold. So that's very convenient because we don't have to define types everywhere, but sometimes you may not be sure what type you have, and there's no easy way to determine that just by looking at the code. But you can determine this dynamically by using this type function here. So if I have a variable and I assign it to 12.0 and I execute type of A, that's going to tell me it's a float. There's a similar method dir, which we'll see in a second, which gives us more details about what we can do with a particular type. So this is a string. We can define it in single quotes. There's no concept of a character or a single character in Python. It's always a string. And even a character would be just a string of length 1. We can also define a string with double quotes. That works as well. And that's convenient because sometimes we may want to have quotes within quotes, single quotes or double quotes and other quotes. So that's a convenient way to define strings. If we want to get the length of a string, we can use the len method like this, or len function. And so that tells us its length of 11. If we want to select a single character, which is itself a string, we can use this bracket syntax, and notice that strings are zero-based. Indices are zero-based in Python. Like a lot of modern languages today, Python checks array bounds. So if we were to index a string well beyond the length of the string, we're going to get an index error, or string index out of range. And one of the nice things that Google Colab does is we can search on Stack Overflow. Whenever it has an exception, it will automatically provide this link, so you can click on it and it'll go to Stack Overflow. You can try that out and see how well it works. So interestingly, Python has this curious ability to use negative indices. And negative indices don't give you an array index out of bounds. What it does is indexes from the right side of the string, from the end of the string. So -1 refers to the last character, which is the G. Python also has this very nice way of indexing. We can specify a range, the beginning and the end. And this is a half-open interval, so this is going to include the first character, but not the 5th character. So let's see how that works. So we only get sum and a space. So the length of this is going to be 5. So it's going to include 5 characters, not 6 characters, because the last index is not included. So that's what's called a half-open interval. And that's common in a number of other languages as well. And we can use negative indices with ranges as well. Next, we'll look at a little bit of string formatting. Now that we've learned some basic Python syntax, let's look at a couple of different ways that we can format strings. So there are 2 ways you can format strings in Python. One is using the printf style, and one is using the format method of the string object. You can use either one. The printf style is a little bit older. It has a few little quirks, so generally the format method is preferred, but both of them are fully supported, so you're free to use either one. And I still use the printf method quite a bit these days because I just learned the printf method, and that's just what I'm used to. But as we'll see, the format method is a lot more flexible. So let's look at a couple of examples. First, let's look at the printf style formatting. So here I have a variable, and I'm going to just assign it to an integer 42. So I have a string here. The answer to the ultimate question of life, the universe, and everything is, and of course we know the answer is 42. But we want to interpolate or substitute the variable or the value of answer right here. And we do that using a format specifier. We use the %sign and a conversion. And in this case, D means decimal conversion. This is a decimal number, an integer, and we want decimal conversion. And to supply the argument, we use the interpolation operator or the %sign. This is also used for modulus or modulo for integers, but here with strings, it's used as the string interpolation operator. And we just supply the variable, and it's going to make that conversion and substitute that into the string. And if we run it, we see the answer to the ultimate question of life, the universe, and everything is 42. Now, if we have multiple values that we want to convert, we have to use a tuple over here. You see, let's say we have 2 variables, length and width. We can't just supply those as a list of values. What we have to do is put that into a tuple, and this is why this is one of the quirks about the printf style. So I have 2 variables, length and width, and notice these happen to be floating point values. There's a decimal point there, so they're floating point. So here my string is going to be, the dimensions are, and I'm going to use this format specifier, %.toF. And what that means is convert this as a floating point number and include 2 digits of precision to the right of the decimal point. We can also include a width if we want to, but I didn't include that here. So dimensions are %.2f feet long and %.2f feet wide. I use the string interpolation operator, and I supply both variables as a tuple. This is called a tuple. When I have a parentheses and a list of values, this is what's called a tuple. And if I run that, you see the dimensions are 8 feet long and 4 feet wide. And you notice the 2 digits of precision to the right of the decimal point in both cases. This works well, but as you can see, if I use the length multiple times in this string, I would have to include length multiple times in this tuple. And I would have to include them in the same order as they are used in the string. So that's why it's somewhat limited, and that's one of the reasons the format method was introduced, and it's much more flexible. So let's look at the same examples using the format method. So I have the answer 42 here, and I have the same string, and if I use the format method, I include that in a slightly different way. In the string, I use curly brace, and in this case, I'm going to specify an index, an argument index. And here, the 0 means argument index 0, and this is 0 base. So if I have multiple arguments to this format method, the first one would be 0, the next one would be 1, and so on. So here I'm referring to the 0th argument or the first argument, and the :D means I want decimal conversion. All right, so let me run that, and you see I get the same result. So there's another way I can refer to arguments using the format method, and this is what makes it more flexible. Let's say I have 2 variables here, length and width. I can refer to arguments of the format method by name, not just by order. So here I'm going to refer to the length argument. The dimensions are length colon .2f, same format specifier, feet long, and width colon .2f, feet wide. And you notice that I can refer to these arguments in any order, because in the format method, the arguments were width and length in that order. Width equals width, length equals length. But I refer to them in a different order. And the other advantage is I can refer to length many times in this string. So I only need to include variables one time in the argument list, and then I can refer to them many times in the string. And if I run that, we get the same results as before, along with the 2 digits of precision to the right of the decimal point in both cases. So that gives you some basic ideas of the differences between the two. If you want to know more details of how they work, I've provided links to each of these. So in the case of the printf style, it explains that it has a few little quirks, and that's why the formatted string literals are preferred. And the quirks that it has to do with displaying tuples and dictionaries correctly. But still, it's easy to use, and I still use it quite a bit. And this gives you a lot of detail on how it works. It has a number of different conversions, and these conversions are very similar to C and Java and a number of other languages. It has a long history. So if you're familiar with those languages, this is probably familiar to you as well. Similarly, the format method, it's much more powerful, much more flexible, so it has a mini language built into it. So there's a lot of detail that you can learn about it, a lot more that you can do than we just talked about here. So it has similar conversions, just like the printf style, but it has a lot more capability. So you can just specify arguments in order like this without including a format specifier or without including a conversion, or you can include the conversion type if you like. There are a number of different examples that show you how to use it in different ways, including things like date time and so on. So that's a little bit about string formatting. Next, we're going to look at type conversion and flow control. Let me mention one other quick Python tip. This has been introduced in Python 3.6. This is what's called literal string interpolation. And let me show you what that means. We've used format in a couple of different ways, used the printf format style and also the format method. And those work, but let's look at something else. Let me create a couple of variables here in my notebook. Let me click on this cell first. And I'll say pi equals, if I get it right, 3.1415926535897. I think that's right. I kind of used to memorize that number when I was younger. I don't know why I did that. Kind of silly, I guess. But that's as far as I can remember. And let me also create another variable. I'll say message equals hello world. Like that. So if I run that cell, it executes, doesn't produce any output. And of course I can, print out each one of these variables and it'll give me the output. Same thing with message. Okay? Pretty simple. So if I was to use printf style formatting, let's say I would say pi equals %f %pi, like that. We're familiar with that. That gives us some formatting, and we can format it a little bit better if you like. And you can see there are some limitations, and where we could do it with the format method, but that's also a little bit more complicated. There's another way we can do this using what's called literal interpolation. If I print a string like this, pretty obvious. It just says pi equals parentheses pi. Now watch what happens if I put an F in front like that. I go away. And then I run that. Notice what it does is it replaces this marker here, these curly braces, with the value of this variable pi. So it's kind of like the format method, but we don't have to do that. We don't have to call the format method and put in all the variables and all that business. So it's much simpler. So this is supported only in Python 3.6 and greater. So this was introduced in Python 3.6. We can also do this with the message. So I could put in message here. And notice it does that string completion, which is very nice. All right, and you see we got the result. So this is a very nice feature. The only downside, of course, it's Python 3.6 and later. And it turns out that Google Colab does use a version that's greater than Python 3.6. So we can check actually what version Google Colab is running, and I think we can do that by importing the sys module, and then I think we just print out sys.version. That's it. So if we run that, notice it tells us it's version 3.6.9, so which means that it will support this string interpolation with the F. And I think we can do it with a capital F as well. Let's see. I can't remember if that's true. Yeah, that works as well. So you can do lowercase f or capital F like that. So that's another convenient way to perform string formatting using what's called string literal interpolation. Let me mention a couple of more details here. So you see here when I ran this and I print out pi, I get all these digits here. So if I want to format that a little bit better, let's just say I wanted 4 decimal digits or something like that, I can also use the same formatting that we used with the format method. So I can say colon dot for F, for example. And notice what that does, it gives me 4 decimal places to the right of decimal point, and it also does some rounding there, which is convenient. And of course I can put in a width specifier in here if I want. Let me put in more so that we see something more convenient, right? You see it put spaces up there, and if I want to prepend it with zeros, I can do that too, right? All of that works. One other thing I can do, which is pretty cool, is if I want to multiply by, I can put in any Python syntax I want in there. So if I want to multiply pi times 2, I can do that as well. So I can put any Python expression in there I want, including, let's put in, let's do this. The system version is, and I'll put it in curly braces there, and I'll do sys.version like that. If I run that, and I can take out this line, that's not going to do anything. And it says system version, oops, what did I do wrong? I forgot the F. Let me put the F in front, and then we run that. There you go. System version is 3.6.9 and so on. It gives us more details as well because that's what sys.version returns. So very powerful, very easy to use. So that's what I try to use as long as we have Python 3.6 or greater. Now let's look at type conversion and how that works in Python. As mentioned before, Python is a dynamically typed language, so we don't declare variable types, but values do have types. So if I was to assign this variable pi to this number, you notice this is a floating point number because it has a decimal point. I can use this function type to tell me what the type is, and it tells me that it's a float. But let's say I wanted to convert this number, which we know is a floating point number, into an integer. I can use this syntax using the type, parentheses, and the variable, and that will convert it to an int. And if we do that, it does this by truncation. So let's say I choose a number that's bigger than 3.5. Let's try 3.5. It's still truncated, right? It does not round up. It does not round up. So if I wanted to do some rounding, what I could do, a common trick, is add 0.5. So that's going to round up. So if we had 3.4, that's still 3. And 3.5 becomes 4. All right, good enough. Now let's look at another way we can do it. We can convert a floating point number into a complex, like this. So notice the imaginary part is 0 because this only has a real part to it. So here's a little bit more about complex numbers. So if I was to take this quantity and assign it to a variable, let's say a, and then I run this again, we have the same result, but now a has a value that is complex, and I can access either the real or imaginary part of it. So if I select the real part, if I use dot, and I select the real part, I get just a real number. Or if I select the imaginary part, I get 0. Or I call the complex conjugate, and this one is a function or a method. And I get the complex conjugate of that, which is minus 0j instead of plus 0j. Since the imaginary part is 0, we don't, it just becomes minus 0. So that's a little bit about complex numbers. If you are not familiar with complex numbers, it's really not that important. It's just if you're used to using them and you have some interest in how they work in Python, that's how it goes. So another thing I can do is if I have a string, I can also convert that to an integer. So let me do that. And you see it turns it into an integer number. Notice if I have a string that is not convertible to an integer, I get a value error. And of course I can search on Stack Overflow for that. Similarly, if this has a floating point component to it, that doesn't work either. So this has to be a decimal number, meaning it cannot have anything other than just digits in it. I could try something similar for floating point values. Let me try float and 42. And I get a floating point number. And if I put float 42.5, that works as well. I can go the other way if I want to convert a decimal number or an integer into a string. So that converts a decimal number or an integer to 42. If I put in a floating point number, let me put in my variable for pi, that works as well. All right, but notice that there isn't any limited precision here. It's going to give you the entire number. So that's where you'd want to use string formatting if you wanted to limit the precision of the number that it produces. So bool is very interesting. So bool, Python treats a number of different quantities as true or false. So 0 and 1 are treated as true and false, as well as a number of others. So including the value none, that's also treated as false. So the concept of a Boolean is very important in the next section where we'll talk about flow control. Python, like many imperative languages, supports flow control like if statements, for loops, while loops, and so on. They work very much the same way as you would expect, but there is one significant difference between Python and just about every other language that's popular today, or at least most of the languages that are popular today. In order to group statements together, we use indenting or tabs, or spaces or tabs to indent or group statements together, and we'll see how that works. So let's look at this first example. This is a for loop. So Python doesn't really have a for loop like C or Java where we specify begin and end index. What we can do is create a range object, and a range is kind of like a list, and this range by default, if I don't give it a starting number, it starts from 0. So it goes from 0, 1, 2, 3, and 4. It doesn't include the last value. It's considered a half-open interval. So if I loop through this, and notice to include any statements that are within the for loop, I must indent, and spaces are preferred. So typically 4 spaces are used. You can use a tab, but spaces are preferred. So let's run this and see what happens. So what this says is it prints out the values 0, 1, 2, 3, and 4 in this range, 0, 1, 2, 3, and 4, and the square of each value. All right? Pretty straightforward. So let's look at another example. I'll do the same thing, but I'm going to use a while loop. And a while loop, I'm going to use an index. I'm going to start from 0, And here the condition I'm going to use is while I is less than 5. So what that means is it's going to iterate through these statements while the value of I is less than 5. And at the bottom of the loop, I'm going to add 1 to I. So let me run that, and it produces exactly the same results as before. So notice this indent, the way we do that, and how these are all lined up. And this is very important. If you were to indent this incorrectly, let's say that I had an extra space there. Let's see what happens. We get an indentation error. So white space is significant in Python. So in a single statement, at the end of a statement or in the middle, white space doesn't matter. But the beginning of a statement, white space is significant, unlike many other languages. So this is a very common problem if you're a beginning Python developer. So just be very careful with that. And one way to avoid a lot of these problems is to make your code inside of a loop or an if statement or anywhere where you have to indent, don't make it too long, because if you have a page full of code, which you shouldn't do anyway, then it becomes very difficult to follow what's indented and what's not. So be careful of that. So here's an example with a for loop and an if-else statement. And if-else works mostly like other languages, but it has another slight difference. So here I'm going to loop through a range starting from 1 to 10. It's going to start at 1 and it's going to go up to the value 9. 1, 2, 3, 4, 5, 6, 7, and 8, and 9. It's not going to include 10. That's just the way the range works. And what I'm going to do here is if the value modulus, this percent sign is modulus when I use it with integers, if the modulus 2 equals 0, where that's the remainder, if the remainder is 2, that means that this number is divisible by 2. Similarly, if it's divisible by 3, I'm going to print it's divisible by 3. So notice here I'm doing else. I'm effectively doing an else if. But Python has a peculiar keyword called elif for that purpose. We don't say else space if. We use elif like this. Right? And there is an else clause at the end. Like that. All right? So if I run it, you notice I get 1 is not divisible by 2 or 3, 2 is divisible by 2, and 3, and so on. So one other detail that I should mention is you notice anytime I have one of these flow control statements, I have to include a colon at the end of the statement to mean that the beginning of the group of statements below. So if I don't include that colon, that's kind of like the end of a statement. So if I don't include the colon, I'll get a syntax error, meaning that there's something missing there. So remember to include that colon at the end of any conditional statement like that. And some of that is due to the fact that Python doesn't have a statement terminator. The end of a line is considered a statement terminator in most cases. In the case of Java and a number of other languages, semicolon is often used, but in the case of Python, end of line is considered the end of a statement. That's most of what you need to know about flow control in Python. There are a few more examples of flow control, and we'll see those in future lectures. Python supports a rich set of built-in data structures, and we're going to look at a couple of them here. The first one we're going to look at is a list. And a list is kind of like an array. It can grow as needed. It's perhaps analogous to an array list in Java if you're familiar with that. The one difference is that a list in Python can contain any data type you like. So let's look at an example. Here's a list. I define it with square brackets, and I can initialize it with some integers like that. So if I run that, you can see it creates a list. I can, of course, add any data types I want. And they don't have to be of the same type. I can even create a list within a list. Right? So lists are kind of like arrays. That's about as close as Python gets to an array. If I want to get the length of a list, I can use this len method. That gives me the length. If I want to iterate through a list, there's a convenient for each syntax like this. So it looks like this: for value in A, where A is a list, and this was a list that we defined above. And then I can print each of the values. So that loops through each of the values in the list, prints each one. Fairly straightforward. Of course, I can have nested loops if I had a list within a list. I can add to a list by calling the append method. So I create a list here with 3 elements, and then I call an append method, and that appends and modifies the original list. So you notice now I have a new list with 4 elements in it. I can add to lists using the plus operator with lists. So I have 2 lists defined here. One, this list A that has 1, 2, 3, and another list B that contains 7, 8, 9. And if I add the 2, you see I get a new list with the 2 of them appended. Often when we're working with lists, it's common to loop through a list and create a new list, modifying the original. This is kind of like a map operation if you're familiar with functional programming. So I can do this conveniently in Python using what's called list comprehension. And the way I do that is I write square brackets, and inside of there I can loop through a list, or in this case a range, which is kind of like a list. It has a list of numbers from 0 through 9. Remember, 10 is not included because it's a half open interval. And for each value, I'm going to multiply it by 2. So what this is going to do is produce a list with values 0 through 18, all the even numbers. And you see it has a list 0 through 18, all even numbers. I can reverse a list using the reverse method, like that. And if I want to sort a list in place, I can use the sort method. All right, that sorts the numbers again. Of course, let me mention how we index into a list, and we do that using square brackets. So if I go to any of these lists that I have here, so I had this list A, and it has these values, I can use square brackets and select any value in that list. And the list is 0 based, so the first one is going to be index 0. So if I index 9, that's going to give me number 18. If I go past the end of the list, I'm going to get an index error, or list index out of range. All right? But there is, similar to what we saw with the case of strings, I can use a negative index. I can use a negative index, which makes Python a little bit clever compared to other languages. So what that means is it's going to start from the end of the list. So -1 is not an error. What that means is refer to the very last value. And -2 would be the value next to the last value, like that. It's very clever. In addition, I can use a range. So I can select, let's say, the first to the third. So that's going to give me the numbers 2 and 4. So this would be the first to the third. And one way to remember this is the length of the resulting array is always going to be the end index minus the beginning index. So 3 minus 1 is 2, so I'm going to get a list of 2 elements, and it's going to start from the first index. And I can also use negative indices if I want. If I use -3 as the end index, -1, -2, -3, -1, -2, -3. So yeah, that's the last one. So it's going to give me 12 as the last value. Right? So lists are very flexible. There's a lot you can do with them, and this range, it makes it even more powerful. So there's a lot more that we can do with lists. I've just shown you a little bit of how they work, but you may want to experiment with them on your own to get the most out of them and learn how they work. Let's look at another data structure known as a dictionary. And a dictionary can contain key value pairs, and it's similar to a Java hash map if you're familiar with that. So let's look at an example. I'm going to define a dictionary here, and to define a dictionary, I use curly braces like this instead of square brackets. If I use square brackets, then it's a list. If I use curly braces, then this is going to be a dictionary. And I can initialize it, with key value pairs, and the keys and values are separated by a colon like this. Now the keys and the values can be any data type I like. In this case, I happen to use strings, and that's not uncommon, at least for the key to be a string. That's a common use case. So what I happen to have here are names and instruments that each of these people play. So I have David St. Hubbins, and he plays rhythm guitar, Nigel Tufnell plays lead guitar, Derek Smalls plays bass, and so on. So if I run this cell, I can see all the values that are in this dictionary. Now, if I want to access a particular value by a key, what I can do is specify the key name. And let me put in one of the key names here. I'll put in Derek Smalls. So what that's going to return is bass, because that's the value associated with that key. Notice if I supply a key that does not exist in the dictionary, I'm going to get a key error. That differs from some languages where they might return null. In the case of Python, it returns you get a key error. So one way to find out if a dictionary contains a value, I can use a syntax similar to this. I can say if I put in foo in band, that's going to return a Boolean, and it says false. There is no key named foo in the band. Whereas if I put in the key Nigel Tufnell, let me do that right. I'll paste it so I get it right. That returns true. So I can test if a key exists in a dictionary by using the in keyword. So similarly, if I want to iterate through all of the keys in a dictionary, I can use a for each syntax like this, for name in band. So this is going to iterate through all of the keys. And given the keys, and then I can access the value associated with the key and print out the name and the instrument for each player. And you notice it produces the output we expect. Now in this case, it looks like the keys appeared in the order that we defined them in this dictionary, and that just happens to be a coincidence. You can't assume that the keys and the values will be returned in the same order that we defined them in the dictionary. That differs from a list, whereas in a list, you'll always get them in order. A list is ordered, whereas a dictionary is not necessarily ordered. I can also return both the key and the value at the same time in the for each, like this, for name, comma, instrument. And to do that, I have to use in band.items. .items. And so that's going to return both the key and the value like that. So this loop should produce very much the same results as the other one. If I want to modify a value in a dictionary, I can specify the key name like this, band, and then the key name, and then assign it a value. So let me try that. And then I can loop through the list as I did before and print out all the values. So I have the names, and this time, actually, I've got this wrong. I have the key as the instrument and the value as the name, and that's not what I want. I want it the other way around. And I think the problem was originally when I created this original dictionary, I had the instrument first and then an unknown name. So what I really want to do is delete this entry and then replace it. So let me do this. Let me put this here, and this is what I want. I want the name, and then that equals the instrument, like that. So that's what I want. So that works. Unfortunately, I've got this drums entry, which is wrong. It's backwards. So if I want to delete that, there's a convenient method I can use. I can use del to delete an entry, and I would specify the dictionary and then the key that I want to delete. In this case, I want to delete drums. So let me delete that. And then I'll rerun this cell here. And notice even if I reassign it, it looks correct. So now I have just names and instruments that way. Names and instruments the way that I want. Notice that this key was deleted before, so if I run this cell one more time, I'm going to get a key error because drums no longer exists. And that's what we expect because we deleted it already. So that explains a little bit about how dictionaries work. They're not too difficult to use, and they're also widely used. Next, let's look at functions and methods. And they're very similar, but they differ slightly. As we've seen, this len is a method. It's a function, I should say. Let me say this is a function. And it's a function because it takes an object as an argument like this. So the argument here is a equals some string, and I'm supplying that to this function like that. And I'm sure you've seen that in many other languages. Now what's different is this upper is what's called a method, and upper operates on a string. And I don't supply this string as an argument. What I would use is a.upper or a.method. And if you're familiar with object-oriented programming, that's the way you would call a method on an object. So if I run that, what it does is returns a new string, which is the uppercase version of this original string. So a function operates on an object, and we put the argument of the object inside as in the parentheses of a function. But in the case of a method, we apply that method using dot and then the method name. So how do I know what's a function and what's a method? Well, given any object, I can use this function dir, and it's going to tell me all of the attributes and methods that are part of an object. And you can do this with any Python object if you're not sure what you've got and what you can do with it. So here, let me create a string, and let me call this method dir a, and then that's going to give me all of the fields and methods that it has. And there are quite a few. There are not a number of these that have underscores and so on. There is alpha, it tells you if it's alphanumeric, if it contains alphabetic characters, if it's alphanumeric, if it's decimal, if it's digit, if it's lower, if it's uppercase. Those are all returned true or false. I can replace values, I can find values, I can split them. There's lots and lots of things I can do with a string. Let's pick one of them. Let's just pick is alpha, and let's see what that does. So let me comment this. In a comment in Python, I use this number sign or the hash in front of a line, and that comments the entire line. So if I run a.is, and the nice thing about Google Laboratory is that it will prompt for the methods. So whenever I call a method, I have to use these parentheses to make sure I'm calling a method. And it says false, and probably because it has a space in it. So let me see if I take out the space, and if I run it, what do I get? Then I get true. Okay, that's what we expect. Right? That's what we expect. Now notice what happens if I don't include these parentheses here. It's going to tell me this is a function. So this returns a function object is actually what it returns. It doesn't actually call the function. So I want to make sure I include the parentheses. So what if you want to define your own function? And the way you do that is using this keyword def. Keyword def, and I define the name of my function, and I can include any number of arguments I like. And in this case, I've only specified one argument. I can specify more using comma with more arguments. And like in the other variables, I don't need to define the type of the argument. So what this is going to do is compute the average of this array. So this assumes I'm going to pass in an array or a list, and it's going to compute the average of all the values. And the way I'm going to do it is first to get the length of the array, which is n, which is going to be the number of elements. I'm going to assign a value total, which is going to be a floating point number. And I'm going to loop through all of the elements in the array, add to the total, for all values, add to the total. And then I'm going to define the total by n, and that gives me the average. Now to call that function, what I would do is use the name of the function, parentheses, and then any arguments I want to supply. And I have one argument, in this case it's a list, and I'm creating the list and calling it all at once. So if I do that, the average is 2. And if I add those up, is that correct? almost correct. So 2 plus 3 is 5 plus 1 is 6, and I get 2. Is that correct? Yes, that's right, because there are 3 values, so 1 plus 2 is 3, plus 3 is 6, and 6 divided by the number of values 3, so I get 2. So that's right. So that does compute the average. So this is a case where the function returns a single value, a single integer. It could return any object, it could return a string, it could return any type I like. I can also return a tuple or multiple values. And remember a tuple, we saw that earlier. A tuple is multiple values contained in with parentheses around it. So it's treated as a single object with many values in it. So one place I might want to use this is, let's say I want to compute some statistics. And in this case, the statistics, it's going to compute the average and it's going to compute the standard deviation. So I want to calculate both and return both of those values. And the way I'm going to do it is I'm going to pass in an array as I did before, and I'm going to call my average function that I've defined up here. That's going to compute the average. And then to compute the standard deviation, I'm going to get the length of the array, create a variable called total. I'm going to initialize it to 0. Iterate through all the values in the array, and then compute the variance. And the variance, if you remember your statistics, is the value minus the average. A sample minus the average. That's the variance. And then what I need to do is add the square variance, or the sigma squared. So I add up all the square errors. These are like the errors, and then I square them, add them all up. And then to compute the standard deviation, I'm going to divide that total by the number of samples, like that. And then I'm going to return both the average and the standard deviation. So let me call my statistics function to test this. I'm going to give it the values 1, 2, and 3, and we know the average should be 2, and hopefully it'll compute the standard deviation correctly as well. So it says it returns a tuple. The first value is the average, and the second value is the standard deviation is 0.666 repeating. All right? So that's how that works if I want to return 2 values. So one other thing I can do is, if I have a function that returns a tuple, I can conveniently assign it to 2 variables like this by defining a tuple on the left of the equal sign. So this is going to produce two variables, average and std_dev, or standard deviation. And if I know this function returns a tuple of 2 values, I can assign it to 2 variables conveniently like that. So what that says is it prints out the average is the average right here, and the standard deviation is 0.67. Notice this rounds off, right? Because I used a precision of 2 decimal places to the right of the decimal point, a precision of 2 to the right of the decimal point, and notice that rounds up. All right? That gives you a basic idea of how functions work and how they're defined. Next, we'll look at classes and how they're defined, and that involves a little bit of object-oriented programming. So if you're familiar with that, it should be reviewed to you, other than just the syntax that's different in Python. If not, you'll learn a little bit about object-oriented programming. Like many modern languages, Python also supports object-oriented programming. So we can define classes, we can define inheritance and subclasses, and all of the things you would expect from other object-oriented languages. So we'll look at a basic example here. If you're not familiar with object-oriented programming, this will be a little new to you. If you're familiar with it, all we're going to learn is the specific Python syntax. And now we could spend an entire course just on object-oriented programming, and we're not going to do all of that here. We're just going to go through a little bit just to give you an understanding if you want to define your own classes and how to go about doing that. We've already seen how you can call methods of an object where an object already has methods, and you use the dot and then a method name, and then the arguments that might have to call a method of an object. But if I want to define my own object and its own methods, this is how I'd go about doing it. And we're going to go through this through a very simple example. I'm going to define what's called a class. I'm going to define a class, and I'm going to call it bank account. And it's customary in a lot of cases to make classes start with an uppercase letter. You don't have to do that, but that's a common practice. So this class, I can define its superclass or its parent class. And in Python, that's called object, this object right here. I'm not going to get into the details of inheritance and everything here. We could spend a lot of time, but for the sake of argument, this is if you're just defining a class and you don't know what you want for the superclass, just define as object. And inside of it, I'm going to define several methods. So these look like functions, and they more or less are functions. What differentiates these, what makes these methods as opposed to functions is they include an initial argument called self. And in Python, self refers to this the object we're in, or myself. It's similar to the keyword this in Java, if you're familiar with that. And we'll see how this is used. So this one method I'm defining here is special. It's what's called the constructor. And this method is going to be called whenever I create an instance of this bank account. And we'll see an example in a second. So this bank account, I'm going to supply, when I create it, I'm going to supply 3 arguments: an account number, an initial balance, and an interest rate, like you would for any bank account whenever you're creating a bank account. So these are arguments that are supplied to this constructor method. And it's a method because it has a self argument. And that self is useful because what I'm going to do is take these 3 values and save them as part of the object. I'm going to save them as attributes of this object, right? And the way I refer to this object and its attributes is I use that keyword self and then any variable name I want, and in this case I happen to call it the same name as the field, or the argument I should say, and I'm going to save them. So if I do that, all of these values will be saved as part of the bank account object when I create it. And we'll refer to it later. Next, I'm going to define a few methods. One of them I'm going to define is a deposit method. And this is a method also because it has the first argument is self. And when I deposit into this bank account, I'm going to give it a certain amount that I'm going to add to this bank account. And the obvious operation we want to perform, if we were going to deposit a certain amount of money, we want to add to the balance. And the balance is an attribute that's part of this object that was initialized when we created it using the constructor. And what we're going to do is add the amount to the balance. And we can do that at any time, right? We can add any amount to the balance whenever we make a deposit. Now we might want to make a test here to make sure the amount is positive. That's a possibility, but I chose not to do that. I'll define another method, withdraw, and this also takes an argument self, so this is a method, and I'm going to withdraw a certain amount. Now here I'm going to do a little bit of a check. I'm going to check to make sure that the balance is greater than the amount we're trying to withdraw, because in this case we're not going to allow overdraft or the ability to withdraw more than the balance that's in the bank account. So if the balance is greater than or equal to the amount, I'm going to subtract that amount from the balance and then return the remaining balance. That's just the way I'm going to define this method. Now, if it turns out that the balance is less than the amount I'm going to withdraw, I'm going to do something special here. I'm going to raise an exception. And we've seen some examples of exceptions before. We've seen key errors, we've seen index errors, and so on. So this is an exception I'm going to raise, and I'm going to raise that if there is insufficient balance for withdrawal. So that's going to be a message that's going to be returned as part of the exception, and I'm going to include some details that there's only certain amount or certain balance in the account when you try to withdraw. So it's not going to do the withdrawal, it's going to raise that exception. And we could present that to the user as an error message. Here are a few other methods. If I want to add some certain amount of interest, so maybe every month I would recompute the interest. So the way I might do that is add to the balance the current amount plus the interest rate divided by 100, because if the interest rate is in a percentage, I will divide that by 100 and perform this calculation. Simple interest calculation. And I'll add one more method if I want to transfer some money to another account. And so I'm going to supply 2 arguments. One of them is the other account I want to transfer the money to, and then the amount that I want to transfer. And the way I would do that is given the other account that I want to transfer to, I'm going to call its deposit method. I'm going to deposit money into another account, and the amount that I'm going to withdraw is from this account. From this account, or myself, I'm going to withdraw this amount and transfer that to the other account. All right. So do I have a little bit of bug here? I think I do, because the withdraw method, I'm returning the balance, and actually I don't want to do that. What I want to do is I want to return the amount here. That's what I want to do. All right. That's what I want to do. Okay. So what whatever amount I'm going to withdraw, that's the amount that I'm going to deposit into the other account. Okay. And then finally, this is an interesting method that you can include in any class. It's this str method, this underscore str, and it has no other arguments than self. And what happens is if you print out any object, it's going to call this method. This is kind of like the toString method in Java, if you're familiar with that. And we can return a string, and what I'm going to do in this case is return the account number and the balance of this account. All right. So that's our class. Let me run that. So that defines the class. And I've got a little bit of test code here. So I'm going to create two accounts, a checking account. This is the account number, balance, interest rate, and I have a savings account account number, balance, and interest rate. So the checking account has $100 in it, and the savings account has, say, $1,000 in it. And they have slightly different interest rates. So the first thing I'm going to do is print checking and savings. Now, if I just print these objects like that, it's going to call this str method by default. And that's just like calling the toString method. I could refer to it directly, but this does the same thing. And then I'm going to add interest to both accounts. And then I'm going to transfer a certain amount of money from the checking to the savings. I'm going to transfer to the savings to the checking, and I'm going to transfer 500 to that, and I'm going to print out checking and savings. So let's run that and see what we get. So what happens is originally I had $100 in my account 101, which is my checking. 201, in account 201, I had a balance of 1,000. I computed a little bit of interest, and then I'm going to then I transferred money. So in the checking account, I now have 601, right? Because I added $500 to the checking account, and the savings account has 550 because we took 500 away, but we also added a little bit of interest. So that looks correct. Now let me try something here. Let me now transfer $1,000 to the checking. Let me do that in another cell here. Let me copy this code. So now what's going to happen? Now we know that the savings only has 550 left in it. So if I transfer 1,000 out of it, what's going to happen? I get an exception. And you see the exception that I get. It says, exception, insufficient balance for withdrawal, only 550 in account 201. So account 201 was our savings account. There's only 550 in there, and so we cannot transfer that. And here's something nice about Python. It's common in a lot of languages that support exceptions. It tells you exactly where the stack trace of how the code executed and where it failed. So it first started when in this method, savings transfer to checking, right? That's this method when we called it. And there's an additional stack frame. It called this other method withdraw. And in that withdraw method, it tried to transfer this amount of money, but there wasn't enough in the balance, so it raised this exception. So, and then we have the value of the exception. So if you're familiar with stack traces in other languages, it works very much the same way. So whenever you get something like this, look at the error message that you get, and then you can go backwards and figure out, well, where exactly did that occur? Where did that error occur, and why did it occur? All right. So that's a little bit about object-oriented programming and how to define classes. So we'll have an assignment where you can experiment with this and play with defining classes. This isn't critical for this course, but in some cases you may want to define a class if you're building something larger than a few lines of code. So now let's look at how we read and write files in Python. There are many ways to do that and many methods to read all kinds of things and write all kinds of things in Python. We're just going to learn a few of the basics here, and if you want to know more, there's plenty of online documentation where you can learn more about it. Let me show you a short example where we want to write a file, and we do that with this simple syntax. As you know, when we read and write files, we want to open a file and close it when we're done with it. And that can be error prone if we forget to close a file. So Python has a convenient syntax, this with syntax. What that will do is, in this case, if it's going to open a file, I'll say with open. It's going to open the file, and then I'm going to specify write. This is the name of the file I'm going to open, and I'm going to specify, I'm going to write to it as f. And this f is going to be of like a file handle, or what's returned from this open object. And any code inside of this with clause, or this block here, is going to be performed using that variable f, or the file. And at the end of that block, it's going to close the file. This is kind of like auto-closable if you're familiar with that in Java or other languages. So this is going to open this file for writing and write 2 lines to it. And notice this f.write, I have to specify the new line. It does not necessarily include the new line. So when I run this method, it's going to create a file and write these lines to it. And if I click on this left pane in Google Colab, it'll show me, if I click on this Files tab, it'll show me all the files that I have here. And right now I don't have any files other than the sample data that exists. So let me run this code. It doesn't print anything because there's no output here. And if I go back, and you notice now I have this sum file that was created, right? That's the file that's created. Now if I want to read the file, I can use similar syntax with open, and I just specify the file name. I can specify R if I want to read, but if not, it's by default, it's going to read as f. And then I'm going to call f.readLine, and what strip does is a method on the string. This is going to return a string. And strip just removes any white space. So we had a trailing new line. This read line will include the new line. We're going to strip that off and print it out. So if I call that method, it should return the first line. Which it does. Right? Now, what I could do is also, now if I run it again, it's still going to return just the first line because every time it opens, it starts from the beginning of the file. Now, I can read all the lines in the file using f.readLines, and that's going to return a list of all the lines. So if I call that, notice I get a list, and it has all of the lines that are in the file, and includes the new line in each of those lines. And remember, if I want to eliminate that new line, what I could use is list comprehension. I could iterate through all the lines in this list and call the strip method to remove the new lines. So that's a little bit about reading and writing. If you want to know more, there's plenty of documentation and plenty of examples all over the internet. Google is your friend here. Not hard to read and write files in Python. Let's just wrap up with one more concept that's kind of important, modules. So in many cases, you may want to import or refer to other modules, and in Python, for the sake of argument, a module is just another file that contains other Python code. And as you know, there are many, many libraries and many, many modules that you can import that have lots of capabilities. And we use those using the import keyword. And the syntax looks like this. We would import some module, and modules can also contain submodules. So this matplotlib would be a module, and it may be a directory that contains a number of other Python libraries in it, or Python modules in it. So in this case, this is matplotlib. What I'm going to do is refer to that as PLT, right? Import matplotlib, and I'm going to refer to that module as PLT. And this is an idiom that's commonly used for matplotlib, and you'll see this for a lot of common libraries. I can also import a library and not give it not specify the module name. If I don't, or an alias for the module name. And if I don't, it's going to just import that, and I'm going to refer to that module using just the module name. So let's look at how we would use each of these. So the math module has a number of useful math functions in it. So here's an example where I'm going to create a list. It's going to create a range of numbers from 0 to 64, 0 to 63, I should say. And it's going to multiply each of those times 0.1. So I'm going to get a range from 0 to about 6.3. There are going to be 64 of those values. And then what I'm going to do is compute sine and cosine. And there is the method sine and cosine, which are functions, I should say, that are part of the math module. There are functions which are part of the math module. They look like methods, but these are really modules, not objects. So this is how I would refer to functions that are part of this math module. And of course, there's documentation to tell you what's all the functions that are defined in each of the modules. There's a little bit of list comprehension to compute sine and cosine for all of the values that are in this list X. All right. So I computed two lists which have lists of sine and cosine, and now I can plot them out. And this is a little bit of matplotlib, which is a plotting package for plotting graphs. And we're going to learn a lot more about matplotlib as we go on throughout the course. So what this does is plots it's a line plot. We give it a list of X values and a list of Y values. And we can plot another one, a list of X values and Y values. We can include labels and colors, line widths, and so on. And a legend, and label our axes, and so on. And finally, once we create that plot, we're going to show it. So let me run this. And you see it produces a beautiful sine curve and a cosine curve. All right? And you see the X and the Y and so on. So that shows you how to use modules. And you'll see plenty of examples of modules as we import them. And you'll notice that a number of libraries, they follow the same customary syntax for importing. Like in the case of matplotlib, it's almost always imported like this. Similarly, when we import pandas, it's always pandas as PD and so on. Those are just common ways that people import packages or modules so that so you see similar code in many different examples. In some cases, you might need a password for a database or other kind of resource that's password protected. You could hard code that password in your notebook, but as you can imagine, that's a security risk and you wouldn't want to do that. Fortunately, Python has a really convenient getPass module that can be used to prompt the user for a password while masking keystrokes so you won't see the password. So let me show you how that works. It's actually very easy to use. So first we need to import the getPass module like this. I'll run that. And then we can prompt for a password. And it looks like this: getPass.getPass. And I can specify a prompt. In this case, I'll prompt for, I'll just type your password like that. So when I run it, I'll get a prompt. It says your password and is waiting for some input. So let me put in a password and press return. It's important to press return, otherwise the cell will never complete. And notice the keystrokes are masked, so you don't see the keystrokes. So if I want to use the password, I can just refer to this variable right here. I'll just print it out so we can see what it looks like. And there it is. That's the password that I typed in. Of course, in practice, you don't ever want to print out this password because then obviously you're exposing what that is. But you could use the password in any of your code. So this is a convenient way to prompt the user for a password without exposing a security risk. So in this example, we're going to learn about logistic regression. And historically, logistic regression was a statistical method But we're going to learn about it from a machine learning perspective. And along the way, we're going to learn a lot about how machine learning models are built, how they work, how they're trained, and how they're tested. So what is logistic regression? Well, it's a way of classifying data into one of two categories. And it's a very important machine learning task, and it can be used in many different fields and many different domains. One of the most common uses today is to classify email as either spam or not spam. Given all the number of spam emails that are sent out on the internet today, there are millions and millions of spam emails that are sent from all over the world. If we didn't have a way to filter those out, our inboxes would be full of thousands and thousands of emails that we just wouldn't be interested in. And the way these spam classifiers work is that they're given examples of emails that are normal and emails that are spam. And they come in many, many different varieties, so these models have to be very general and have to learn the general structure of what a spam email is versus a not spam email. And they're not perfect. They do make mistakes, but fortunately they do remove the vast majority of spam, so at least the emails that we're not interested in are relatively small. So in this example, we're going to build a basic machine learning model from the ground up without any complex libraries. All you need to know is a little bit of Python and some basic math. So the particular problem we're going to solve here is to classify flowers. And this is a problem that has been solved many times before, but we're not here to come up with the best solution to this problem. We're going to try and develop a very simple machine learning model just to understand the ideas behind machine learning, how models are built, and so on. So it's purposefully made very simple, so it's easy to understand, and you can experiment with it on your own without a lot of complexity and without a lot of black boxes that are hard to understand. So this particular problem is actually quite useful. You can imagine if you were a naturalist in a specific field, you may want to classify a species into one of many categories. Those categories could be different types of animals, they could be insects, they could be plants, they could be rocks, you name it. And you've probably learned a lot of these different categories. And if you were a seasoned professional, it could take years of training to learn to properly classify any particular species. So in this example, we're going to use the well-known iris flower dataset to classify flowers into one of 3 iris species. And if you look over on the right, there are some pictures of these 3 different irises. And if you didn't know anything about flowers or iris, they may all look the same. And you may not know the difference between them. So what we're going to do is we're going to develop a machine learning model to classify them. Fortunately, the data set we have gives us examples of each of these different flowers, and it gives us a label, tells us which type they are, so we can use what's called a supervised machine learning technique to train a model. And along the way, we're going to learn a lot about the process of machine learning and how models work and how they're trained. Let's spend a few minutes just talking about the machine learning development process. The machine learning model development process is a little bit different compared with traditional software development. Machine learning models depend heavily on data, so it's extremely important to understand the nature of the data that we're using and how that data can influence our model, and also to understand why our model isn't necessarily performing as well as we might like. So in each of the examples in this course, we're going to follow a similar structure. The structure corresponds to the process of developing a practical machine learning model. And this is the process that just about every machine learning engineer or data scientist uses when developing a machine learning model. So if you look over on the right, you will see a number of steps. This is sort of a broad outline. There may be more details to it, but this is the rough outline of how it works. The first step, and it's a very important one, is to analyze the data. Before we write any code at all, we've got to analyze the data that we're going to be working with. The data is going to dictate the kind of model we're going to use. And once we've analyzed that data, we can then define a model. Choosing a model is based largely on experience, and you're going to learn a lot of that throughout this course. You're going to look at a number of different examples and learn how to choose a model based on previous examples. And that's what most people do. They'll look at a problem and try and identify other problems that are similar and find models that worked well for that kind of problem. Rarely do we try and come up with a totally different model that no one has seen before. That's kind of a research project, and that's an advanced topic that most developers will not get involved in. Usually, we'll try and find a model that's best suited to a similar problem. Then once we've chosen a model, we'll train it given our training data. And once we've trained it, we will evaluate the performance. We'll evaluate how the model performs against the training data and the test data, determine if it's accurate, and also identify cases where it's inaccurate and try and identify why it was inaccurate. And finally, we'll try and identify ways that we could maybe improve the model. So we'll go through each of these steps, and in this first example, you'll see how these steps work, and we'll go through it one step at a time. And in the beginning, it may seem a bit slow, and it may not seem obvious why we're doing all this analysis, but as you go through more examples, it'll become a little bit more clear. To learn a little bit more about this problem, let's explore the data set and the notebook that we're going to use for this example. And to do that, I'm going to go to Google Colab as usual, and the way I'll do it is I'll open up a Google browser. I'll open up a web browser. Just go to Google and search for Google Colab, and that's probably the fastest way to get there. There is a link we can use, but it's one of the easiest ways to get there. And this is the first link right here, Google Colab, colab.research.google.com. And as you know, Google Colab has a very convenient runtime environment in the cloud where it hosts notebooks and you can experiment without having to install any software. So if you're presented with this dialog, what you want to do is go and click on GitHub, because the example we're going to use is in GitHub. If this doesn't appear, let's say, for example, if it appears this way, we just need to go and say Open Notebook, File, Open Notebook, and again, select GitHub and provide the URL. And I'm going to type in my GitHub repository. This is the one we're going to use for our examples. And this is the name of it. I'm going to give you the link in the resources section so you don't have to remember what that is or type it in. You can just click on the link. So what we were looking for is under regression, and we're looking for iris classification. That's the notebook that we're looking for. irisclassification.ipynb. So here's the notebook. And it gives us a little bit of description of how this works. And it uses this iris data set, and it comes from the scikit-learn library. We're not going to use the scikit-learn library here. We're just going to use it as a way to get the data. The data is widely available in many different places, but scikit-learn has a very convenient method to load the data, so we don't have to go through the details of loading the data. And this data set contains 50 samples from each of 3 species of iris. And there are 4 features that are measured from each of the samples: the length and width of the sepals and the petals in centimeters. And these are the 4 features we're going to use to train our machine learning model. We could obviously make a much more sophisticated model if we had images of different iris. That's another way to do it. But here we're going to work on something very simple because, as mentioned, the goal here is to learn more about machine learning and how to build a model, not to build the best, most sophisticated model out there. So let me go over here and let me clear all the output before I get started. And the first thing I'll do is I will import a few libraries, and we get this warning that this notebook was not authored by Google, and we can safely ignore that. This is not a dangerous notebook in any way. So we're going to use really just this scikit-learn. We're going to use just the data sets from scikit-learn. And we'll also use matplotlib just so we can plot out some data. And we'll also import the Python math library. We just need some very basic math in that library, nothing complicated. So we'll use the scikit-learn method load iris, and it loads the data set. It's very quick. It's a relatively small data set. And scikit-learn is very convenient in this way. All their data sets have a nice description, so we're assigning it to a variable called iris. And if we print out iris.descr, or the description, it gives us a very nice description of what's in that data set. It says there are 150 instances or 150 examples of 50 of 3 classes, 3 different types of iris, and there are 50 of each. And there are 4 numeric attributes and a predictive attribute for the class. So the attributes are the sepal width and length in centimeters. And the class, there are 3 classes, iris, setosa, versicolor, and virginica. And those are represented just by numbers, 0, 1, and 2. All right? And the distribution, there's 33% of each, or 1/3 of each, and it was created by R.A. Fisher, and it was donated in 1988, but I think the original data set is quite old. So if you read more about it, I think the original paper that R.A. Fisher wrote about it was in 1936. And he used a statistical technique that they didn't call it machine learning in those days. He used a statistical technique to develop a model using this data to classify iris. So we're going to do something very similar, but we're going to use more of a machine learning approach to the problem. So the iris dataset also has what's called the target names. So remember there are 3 different categories, and it has the names of each of those categories in addition to the indicator variable, which has the numbers 0, 1, and 2. So 0 would represent setosa, 1 would represent versicolor, and virginica would represent 2. If we look at the length of the data, the raw data, as mentioned, there are 150 samples in there. And if we were to look at just the first 5 samples, we could look at all 150, but that's a lot to look at. If we just look at the first 5 by just taking a slice or a subset of the data, this is what it looks like. It's a 2-dimensional array, and it has 4 values for each sample, and the sepal width and length for each sample. Right? There's 4 of them. And there's also a target variable, or the label describing each of these samples. So the first sample we see right here, this is the sepal width and length of the first sample. That first sample has a label of 0, and that label 0 corresponds to iris setosa. And the way this data is organized, the first 50 samples are setosa, the next 50 samples are versicolor, and the last 50 are virginica, like that. So these are the targets, or the labels, for what each of these samples are, and these correspond 1 to 1. So the first 5 that we see here, these are the first 5 samples, and they are all setosa. If we were to look towards the end, we would see examples that are virginica, and so on. And you can explore those in detail, and I encourage you to do that just to get a better understanding of the data. And that's a good practice in general. Whenever you're working with any new data set and you're developing a machine learning model, the first thing you want to do is explore the data and understand it and understand how it's structured. So what we're going to do here is make some basic plots of this data. And the way that I'm going to do it is take the data, or just the sepal width and length, right? The sepal width and length, which are the first 2 right here. The first 2, these are the sepal width and length. I'm going to plot those as x and y. So this means take all of the samples and just the first 2 columns of each sample. All right? And then we'll also plot the target, or which one of the types of iris it is, as a different color. All right? And we'll talk more about Matplotlib in future examples. But here we're going to create a scatter plot of the x values of the sepal width and the sepal length, right? The sepal width and the sepal length as x and y, actually, even though they're both called x. And we're going to use the target label as the color. And we'll display some labels here. So you see that they cluster in different ways, and there are some overlaps. So it's not very clear which one is which. In some cases, you could get in a sample here that could fall into one of 2 categories just based on the sepal length and width. We can do something similar for the petal width and length. All right. The only difference between this, the way we selected it here, if you look very carefully, we're selecting the first two values of each sample. So this means select all samples and the first two values of each sample, the first two numbers. And here we're doing slightly different. We're taking all samples, all 150 samples, and we're going to start from 2 to the end. So it's going to take the last two of each, and plot those out in X and Y. And you notice the distribution is a little bit different, right, for the petal width and length. So even though there isn't a lot of data here, it's got enough complexity that it's not obvious how to describe each of the different samples. So that's where we're going to develop a machine learning model, just given these 4 features, to classify them into one of 3 categories. Now that we've explored the data, let's look at the model and how we would develop a model to classify these different types of iris. So what we see here is a diagram of the logistic regression model that we're going to use. And the way it works is actually pretty simple. On the left here, we have the input, and here I'm showing just one sample. So these would represent the 4 features for each sample of iris that we're looking at. So this would be the sepal width, the sepal length, petal width, and petal length. And I've just chosen some values maybe from the first sample. And so what we would do in this model is take each of these values, each of these lengths and widths in centimeters, and multiply it by a weight factor. Each of these would be multiplied by a weight factor. And initially, we don't know the values of these weight factors. We're going to learn those weight factors during the process of training. So initially, we'll assign these weights to 0 or some random numbers, and then we will train the model, and once trained, it'll have the correct weights to make a prediction. So each of these values would come in, be multiplied by these weights. We would add up all those values together, and we would also add one more value, a bias, which is also another value that's learned. And that'll give us a number. And that number, or score, is an indication of whether the sample we have is either an iris that we're looking for or another type of iris. Now, we'll do one more thing. After we compute this value, this product and sum of all these inputs and the weights, and adding the bias, we'll pass that through a nonlinear function. And this is a common operation that you'll see in machine learning, and specifically in the case of neural networks. Here we're using a nonlinear function. This linear function is what's called the sigmoid function, or the logistic sigmoid, and it has this funny S shape like this. And the reason we use that is that for larger values, for very large values, because this value could produce a number that's very small or very large, we want to turn that into a value that's either close to 0 or close to 1. 1 meaning it is the category we believe it is, and 0 meaning it's not the category. So that's really the purpose of this nonlinear function, is to convert a value that ranges from could range through a large number to just the values 0 and 1 in a smooth way. And that'll represent our output. And from here, we can take so this ranges from 0 to 1, so anything that's above 0.5 we would say is a match. It is the category we're looking for, and anything below that would be not a match. So this is the basic idea of logistic regression, and it turns out that model is very similar to what is used in neural networks. And in fact, in the early days in 1958, there was an image recognition machine that was developed using what's called a perceptron. And this is actually a model of a perceptron, a single layer perceptron, similar to a neuron in a human brain, conceptually similar. And there was a machine that was developed with 400 perceptrons at Cornell Aeronautical Lab that was used for image recognition. And it showed some initial promise and sort of led the way to some of the ideas of modern machine learning, specifically deep learning. The original initial design didn't work very well. It had limited capability, but it did pave the way for more sophisticated multi-layer perceptrons, which are much more powerful, and they are widely used today in deep learning models. So what we're looking at, even though it's logistic regression, it's very similar to a perceptron or what's used in a neural network. And that's the way we're going to train this model. Now that we have the structure of the model worked out, let's implement that in code. And what we're going to do is develop this model, and we're going to first work on the forward pass, or the predict function. That's going to predict, assuming that we have the weights and biases. Let's assume that we've already got those values. Given any sample, we want to make a prediction. And then we're going to write the part that determines the weights and biases, or the training part. All right? So first we're going to do is create what's called the sigmoid function. And the sigmoid function is defined right over here. There's a link to it right there. And if I right-click on it and open a new tab, I can see the definition of sigmoid function. It explains it in more detail. It's a mathematical function. It has this S-shaped curve, or what's called the sigmoid function, or the logistic sigmoid function. It's actually, if you go to this other link, it'll tell. They also call it the logistic curve or the logistic function. Same thing. And it has this definition. It looks like this. For any given value x, input value x, the output value is 1 over 1 plus e to the minus x. Or you could rewrite it as e to the x over e to the x plus 1. So what's interesting about it is for very small negative values, very small values, or the output of this function becomes very close to 0, and for very large values, the output is very close to 1, which is what we want if we want to do binary classification. So in this case, 1 would mean true, or it does match the class we're interested in, and 0 means false, or it doesn't match the class we're interested in. All right? So to define that sigmoid function, very simple. We'll supply an argument called z. That'll be the input value, and the result is going to be 1 over 1 plus the value of e, the Euler constant, math.e, and that's where we use that math library from the Python library that we imported earlier. And then we raise that to the power of e to the minus z. And what I have here is a little bit of code just to test that function and to plot it out to make sure it produces the right value. And the way I'm going to do that is I'm going to choose a number of x values, and what I'm going to use is a little bit of a trick, a little Python trick here. I'm going to loop through a range between minus 50 and plus 51. Minus 50 and plus 51. That's going to be the value of I. And then I'm going to take that value I and multiply it by 0.1. So that means that the entire expression is going to range from minus 0.5 or minus 5 to plus 5. Minus 5 to plus 5, because we're multiplying 50 and 51 times 0.1. So that'll give me a list with values within that range. And then I'm going to create another list which evaluates the sigmoid function for every value x. So the x ranges from minus 5 to plus 5, incrementing at 0.1, and this is going to evaluate the sigmoid of each of those. And then I'm going to use matplotlib to plot those out. So if I run that cell, it defines that function and it plots out the sigmoid function very nicely. All right, and as you can see, it looks very similar to the function we see here. It has the same shape. Values that are very small asymptotically approach 0. Values that are very large asymptotically approach 1. So that's exactly what we want. All right. So now this box is finished. We want to work on this prediction function, or this prediction, or put it all together so that we can do this multiplication times the weights, add the bias, and then also pass it through the sigmoid function. All right. And this is what the predict function is going to do. So the prediction function is going to take a single sample, and a sample has 4 values, sepal length, width, and petal length, width, as an array or as a list. And we're going to multiply that times the weight and add that all up. So the way we'll do that is we'll have a result variable. We'll start initialize that with 0 and loop through all of the values in each sample. For one sample, there are 4 values. I could have written this out going through each of them individually, 0, 1, 2, 3, 4, because there aren't so many. But, this is a convenient way to do it, just in a loop. So I'll loop through each of the samples, and I'll add to the result each of the weights times each of the sample values. Each of the weight values times each of the sample values. And later I'll define this weights and initialize it to 0 or some random values. All right. And then we will also add the bias. And once we're done, we're going to return the sigmoid of the result. We're going to apply the sigmoid function. So this predict function performs all of this right here. Everything you see here is in this predict function. So it's quite simple. It's quite simple. So we have the forward prediction. So if we had the right values of weights and bias, then we could make a prediction for any values that might come in and classify any iris that we might find. Now that we've defined the predict function, we need to define a way to measure how well our model is doing compared to the expected output or the ground truth. And we do that with what's called a loss function and cost function. And it's effectively just taking the difference between the predicted value the model is producing and the expected value, which is our training sample. There are a number of ways to do that. We could just take the difference and use the absolute value. We could use mean squared error. In general, those do work, but in this particular case for linear regression, since we're using this sigmoid output, this more complex function is more effective. It looks complicated, but it's actually quite simple. What we do is we have the y value, which is the expected training value, and y hat is the predicted value from the model. And if you were to plug in values that are close together, let's say 1 and 1 for both y and y hat, you would see that the loss function would actually have a low value. So let's just take that example. If both y and y hat were 1, this value would tend to 0, and this value would tend to 0. So then that's close to 0, which is what we want. Similarly, if the value was 0, if y and y hat were both 0, meaning they were close together, the loss function would also be 0 because this one would tend to 0. So we can actually experiment with this with this little bit of code that I have right here. So this code right here defines the loss function, and all I did was just code what this equation is in Python, like you see right here. And what I have down here is a little bit of code to look at that curve and see how it behaves for different values of predicted value, or y hat, predicted value from the model. So I can choose a value for y train, let's say 0.1, and we can see what the loss function looks like for different values of y hat. And as you can see, if y train is close to 0, the loss is actually very low, which is what we want, meaning that it's close to the expected value. And if it's different from that, the loss is high. So that would tell us that the model is far away from the expected value, and we need to adjust the weights and biases accordingly. Similarly, if the expected value is close to 1, when the predicted value is also close to 1, then the loss is very low. And any value other than that, the loss is very high. So in both cases, what we're trying to do is reduce this loss and get to the bottom of this curve that's the loss curve. And in the next section, we're going to see how we do that. We're going to use something called gradient descent to do that. Now, that defines the loss function for one sample. If we were to average all of the losses for all samples, that will give us what's called the cost function. And I've defined that right here. And all that means is that we just add up all the losses for all samples that we feed into the model and all the expected values, and then divide by the number of samples m. So that'll give us what's called the cost function, which is the average loss. And we're going to use that to understand how well our model is doing overall beyond just one sample. Now that we've defined the loss and cost functions that measure how well our model is doing compared to the training data, we need to find a way to adjust the weights and biases in the right direction so that it reduces the overall cost. And we have to do this iteratively. There isn't a closed form solution to this problem, so we have to iterate multiple times. So if we look at these two equations here, this describes how we make those iterations. And what we have here are wk plus 1, which is the next value of the weights after an iteration. Bk plus 1 is the next value of the weights after an iteration. Wk and bk represent the current value of the weights and biases in the current iteration. So we're going to compute the next value by taking the current value and subtracting this term right here. And this term has a couple of factors. The first factor is called alpha, which is the learning rate. And the learning rate is a number. It's a hyperparameter. It's a tuning parameter that we'll use to adjust how quickly our model changes. And that number is determined empirically, and we'll look at how we do that in a second. The next term is the gradient, or the slope, of the cost function with respect to the weights. The slope, or the gradient, of the cost function with respect to the weights. And if you had a little bit of calculus, you've seen this term before. And what that is the partial derivative, or the first derivative of the cost function. If you haven't had any calculus and you're not familiar with that, it's okay. We'll look at this intuitively so you understand how it really works. So we do the same thing for the bias. We subtract from the current value of the bias the learning rate times the derivative, or the partial derivative, of the cost function with respect to the bias. And so each of these two terms are called the gradients, all right, or the slope. You can imagine it's kind of like going downhill in that curve of the loss function that we saw earlier. All right, to explain this a little bit further and to give you some idea of how this works, let's look at a simple example that's not really related to machine learning, but it just shows you how gradients and derivatives and what this gradient descent and how it works. So what I've defined here is a simple parabola. It's y equals x squared plus x over 2. And right here I have a little bit of code that describes that parabola. I've defined a function, x squared plus x over 2, and I have a little bit of matplotlib code to plot that function. So if I plot it, this is what the curve looks like. So you can imagine if we wanted to find the minimum of this curve and we started at some point over here, we'd want to go downhill. And how do we go downhill? Well, we go downhill by looking at the slope of where we are at any point on this curve. So if we were over here, the slope is positive, so we'd want to subtract and go down this direction. If we were over here, the slope is negative, and we want to subtract negative, which would mean we'd want to add a little bit. So let's look at how we would use gradient descent to solve this problem. And we can see the minimum is somewhere around minus 0.25. So the first thing we need to do is define the derivative, or the partial derivative, of that function. And if you've had calculus, you would know that the derivative of x squared plus x over 2 is 2x plus 0.5. If you're not familiar with calculus and you're not familiar with how to calculate derivatives, it's not super important right here. This is just, it's important to know that this is how we calculate the derivative for that equation that we saw above. Now, to find the minimum, we would use the same iteration that we saw before. We take the current value of x and subtract this term, which is the learning rate times the derivative, or the gradient, at that point. And we would continue iterating this equation until it converges to some reasonable value. So I have some code down here that does exactly that. We're going to start with xk equals 0. That's our initial value. We're going to choose an initial learning rate of 0.1. I've defined the derivative function, which is this same function right up here, 2x plus 0.5. And here's my iteration, where through every iteration I'm computing the gradient, which is the derivative xk. Derivative xk calls that function. And I'm going to subtract from xk the learning rate times this gradient, or the derivative, right? And I'm going to iterate. And here I'm going to just iterate 5 times just to see how it does. And then I'm going to print out what the estimated minimum is and the derivative at that point where we got to the minimum. And I have some matplotlib code to plot out the function and the point where xk is, and also the slope. So let's run that and see what we get. So it looks like we got close to the minimum, but not exactly. We started here at 0, and we got part of the way. We're not exactly there. And if you look at the slope, it's still positive, meaning that we've got a little bit more to do, a little bit more to go. So what we could do is we could adjust one of the hyperparameters. In this case, let me just increase the number of iterations to 10. And let's see what happens. All right, it's a little bit better. We're almost there. The gradient is 0.07, so it got smaller, so we're almost at the absolute minimum, but we're not exactly there. So let me go to even a higher number, 100 iterations or 100 epochs. And there it looks like we did get to the minimum. And you notice the gradient is 0, so there's nowhere to go from there. There will be no more adjustment made to this xk because the gradient is 0. Even if we iterate any more, it's not going to change xk. So that took 100 iterations or 100 epochs to get there. So we could get there a little bit faster if we used a larger value of the learning rate. Now let's adjust the learning rate and see how it affects gradient descent. So let me increase the learning rate to 0.5. And that definitely gets us to the minimum. So if an increased learning rate gets us to the minimum, and then what I could do is I could try and reduce the number of epochs. And you see that gets us to the minimum with fewer iterations. So that means that a higher learning rate is better. So then let me try an even bigger learning rate. Let me try 1.5 and see what happens. Well, it looks like we completely overshot the minimum. We're way over here at 250. So 1.5 is way too large for learning rate. So what that means is we want the right learning rate. So a higher learning rate is better up to a point. And beyond a certain point, we're just going to completely overshoot the minimum, and the gradient descent's not going to work at all. So let me go back to a reasonable number. I think I had 0.5. And we're at the minimum. And then I can just reduce the number of iterations, and let me go just to 5 iterations. And there we get to the minimum again. So it seems like some of the best values, or some better values, for learning rate and iteration are 0.5 and 5 respectively. So you can see that these parameters or these hyperparameters we determine those empirically. And later we'll look at some other ways that we can determine those automatically. But these are kinds of parameters that we may want to tune while training our model. So a low learning rate means that it'll take longer for our model to converge, but too high of a learning rate means we'll completely overshoot and we won't get to a minimum cost. Next, we'll implement backpropagation, which is going to apply this gradient descent algorithm to adjust all of the weights and all of the biases in the right direction to improve the quality of the model. All right, so we're almost there. We've defined the loss function, we've defined our gradient descent, so we understand how gradient descent works. We're going to put all that together and use what's called backpropagation. And backpropagation is the algorithm that's used in neural networks, deep neural networks, and even in this logistic regression algorithm. So we're going to do something very similar that we did in our previous simple example with a parabola. We'll just expand it to all the weights and biases and also compute the average cost. So what I've done here is defined a function called train one epoch. So this is like one iteration where we're going to update the weights and biases for one set of training data. And we'll do this over and over in another function. We need this value of num features, which is just really the number 4. It's number of, because we know we have sepal width and length and petal width and length. That's just a number 4. And I could have hard-coded it, but I just chose to get it from the size of the data for generality. So to train one epoch, I have the X train samples, which are all the widths and lengths of the sepals and petals, and then the Y train samples, which are the indicators that tell us which of the three iris that we have. And this is just going to be a value of 0 to 1. We're going to choose 1 for each of the different iris types. So I'll initialize the overall cost to 0, and I will create a variable called dw. This is going to be the change in the weights. And this is another Python trick. I'm going to create a list, which the initial value of 0 and times num features means that I want a list of 4 features. I want 4 values in this list, and they're all going to be the value 0. We'll initialize it to 0. and this is the change in the bias. We're going to set that to 0 as well. And then we have a global variable for the weights and biases because the actual weights and biases are not going to be defined in this function. They're going to be global variables that we'll define elsewhere. M is the number of training samples that we have. It was 150 in our case. And we're going to loop through all of the training samples. We're going to get each of the features, the X sample and also the Y sample, which is the predicted value. And we're going to make a prediction. This is going to call our predict function that we defined earlier, given one sample, and it's going to make an estimate, a guess. So the initial value, it's going to be a total guess because we have zeros for all weights and biases. It's a complete guess. Then we're going to compute the cost. We're going to add up the cost by computing the loss for whatever we predicted, and the known value or the ground truth is the known, or is the ground truth or the training value. We know what the value should be, and this is what we predicted. Maybe close, maybe completely wrong. All right. Then we're going to compute a derivative, and this is a little more involved. When we compute the derivative and all the other derivatives that we need to compute all the weights and biases, is a little more involved than the simple example we saw earlier. But for this loss function, this is what the derivative happens to be. So then we've got 4 weights we've got to update. So we're going to loop through all of the weights, there are 4 of them, and update the values for all the weights using this dz variable, right? And we're going to do the same thing for db. So that goes through all of the samples and computes the change that we need to make for the weights and the biases. So we're not yet ready to update the weights and biases because we've got to average them out. So first we average out the cost by dividing by m, the number of samples. Then we also average out the bias by dividing by m. And then we can subtract from the bias learning rate times the change in the bias. Right? Very similar to what we saw earlier. We got to do the same thing for the weights, but since we have 4 weights, we've got to do it 4 times. We've got to loop through all of the weights and do the same thing. We're going to subtract from the current weight value divided by m, which is the average, the number of samples, and then subtract from the weights. Remember, we're going to multiply that by the learning rate, and that'll compute the updated weights and biases for one epoch, one iteration going through all the training data. And then finally, we'll return the cost so we can plot that out and see how well our model is doing. So now that we have that function, let me run that, we're ready to do some training. So we've defined our loss function, our backpropagation algorithm. I'm going to go ahead and run these 2 cells so those functions are now defined. They don't produce any output here because we're just defining functions. All right. And now we come to the training algorithm itself. So what this algorithm is going to do is iterate through the training data many, many times and call the backpropagation functions to update the weights and biases until they're correct values. And then once it's done, we're going to plot the loss. We'll keep track of the loss, or how close the model is getting to the expected predicted value, and we'll plot that, and hopefully it's getting close to what we expect. What we're going to do is define the weights and the bias. The weights is an array of 4 values because we have 4 features, one for each of the input values, the sepal width and length and petal width and length. And we have 1 bias value. And we'll initialize those to 0. And we're also going to define the learning rate. And learning rate is a hyperparameter that we can adjust. It's a value that controls how quickly the model converges on the solution. Now, if we make this value too small, it's going to take a long time to converge. And we just don't want to wait a long time. There's nothing wrong with that. It just could take a long time. Now, if we make the value too large, the model could just run past the optimum value completely, and it could just oscillate back and forth and never get to the optimum value. So we want to adjust that learning rate, and that's an experimental process or an empirical process. And as you will learn, a lot of machine learning is an empirical process. There are many factors or parameters or hyperparameters that we will adjust to get the best results from our model. Another hyperparameter is the number of epochs, the number of times we iterate through the data. So more is generally better. Of course, at some point it's going to hit an asymptotic value and it's just not going to get any better. And there are also possibilities of what is called overfitting, which we'll talk about in a later lecture. So this number is something I arrived at experimentally. These are all values you want to experiment with when you are working through this example. Experiment with the learning rate, experiment with the epochs, and see if you can improve the model. We're going to just run it through it here and see what it looks like. All right. So let's collect our training samples. This is just the iris data. And the Y-train samples are the expected value, which is just going to be 1 or 0. And I'm going to use a little bit of a trick here. So what I'm going to do is I'm going to set the value to 1 if the target value is 0. Meaning, remember, our target values in our training data set were either 0, 1, or 2. 0 meaning which iris it was. 0 would be iris setosa, 1 and 2 were the other 2 iris types. So this particular model, the way I have it set up here, this is going to predict if the samples we have are iris setosa. So 0 here means iris setosa. Okay? We can adjust that value for the other 2 types. So we'll go through it just one time just to predict. So this right now is going to just determine if the input is an iris setosa or not. All right. And I'm also going to keep track of the losses as we go through each epoch and train it. And this is a nice thing to do because in theory, if it's working properly, the loss should go down, meaning the model is getting better and better and predicting closer and closer to the correct value. So I'm going to iterate for the number of epochs. I'm going to train one epoch given the training samples and save that value or append it to this loss array. And at the end, I'm going to plot for each epoch the loss array or the loss over the number of epochs. So let's go ahead and run that and see what we get. It's going to take a couple of seconds because it has to do some iteration. It doesn't take a long time because we have a pretty small data set. And if you look at this loss, it looks pretty good. It starts out fairly high, which we expect. The prediction was totally wrong. And, almost 1, meaning it was completely wrong. It wasn't completely wrong, but it was close to wrong, almost completely. And then it quickly falls, and then it gets really quite accurate, and it reached an asymptotic value. So it looks like we may be doing quite well with this. We may be doing quite well. All right. But before we get too excited, let's try a couple of others. Let's try it with the other type of iris, the second type of iris. All right. And let's train it again and see what we get. Takes a couple seconds. So now this one doesn't train. It does seem to get better, but doesn't train nearly as well. So it looks like that second one is probably a little bit harder to predict than the first one. That's what that suggests. So let's try the last one. Okay, it's going to take a couple seconds. Not too bad. It's maybe in between, and you see the loss is a little bit better than the second one, but not as good as the first one. All right, and it is sort of reaching an asymptotic value. So we could go further with it and try and increase the number of epochs, and that's something you can experiment with on your own and see how well you can do and see if you can do a better job. So now we're able to train the model, and we see that it is training and it is predicting generally going in the right direction. It is getting better, not perfect. In the next step, we'll make a prediction and actually look at the output value that it's producing and compare it to the actual value and see if it's correct. Now that we went through all of the model training, it's time to make some predictions. And what I'm going to do is, before we go through that, this is the moment we've all been waiting for. Let me go and set this back to 0 because we want to predict iris setosa. So I'll retrain it again just for iris setosa. All right, and we know that one had a very low loss. In theory, it does really well. And notice the initial loss, when it starts up, it's almost 75%, which is what you would expect, because if there are 3 classes, it's probably randomly 1/3 right. Maybe it's a little bit better than 1/3 right, so it's probably doing the right thing. So let's go ahead and make a prediction. All right, and what this prediction is going to do is go through all of the training samples and make a prediction for each sample, and then save the prediction value. And if the value is greater than 0.5, remember the output we're getting from our model is a continuous value between 0 and 1. So if we're going to say if the value is greater than 0.5, that means that it's a positive match, meaning that it predicted what we expect. It is the iris that we're looking for. Otherwise, we're going to set the value to 0. All right? And if the value that we predict equals the training sample, meaning the known value, or what often called the ground truth, then we'll say we'll add 1 to this variable called correct. And we'll add up how many values are correct and compare that to how many are incorrect. And then that'll give us our accuracy. So let's go ahead and run it. All right. And also what I did is I'm plotting out the Y-trained samples of what it should be. So here's the ground truth in orange, and that's the first 30 samples, or the first 50 samples, or 30%, 1/3 of the data. So this is what we expect to see, and the other two are the other iris types. So we don't it should predict incorrectly. And you see it does really well on that first iris. It predicts extremely well, and in fact it's 100% accurate for every sample. Every type of iris, it predicts correctly. There are a couple that, it has a few doubts, but it's, for the most part, it's doing really, really well. So now let's move on to the next iris and see how well it predicts for that one. So this is iris 1. Iris 1. And note, remember, this is the one where the loss was not as good. It was not very good at all. So let's go ahead and run the prediction for that one and see what we get. I'll go ahead and run the prediction. Notice prediction is much faster than training because it only has to go through the data once. It doesn't have to iterate and doesn't have to go through back propagation. So you look at it, the output is quite ugly. So this is what we expect in the orange. So because the middle 50 are the ones we're looking for. And if we go through, even though it doesn't look correct at all, well, it's sort of reasonably correct in the first 50, the last 50, not so, maybe. Hard to tell. So really, we got to look at the math and look at the values for how many were correct and how many were wrong. And it's not terrible. It's 74% accurate. Not the greatest model out there, but okay. Well, what do you expect for a really simple model? It's okay. It's better than 33%, which would be random, right? So let's try the last one. So this is the last iris type. Make the prediction, or I'm sorry, go through the training. And remember, the loss is lower than the second one, but not as low as the first one. So then let's go ahead and make our prediction and see what we get. Not too bad. Not too bad. Notice it's got some doubts in the middle, right? It seems to be incorrect. This value, this case, it's clearly incorrect because it should have been 0 here, and it's well above 0.5. So that one's definitely incorrect, and these may be incorrect here. But if you look at the accuracy, it says 98%. So it didn't get too many of them wrong, even though it has a few doubts here and there. It didn't get completely wrong. So another interesting result from this is beyond whether the binary value, whether we predicted the iris or not. The actual value, the predicted value as a number, gives you a bit of a confidence factor of how well it predicted. You see over here, the confidence is very high, right? The confidence is extremely high. So when the predicted value is exactly 0 or very close to 0 or very close to 1, that means the model is extremely confident. When it's closer to 50%, it has some doubts, so it's not as confident. So that's another piece of information that we can use from our machine learning models. Beyond whether it just got the value right or wrong, we can also look at those values in terms of confidence and determine how confident the model is. And if something it's not super confident about a model, then what we could do to improve the model, one of the many ways we do it, is look at these samples. Try and understand what's special about these samples. Maybe these samples are very close to others. Maybe they're misclassified. It's possible that somebody who looked at all these irises and classified them and gave us the ground truth, they may have made a mistake. That's not uncommon in a machine learning model, is that you can't assume your data is 100% accurate. It may not be. Or the other factor is that these samples look very close to others, in which case what we may need is more data. That's another way we could improve the model, is just give it more data. Now, in this particular case, this is not a particularly sophisticated model, so that may not help a lot. But if we had a more sophisticated model, more data may help it. So let's look at a couple other things. What was actually learned? What was the output of this model? Well, remember the weights and biases. So if I look at the weights here, you see there are 4 numbers, and that's really the knowledge. What this, in addition, let me plot one more, is the bias. Right. At the end, this is what the model has learned. So if I want to use this model in production, what I would do is I would train the model. I would save these weights and biases. Not a lot of data, small amount of data. We would save that, maybe put it in a file. We could read that back later, and that's the knowledge the model has learned. So the way we've set up this model, it only predicts 1 of 3 irises at a time. You can see how we could extend it. We could create 3 different models, train 3 different ones, 1 for each iris, and have different outputs. So there are several number of different ways we could use it. So even using a simple technique, this simple logistic regression technique, which we've actually presented as a machine learning model, there's a lot we can do with it, and a lot we can learn from it. And I encourage you to experiment further with all of this. That's really the best way to learn. You really have to experiment and get your hands dirty with all of this. And that's why I tried to provide a simple example. You see all the code here is not very complicated. There are no special libraries used. It uses just basic Python. There is a little bit of math here. And as mentioned, if you want to know more about that, exactly how this was calculated, how the differences for the weights and biases are calculated, just let me know and I'll answer any questions you might have. If you have some experience with machine learning already, you probably noticed that we cheated a little bit in this example. One thing we didn't do was we didn't separate the data set into a test and train data set. And that's a common technique. And what that means is to set aside some of the data for training and some of the data for testing. A small subset of the data is usually set aside for testing. And that's okay. In this example, we were just learning. It wasn't really, the purpose wasn't to come up with the best model or to make the most general model possible. The purpose here was to learn some of the basic ideas of logistic regression, gradient descent, backpropagation, and so on, and how models are trained and so on. That's what we were really after. Anyway, we didn't have a lot of data here, so splitting it into a test and train data set probably wouldn't work very well. Of course, if we had much more data, if we had thousands and thousands of examples or even millions of examples in some cases, we could separate the data into a train data set and a test data set. And that's a very common approach that's used today. And the reason we would do that is we want to train the model and test it on data that's independent of what it has been trained on. So you can imagine if we trained a specific model and we tested on the same data that it was trained on, the model might just memorize the data that it has seen, and it may not generalize at all. So if you look at this graph on the right, what it's plotting is the accuracy of the model on the test data and the training data. And notice that those graphs are very different. And that difference between the accuracy it has on the training data versus the testing data is what's known as variance. And an ideal model, a model that is well trained and generalizes well, will have no variance, meaning it will produce the same accuracy no matter if it has been tested on the training data set or if it's tested on the test data set that it has never seen before. There's also something known as the bias, and that's the ultimate accuracy independent of test or train. So we'll learn more about that in future lectures and how we split the data into test and train. Typically, we'll use something like an 80-20 or a 90-10 split, meaning that the majority of the data, either 80 or 90%, will be used for training, and a small percentage, say 10 or 20%, will be used for testing. So getting back to our case where we didn't have a lot of data, when we had a few examples, maybe 150, and we really can't split it into test or train and get an effective answer out of it or an effective accuracy out of it, what do? Well, one solution used to use what's called k-fold cross-validation. Generally, what that means is to shuffle the data or randomize the data and then split it into k different groups that are overlapping. And maybe there are about 5 or 10 groups or so. And then we would test the model on those different groups of data and see how well it does on different parts of the data. And if it does well on all the parts of the data, then we could say that the model is very accurate and that's a good model. Of course, all those techniques like k-fold validation were used in the past when we didn't have a lot of data. But today, we don't really have that problem. We have lots and lots of data available. There is data from many, many different sources. Data from social media, from the internet, from searches, from log files, from IoT devices. There's data from many, many places, and that's one of the areas, that's something that many companies tried to do, is collect data from as many places as possible. And the combination of these deep models that we have today, these sophisticated models, and the availability of large data, and the compute capability that we have with GPUs and hardware acceleration, that's what really makes modern machine learning as effective as it is today. In general, training modern machine learning models can be compute intensive. There are lots of calculations need to be done, lots of multiplies and adds, and that could take a lot of time. In our particular example, our data set was relatively small. We only had 150 samples, and the model was quite simple, so it didn't take much time, even on a desktop CPU. But you can imagine if we had much more data, we had thousands and thousands of examples, or even millions of examples, and we had a much more complex model, which is not uncommon today, it could take a very long time to train. It could take hours and hours to train, or even in some cases in the past, it might take days or months to train a machine learning model. So we need some ways to speed up this training, and there are a couple of ways to do that. One way is to improve the training algorithm. As we saw, the learning rate has a huge effect on how quickly the model will converge on a solution. And choosing that learning rate can be very challenging. We could experiment with it on our own, we could estimate it, and that can be done, and that was done in the past using the standard gradient descent. But there have been some better algorithms that have been developed. One of them is what's called the ADAM algorithm. And ADAM is based on what's called adaptive moment estimation. And what it tries to do is estimate the learning rate based on previous estimates of learning rate. And it turns out it's very effective. And modern libraries such as TensorFlow and Keras and PyTorch and others, they include an implementation of the ADAM algorithm. So we don't have to tune anything. And that's a great place to start. And we'll see examples of how ADAM works in upcoming lectures. Another way to speed up training is through accelerated hardware. And the preferred hardware of choice today for modern machine learning are graphic processing units. Graphic processing units contain thousands and thousands of floating point cores that are capable of performing multiplies and adds at high speed in parallel. And if you remember from our example, all we were doing is multiplying the weights with the input samples, adding them together, and passing it through a nonlinearity. That kind of multiply and add is a vector multiply, and that's what GPUs are very good at. And the nice thing is cloud providers offer these GPU instances at low cost. In the case of Google Colab, we could use a GPU instance for free. So that's a very effective way to do it. So combining these two techniques, using modern libraries, using modern algorithms, and also GPU acceleration in the cloud, that's what makes modern machine learning so effective today. Even though this section was about logistic regression, what we really learned about was a single layer neural network. It's the same idea. It worked, but we could expand on this and make that model better. And one way to do that is to use a deeper model that's more effective. It can learn much more complex features and solve much more sophisticated problems. And in fact, deep models that are used today, they can do some very sophisticated things. They can do image and speech recognition. They can translate language from one natural language to another. They can also understand natural language, generate text or music. They can play games that beat humans at some of the most difficult games like chess or Go or even video games. So the way these deep neural networks work is they just expand on the ideas that we just learned about. Instead of just having one layer, one input layer with a number of weights and biases that feed into a summation and then go to one nonlinear function like the sigmoid function, we could have many layers, and each of those layers would include a nonlinearity as well. And we can make very complex models like this. And typically the way these deep models work is there's an input layer that's similar to what we've seen, and there are any number of hidden layers. And the number of hidden layers is a measure of the capability of the model, and deeper models tend to be more capable. But of course, to train really deep models requires lots of data and lots of time to train and so on. So just making a model deeper doesn't necessarily make the model better. Training it is a bit of a challenge, and that's a significant skill. And that's something we're going to learn as we go along in this course. And then after these hidden layers, we can have output layers, and these output layers could make many different kinds of predictions. They could make just binary classification, just true or false, or multi-class, meaning one of several classes. Maybe it could have 10 outputs, and we'll see an example of that. Similarly, we could predict a continuous variable, let's say the price of a house or something like that. We could also generate data. We could generate another image. We could generate text, or we could generate speech. So the concept of a deep neural network is very powerful. It's very flexible. And this isn't new. People had these ideas for a very long time, but they just didn't work very well. And there were some great breakthroughs around 2012 that made them work as well as they do today. And a lot of it is very subtle. One of them has to do with that sigmoid function that we saw earlier. Historically, people thought, well, that's the function we should use in between all these layers because that's what we see in nature. But it turns out that it has some problems during backpropagation due to what's called the vanishing gradient problem. So what works better in the in-between layers is what's called a rectified linear unit. And we'll learn about that in future lectures. So of course, there are many types of deep learning models. There are dense networks, convolutional neural networks, recurrent neural networks, autoencoders, transformer models, and they all solve different kinds of problems. Some are better suited for image processing or image recognition. Some are better at speech and audio. Some are better at text. Some are better at anomaly detection, and so on. And we're going to learn more about these as we go throughout the course. And of course, this is an open area of research. This area of deep learning only started a few years ago, and it's going to continue to improve. So you can imagine there are going to be many, many breakthroughs, and it's growing at an exponential rate. There are some interesting graphs of the publications that have come out in deep learning, and it is growing at an exponential level. There are, of course, people that are going to question how far will it go? Have we hit a wall? That's always going to be there. People are always going to question how far the technology will go. And it's hard to know. We're still in the early days. So I'm certain that even with the technology that we have today, there are going to be many, many applications, and it's going to be applied in many, many places. Even if there aren't any great advances made in the future, just given the technology that we have today, there are many places it can be applied and many problems that can be solved. And that's an opportunity for you. So think about what you can do with all of the ideas that we're going to learn in this course and how you can apply it to the problems that you're working on. Let's look at one of the foundational technologies called NumPy and see how it's used in machine learning and data science. So NumPy is a powerful Python library for manipulating numerical data. It's widely used for machine learning and data science. With NumPy, you can create multidimensional arrays and perform a number of numerical operations at very high speed. It performs much better than Python by itself. It has a number of optimizations. NumPy has a number of built-in functions for linear algebra, statistical analysis, transforms, and many, many other operations, far too numerous to list here. In fact, we could have a course just on NumPy alone, just to learn all of the features of NumPy. But we're going to learn just what we need just to solve machine learning problems. It also turns out that a number of libraries depend on NumPy, such as Keras, Pandas, and Matplotlib. And we'll learn more about those libraries and how NumPy is used in each of those. We'll also look at a number of examples on how to use NumPy. Let's look at some examples on how we create data with NumPy. Later we'll see how to manipulate this data in a number of different ways. We're going to do this in Google Colab. So I can just search for it here. I'll just type Google Colab in the Google search bar and it comes up right there. That's probably the easiest way to get to it. And I'll go to my GitHub repo. I'll select that up here and I'll type in my repository name there and click search. I'll put a link to the repository in the resources section so you can get to it easily. It comes up with the machine learning repo. That's the one we want. And let me scroll down and look for, here it is, the NumPy notebook. So let's open that up. Here it is. And what I'm going to do is first, let me clear all the outputs so we can go through it step by step. All right. So as mentioned, NumPy is a powerful Python library for creating and manipulating multidimensional arrays. It has functions for linear algebra, statistical analysis, and many, many others. So the first thing we need to do is we need to import NumPy, and it's customary to import it as NumPy as NP. NP is a very common prefix that we use for NumPy. And of course, Google Colab says this notebook was not authorized by Google. It's okay, it's not doing any harm, so we're going to run it anyway. All right. So first thing we're going to do is create a NumPy array using np.zeros. This is probably the easiest way to create a NumPy array. And here I'm going to specify the number of zeros, which is 5. And then I'm going to display that. So let me run that cell. And as you see, it creates a NumPy array that just contains 5 values, and they're all 0. Very simple, not very complicated. There's a similar one that creates an array of all ones. There's another one that allows you to fill an array with a set of values. Here's one that creates a set of random values ranging from 0 to 1, and here I want 5 values, and you notice that they're randomly created. There are also methods for initializing the random seed if you want deterministic behavior. I can also create an array from a Python list. So inside of this array function, I'm including a Python list here, and this is effective because NumPy arrays are much more. They perform much better than Python lists by themselves. All right. I can also create arrays using shapes more than just a single dimension. So here I can create a 2 by 2 set of zeros, and it looks like a matrix like this, a 2-dimensional matrix. I can do something similar with the random function, random.random, using creating a 2 by 2 matrix, and you see it creates 4 random values as a 2 by 2 matrix. I can also create a NumPy array using two lists, a 2-dimensional array. So this is a matrix, a 2-dimensional matrix, right? So as mentioned, there are a number of other ways to create NumPy arrays, and we'll see some more examples. If we go to the documentation for NumPy, it shows several array creation routines. We can create an identity matrix if we want, or an identity. The ones, we've seen that. Zeros we've seen, or we can fill a set of values given a certain shape, or from other existing data. Many, many different ways that we can do it. We'll look at this other one, a range, which gives us a range of values, and so on. So this is a good place to refer to if you want to learn how to create NumPy arrays. And of course, there's a bunch of examples for each of these. So if I click on any one of these, it will give me a description of how to create the array, the possible arguments, and it provides a number of examples. So it's very easy to use. Now that we've learned how to create arrays in NumPy, let's look at some basic operations. So I have my same notebook open, and I'm going to create a one-dimensional array here filled with ones like this, and we've seen that before. So it creates 5 ones like that. It's a NumPy array. And I can do a number of basic operations like multiply all the values by 2. So if I multiply by a number, it'll multiply all those values. I could obviously add values as well. So if I add a constant, this does what's called a broadcast. It will add or perform an operation on every value in that array. Right? If I had a 2-dimensional array, it would do the same thing, or a multi-dimensional array, it would work in a similar fashion. So let me create another array here. In fact, let me create another array here. All right, and this is just going to contain a list from 1 through 5. Right, array named B. Then I'm going to add A and B. So notice A was with values 1, 1, 1, 1, 1. And B had values 1, 2, 3, 4, 5. And if I add the two, we get what we would expect. It adds each of those element-wise. So 1 plus 1 is 2, 1 plus 2 is 3, and so on. So I can also take a slice of an array. This works just like a Python list. So if it's one-dimensional and I start with index 1 and goes up to, but not including index 4, I get 2, 3, and 4. So the length is 4 minus 1. I can do something similar with multi-dimensional arrays. I can do some other operations. So here's a 2-dimensional array that's a 3 by 3 matrix. It has an array within arrays like that. So if I create that, you see I have a 2-dimensional matrix which is of shape 3 by 3. I can reverse the columns using this interesting syntax. This means to start and stop, and then I want to increment by -1. So this will reverse the columns. So you notice now instead of 1, 4, 5 on the left, I have 3, 6, 9, which was on the far right. Notice the middle is unchanged, and you notice 1, 4, 7 is on the right as the furthest column to the right. I can do something similar by reversing the rows. This is the syntax for reversing the rows. So notice 1, 2, 3 was at the top here, and now 1, 2, 3 is at the bottom. Similarly, 7, 8, 9 is at the top where it was originally at the bottom. I can also select a certain set of rows and columns using multiple indices. So what this means is select the rows from 1 to 3 and the columns from 1 to 3. So this should give us a 2 by 2 matrix, which it does, starting from 1, index 1, and going to index 3, the number that's the starting row, and then the starting columns is index 1 and index 3. So you see it's taken this section down here. Hard for me to select that with the mouse, but it selects 5, 6, 8, well, of course I got to look at the one up here. This is the original one, 5, 6, 8, and 9. Notice it doesn't modify any of these operations do not modify the original array. So I have to, I'm looking at this array up here, 5, 6, 8, and 9. We'll look at some other ways to manipulate arrays in the next, in some later sections. But this gives you some basic idea how you can manipulate arrays. Over the next few lectures, we're going to learn about linear regression. And linear regression is a classic method of fitting a line to a set of data. It's not exactly a machine learning model, but many of the ideas in linear regression can be applied to machine learning. Specifically, it uses linear algebra. And if you're familiar with linear algebra, this might be a bit of a refresher. If you're not familiar with linear algebra, this is an opportunity to learn a very important branch of mathematics. Even if you're not really good at math, it doesn't matter. It turns out linear algebra is not very complicated at all. It's really just multiplying and adding. That's all it really is. What makes it challenging are some of the abstract concepts and terminology that you may hear. So we'll go through it one step at a time, and along the way, you'll learn quite a bit about the math, and you'll learn how linear algebra is applied to machine learning. As you will find, it's very important to modern machine learning. So I have a notebook here that describes this linear regression problem. And I'm going to import a few libraries because we're going to use this to apply these ideas. We're going to use NumPy and solve a real problem using NumPy, and you'll see how easy it is to use. We're also going to use Matplotlib to plot some of the results to get a visual idea of what's going on. So you remember from basic high school math, this equation for a line, y equals ax plus b. You may have seen it as y equals mx plus b. It's the same thing. So in this example, a represents the slope of a line, and b represents the y-intercept of a line, where the line would intersect the y-axis. So if we're given 2 points, x1 and y1, and x2 and y2, we could solve for the values of a and b to define the line that passes through those points. So let's see how we might do that. So in this bit of code, I've assigned the values of x1, y1, and x2, y2 to these values, 2, 1, and 3, 3. Those are my 2 points. And I'm going to plot out the line that passes through those 2 points. And here's the line. There are the 2 points, and there is the line that passes through that. So the question is, what is the equation that describes this line? We need to find the values of a and b in this equation above to describe this line. And with a little bit of algebra, we can do that. All we need to do is substitute in these values of x and y, x1, y1, and x2, y2, and create these 2 equations. And you can, if you remember from high school algebra, these are a set of simultaneous equations with 2 unknowns. And it's easy to solve for a and b. So knowing that these are the values, we could then plot a line with that y-intercept just to confirm that we got the right values. So if we plot that line and the y-intercept is right here, where x is 0 and b is minus 3, you notice that line passes through those 2 points above. So how does linear algebra help us? Well, this problem can be abstracted using linear algebra. Remember that system of linear equations that we had before, using those 2 points and 2 equations. We can rewrite those 2 linear equations in matrix form like this. On the left, what we have is a vector. And this vector contains 2 values, which are the 2 y values, the same ones you see up here. And these square brackets means that this is a vector. And on the right, on the far right, we have the 2 variables, a and b. And those are the 2 variables we're trying to solve, just like we did earlier with the set of simultaneous equations. And in the middle, we have a matrix, in this case, a 2 by 2 matrix. And you notice the values in the matrix are just the coefficients of a and b. You see 2 and 3, which are the coefficients of a, and the value 1, which are the coefficients of b right here. Now, when we multiply this vector times this matrix, we take a multiplied times 2, take b multiplied times 1, and we add the 2, just like we see these equations up here. And the same thing for the second row. Take a multiplied times 3, take b multiplied times 1, add the 2, and that's the result, 3. So whenever you do a vector and matrix multiply, you take this vector and rotate it to the left by 90 degrees and multiply it by this row, multiply each of the components, and add all the values. You can also multiply matrices times matrices. It's the same idea. We can rewrite that equation like this. Y equals AV, where A is this matrix in the middle, And v is this vector representing a and b. And in this case, y would represent this vector of two values, 1 and 3. And that's what these three equations show. All we're doing is substituting values to represent these two equations. Now to solve for a and b, that's equivalent to solving for this vector v. So how do we go about that? Well, we can do this through the means of an analogy. Let's say we had an equation of one variable that looked like this. 1 equals 2x. By inspection, you know what the answer is. How do we solve for x? You know that x is 1/2. But if we were more explicit about it and just take it one step at a time, the way we would solve that is we could multiply both sides of the equation by the inverse of 2, which is 2 to the power -1. That's its inverse, or 1 over 2. So if we multiply 2 to the power of -1 times 1 on the left, and we also multiply 2 to the power of -1 on the right, you can see that on the left we'll have the value 1/2, and on the right, this term, 2 to the raised to the power of -1 times 2, that becomes 1. So that term is eliminated, and we find that x equals 1/2. Pretty simple, but what's important is the concept of this inverse. We multiply both sides by the inverse of 2. So we had an equation earlier, y equals AV. We could find the value of v, or the vector v, if we were to multiply both sides by the inverse of a, or a inverse. That would, in theory, eliminate this a on the right, and we would have the value for the vector v. So that's what this equation shows here. If we were to multiply the left by a inverse, the matrix inverse of a times y, and on the right we multiply a inverse, the inverse of a times v. And it turns out this quantity a inverse a, just like 2 to the 2 inverse 2 multiplied together is 1, a inverse a is not exactly 1, it happens to be what's called the identity matrix, which is similar to the concept of 1 in scalar math. So we would then rewrite this equation as v equals a inverse y. So that would give us the values for a and b. So the question is, how do we compute this inverse? How do you compute a inverse? And there are a number of numerical methods to do that. It turns out to be kind of challenging to do it by hand for large matrices. For small matrices, it's not too difficult, but for when you have a large number of values or a very large matrix, it can be very difficult. Fortunately, NumPy has some methods to compute the inverse of a matrix. So let's see how we would do this for our previous example. We could create an array, a NumPy array, given our values that we had earlier, x1, y1, and the values 1 and 1, right? It's the same as this matrix right here. x1 and y1, these are the x1 and y1, and these values 1. We'll create that matrix. And if you see, that matrix has the same shape as this matrix that we see right here. So that represents the matrix A. To compute the inverse of that matrix A, NumPy has a method np.linalg.inv. Big complicated method call, but that computes the inverse of A. And then we can print out what that inverse is. And it turns out it has these values, -1, 1, 3, and -2. That's just the inverse of that matrix. And how do we know it's the inverse? If we were to multiply the inverse times the matrix A, the inverse of A times A itself, we do that in NumPy using the dot method. So A inverse dot A, if we make that multiplication, we should get the identity matrix. And you notice the values along the diagonal are 1, and that is what the definition of the identity matrix is. All the values along the main diagonal, this is what's called the main diagonal, they are all 1, and all other values are 0. It turns out in this example, the values aren't exactly 0 because of a bit of a round-off error, but you can see they're very, very, very small. So for all intents and purposes, this is very much the identity matrix, or very, very close to it. So that shows that A inverse is the inverse of A. So now if we multiply the vector v with A inverse on the left, we will get the value of the vector y. So here's our vector y, 1 and 3, and you remember up here, our vector y right here, 1 and 3, and we multiply it times the inverse of A, multiply it by the inverse of A on the left, that'll give us the vector v. And you see the vector v has the values 2 and -3, which are the original values of A and B, which we solved earlier using basic algebra. So you can see how linear algebra can be used to solve a system of linear equations. And this can be extended to 3 equations with 3 unknowns, 4 equations to 4 unknowns, or n equations with n unknowns, as long as they're linear. And the nice thing about it is we have a library like NumPy which will help us to compute that matrix inverse. And if you can imagine, if I had 4 equations with 4 unknowns and I wanted to solve for all of the coefficients of those 4 equations or the 4 unknowns, it can be very tedious. But the matrix inverse, or this linear algebra, makes it very straightforward, as long as we have a way of computing this inverse efficiently. So next let's look at how we can extend this if we have more data, more than just 2 points. Because if we have 2 points, that defines a line precisely. But what if we have more data? Let's look at that in the next lecture. In the last section, you learned how to use linear algebra and NumPy to solve for n unknowns given n equations. So in our specific example, we had 2 unknowns, 2 variables a and b, and we had 2 points. So that defined the line that describes those points precisely. But what if we have more than 2 points? What if we want to find a line that passes through many points? How would we do that? And in this section, that's what we're going to learn. And this is what linear regression is all about. Let's say we had more than 2 points. We had n points. Let's say we had the values x1, x2, x3 up to xn, and y1, y2, y3, and so on up to yn. We could write a simple linear model similar to what we saw earlier, like this: yi equals axi plus b. We would still have the constants a and b like we had before, but we have many points for y and many points for x. And we can rewrite this in matrix form, similar to the way we did earlier with 2 points, like this. We would have a vector on the left, y1, y2 up to yn, equals a matrix x1, x2 up to xn, and then a bunch of 1s, multiplied by this vector a and b. And if you go through the same exercises we did before, to rewrite this equation in algebraic form, we would multiply a times x1 and then add it to b times 1, and that'll give us y1. And similarly for x2, y2 up to xn, yn. So the way we would multiply it, take the vector ab, rotate it to the left 90 degrees, and multiply it by these 2 values individually, add the 2 values, and that gives you the result. So if you go through that exercise, you can show that this matrix equation is the same as this algebraic equation for all values. So let's introduce some variables to simplify these equations like we did before. We have this vector y representing all the y values. We have a matrix A that looks like this. And we have a vector v which has the values of a and b. And this is what we want to solve for, these values of a and b. And if we substitute that, we have the same equation we had before. The only difference is this matrix A is no longer square. It is no longer a 2 by 2 matrix. It is a n by 2 matrix. As we saw, if that A is a square matrix, meaning that n equals 2, then we can determine A and B exactly by computing A inverse. Compute A inverse, multiply by the vector y, and that'll give us the vector v, which is the same as getting the values for A and B. And that represents the line, the equation for the line that we're looking for. So in the case where n is greater than 2, the matrix A isn't square and we can't invert it. It turns out there isn't a strict definition for the inverse of a matrix that's not square. So one solution to this problem is to compute what's called a pseudo-inverse. And we can compute a pseudo-inverse of the matrix A by multiplying A by its transpose. And the transpose is effectively rotating the matrix to the left once. And if you multiply those two, you will get a square matrix. So A transpose looks like this. We write it this way, AT like that. That means A transpose. So if we multiply this equation we had up here by A transpose, we have A transpose times Y equals A transpose A times the vector V. And it turns out this quantity A transpose A is now a square matrix. So that matrix is invertible. We can compute that inverse. So if we were now to multiply both sides by the inverse of this matrix A transpose A, on both sides, we'll have this equation. Looks complicated, but if you work through it, it's correct. So what we have is A transpose A inverse. This is a square matrix. We can invert that. Multiply it times A transpose. Multiply all that times Y. And the same thing on the right. A transpose A inverse times A transpose times A. All right? So all I did was just substitute variables. That's all I did. No more complicated than that. Just substitute variables. Now, if we simplify this, we can eliminate this, a lot of these terms, and it comes out to solving for this vector V. So V equals AB, right? Equals A transpose A, the quantity inverse times A transpose times Y. That's the simplification. And the reason that's true is because if you look at this term here, A transpose A inverse times A transpose A, these two are the inverse of each other. This matrix is the inverse of that matrix, so when we multiply that, that just becomes the identity matrix. And as we saw, whenever you have the identity matrix times any vector, that's the same as just the vector by itself. So the result is V equals the quantity A transpose A inverse times A transpose all times Y. So that's interesting from a theoretical perspective. So let's put it into a practical example and see how it works. So let me come up with a bunch of values. Here are some real values for X and some real values for Y. And I'm going to plot those as a scatter plot, just so you can visualize what it looks like. So here are those values, all the X and Y values, many of them. And by inspection, you can see that there is probably a line that fits this curve, fits all these points. There's probably an optimal line that fits through all these points. So how do we find the equation for the line that goes through most of these points, or at least is close to the line represented, close to all these points? Let's go through the same process we did before. We need to create this matrix A that's of this form, x1 through xn and a bunch of ones. Right? And the way we do that is we can create a NumPy array given these values x above. These are all our x values right here. And we're going to reshape it so that we'll add one more dimension. Because if we just use NumPy of a list like this, it'll give us a single dimension. And this reshape len x like this, comma 1, adds one more dimension. So this is going to turn it into a matrix. So originally x was a vector, this will turn it into a matrix. Now we need to do one more trick because we need to add all these ones right here. And we do that by creating a vector of ones, and we use this NumPy method np.append. We append the matrix, the ones, and then we use this axis equals 1, meaning we want to add all of these ones in this axis like that. And then we can print out that matrix A and see what we get. So what we see are all the values x and then a bunch of ones. That's exactly the matrix that we want. All the values x and then a set of ones in this column. All right? So we have our matrix A. So now we need to just compute this pseudo inverse, A transpose A, the quantity inverse times A transpose. And with NumPy, that's very easy to do. To compute A transpose, in NumPy we just type A dot capital T. That gives us the transpose. And then to compute the pseudo inverse, we first compute the inverse of the quantity A transpose A, this quantity in here, A transpose dot A, that's A transpose A. We take the inverse of all of that, and then we multiply it times A transpose, which is again using dot. When we do a matrix multiply in NumPy, we use the dot method. that gives us the pseudo-inverse. And if we print that out, this is what it looks like. These are all the values of that pseudo-inverse. And now to compute A and B, we multiply the pseudo-inverse times this vector y. And the vector y are all these values right here. These are the values y. And this little bit of code does that. So what we do is take the pseudo-inverse and then multiply it by the vector y. And then we're going to plot out all the x points and all the y points, but we're also going to plot out the line based on those coefficients a and b that we computed. So let's plot all that out and see what it looks like. So those are all our original points that you see in red. And then this is the line, the values that are represented by the values a and b, the slope a and the y-intercept b. And you can see by inspection, it seems to go through most of the points. So we did compute a model, if you will, that represents most of the data. And if you think about it, it is a bit like a machine learning model. We could make a prediction using this simple model. Let's say we had some new values x, we could then predict what would be the expected value y given those values a and b. It's just a linear equation. So even though it's not a sophisticated machine learning algorithm, the idea of fitting a curve or finding some parameters that represent a model and then using that to make predictions in the future is the same concept. Of course, an important question to ask when we have any model is what's the accuracy? How accurate is that line to all the values that we had originally, which we might consider our training samples? And one way we could measure that accuracy is to take all of the estimated values, and that's what this term is here, AXI plus B. These are the estimates based on this line that we generated. Subtract that by the real values that we know, YI, square that, so this would be the squared error. This is the predicted values minus the known values, or the ground truth. Square that, so that'll give us a positive value. Add up all those values and divide by the number of terms. So this is like an average. We would average all the mean squared errors. So this is what's called the mean squared error. And we could represent it by this Greek letter epsilon. So we can calculate that mean squared error like this with NumPy. It's very simple. AX plus B is, we just take the coefficient A that we computed and the value B that we computed, multiply times the vector X, subtract the vector Y, square that. That gives us the mean squared error. That gives us the squared error, and then we take the mean of that, which is the average. And then finally, we want to take the square root of it, because what we really want is the average distance between each of the values, because this is a squared value, we want to take the square root. So if we take that square root, we see that the typical error is 2.12. 2.12. So, and if you look at it, most of these values are probably within about 2 of this line. If you look at this y-axis over here, most of the values are within about 2. So it does fit the data reasonably well. Now, of course, if we had data that was wildly different, that were all over the place, the error would be considerably different. But as you can see, most of these values are close to a line, so you expect that the error is relatively low. So if you've had linear algebra in the past, you've probably seen something like this, and it probably looks pretty straightforward. If you haven't had any linear algebra, you might want to review these lectures a couple more times, and that's perfectly fine. I'll tell you, there have been math concepts that have taken me many, many years to learn. There are some that I spent 20 years learning, but eventually you'll get it. And as always, if you have any questions at all, feel free to post a question or send me a private message. I'll be happy to answer any questions you might have in detail. So everything we've done so far works well if we have data that fits a straight line or looks fairly linear. But what if we have a more complex data set where the data would not fit well with a straight line? In that case, we could use a more complex equation to describe our data. We could use a polynomial of higher order, or we could in fact use any equation as long as it had linear coefficients. And that's the real power of linear regression. So let's see how this would work in practice. Let's extend it to just a quadratic equation, and you could see how this might work. So let's say that we had an equation like this, and we wanted to fit our data points to a quadratic equation, y equals ax squared plus bx plus c. So it's very similar to what we had before. The only difference is we've added one more term, a quadratic term. So what we're trying to learn are these coefficients a, b, and c. And those are still linear terms. So we can write this as a matrix equation, similar to what we did before. And the matrix equation would look like this. We would have a vector on the left representing all the y values. We'd have a matrix in the middle, but instead of being n by 2 in dimension, it'll be n by 3 in dimension. N by 3. And then we would have a vector a, b, and c representing the coefficients that we want to determine. So this matrix in the middle, this matrix A, the first column is going to have the square terms, x1 through xn all squared. And then we'll have the middle column, which are the linear terms, and then we'll have ones. And we go through the multiplication that we did before, multiply this vector times this matrix. Remember, we take this vector, rotate it left 90 degrees, multiply it by the first term, the second term, and the third term respectively, and add all those values, and you'll get exactly this equation that you see up here. So what that means, we have a matrix that looks like this. It's n by 3 in dimension. And we can use the same procedure as we did before to determine the coefficients a, b, and c, computing the pseudo-inverse like this, A transpose A inverse times A transpose, and multiply by all the values y, and we will get the terms a, b, and c, which closely fit the data that we have. And this process is widely used. It's been used for decades, if not more, or even centuries, to fit a curve to a set of data. It's perhaps one of the simplest forms of machine learning, if we want to call it that. And it can be used to make predictions. And this was widely done, particularly in the areas of physics. If I had a bunch of data and I had a model that I was trying to fit, I could then use that data, which may have some error in it, it may not be perfect, and then fit a curve and measure the error to see how close the data fit the model. And if the data fit very closely to the model, then we could argue that our model is quite accurate. So in this case, our model is this polynomial function. And the knowledge we're trying to gain, or what we're trying to learn, are these coefficients a, b, and c. Now let's look at some statistical functions and also some linear algebra that we can perform with NumPy. So NumPy has a number of stats functions here. So here's a case where I created an array with values 1 through 5. And there's a function called mean np.mean, which gives me the average. And you can see the average is 3. If I was to add up all these numbers and divide by 5, I think I will get 3. Similarly, there's standard deviation. This gives me the standard deviation of all these values. And also, if I want the minimum, there's also, of course, a maximum and a number of other functions that you can perform on this set of values. Here's an interesting one called argmax. And what that does is gives me the index of the maximum value. And we look at the maximum value here, its value is 5, so the index comes out to be 4. Of course, the indices are numbered from 0 through 4, so that is the largest value. And this argmax is used in a number of different places, and we'll see examples of that in other machine learning cases where we want the maximum of, let's say, the output layer of a softmax function. That would give us probably the most likely output. All right. And of course, the documentation lists many, many more statistical functions. I've just shown you here. There's max and argmin and so on. You can find that in the documentation. Here's some examples of linear algebra. that we can do with NumPy, and this is where NumPy really shines. So if I have, let's say, a set of ones, 5 ones, and I multiply all that by 2, that'll be values 2, 2, 2, 2, so 5 2s. If I create another array of 1, 2, 3, 4, 5, I can compute the dot product or the inner product of those two vectors using np dot, right? And I specify the two arrays. So if I was to multiply the vector 2, 2, 2, 2, 2 by 1, 2, 3, 4, 5, I'll get the value 30. It's a scalar value. Similarly, if I have a two-dimensional matrix like this with 1, 2, 3, 4, the classic two-dimensional matrix, I can transpose that matrix using a dot capital T. And if I transpose it, what that does is it transposes across the main diagonal. Notice the diagonal values 1 and 4 are unchanged. It just interchanged 2 and 3 like this. So that's the transpose of a matrix. And these are common linear algebra operations. If you're not familiar with linear algebra, don't worry too much about it. If you are familiar with linear algebra, you've probably seen this kind of thing before, and this just shows you how to do this in NumPy. Similarly, if I want to compute the determinant of a matrix, there is np.linalg. A lot of the linear algebra operations are in this module called linalg, and I compute the determinant, and the determinant happens to be -2. And if you remember your basic linear algebra, that would be 1 times 4 minus 2 times 3 for the simple case. For larger matrices, it's quite a bit more complicated, but fortunately, NumPy does all of that for us without a lot of work. I can also invert a matrix using the np.linalg.inv function, and that will compute this matrix like that. And it'll, of course, do it with higher dimensions. And notice if I have the inverse of the original matrix, this was 1, 2, 3, 4, which was my A matrix, and I invert it and I get this matrix B. And if I multiply a matrix times its inverse, I should get the identity matrix. So let's see how that works. If I do use np dot, that multiplies two matrices, similar to what we did with a vector. So np dot multiplies matrices, and you notice this is very close to the identity matrix. Notice the main diagonal has values 1. The off-diagonal elements are 0 or extremely close to 0. So it's maybe slightly off due to just some round-off error, but this is very close to 0. So that demonstrates some statistical functions and linear algebra functions. And of course, those are all found in the documentation. NumPy integrates with Matplotlib, and Matplotlib is a really nice plotting library for Python. It does all kinds of plotting, and it's very easy to use. You can produce some very sophisticated, very high quality plots without a lot of work. So let's look at some examples to see how this works. So what I'm going to do here is I'm going to import math because I'm going to use some math functions, and I'm also going to import Matplotlib, and it's common to import it this way, matplotlib.pyplot as plt. So let me run that cell. It imports Matplotlib. And then what I'm going to do is create an array, a couple of them, one of sine values and one of cosine values. And NumPy has math functions like np.sine and np.cosine to create sine and cosine. And I'm going to, let me run that. And the way it's going to start from 0. The x value is going to start from 0 to 2 pi, and it's going to have up to 50 values of that. So if I was to actually look at the sine and cosine values, if I was to run this cell, the list of sine values, you see it's an array, and it has a number of values there. All right. So now let me use Matplotlib to plot that's both sine and cosine curves. And there's a plot function where I give it the x values, the y values. I can give it a label and a color and a line width and many other parameters. And I'll label the y label as y and the x label as x, and I'll also show a legend. All right, so let me run that cell, and I get a beautiful plot. And as you can see, I plotted both a sine curve, which starts from 0, right, all the way to 0 to 2 pi, right, and a cosine curve, right, and cosine, of course, starts from 1 when the angle is 0, the x value is 0. And notice I've used different colors and different line widths. There are many, many parameters you can adjust. The Matplotlib library has many features that you can use. All right. And notice I put the legend in the upper right, right? So it shows what each of these represent with the label for each. And I have the y-axis and the x-axis labeled as well. And also notice it scales everything very nicely, so I don't have to worry about scaling. But I can adjust that if I like. Let me do another one. It's very similar, but I'm going to use a scatter plot in this case, using x and y. And I can then plot each point, right? And here I did it with the color green. And notice this is it plots each point individually. So if I was to choose a fewer number of points, it would definitely be much more sparse. So now let me do one more where I'm going to plot a bar chart. And it proves a bar chart like this, right? Or I can use a horizontal bar, which is bar H, right? It'll produce a horizontal bar, right? So there are many, many other things I can do with Matplotlib. And if I just go here to the website, there is many examples that we can look at. And if you look at some of these, they're really quite impressive. They're very eye-catching. They have a lot of sophistication to them. I can have subplots if I want. And we'll see more of these examples as we go through. We'll see more ways to use Matplotlib as we go through some more examples. There are tutorials for, there's a usage guide. You know, you can start from zero and go through different sections of Matplotlib. There are some intermediate examples and some advanced examples, right? Transformations, colors, how to include text, how to use images, and so on. And there's the API, which you can look at in detail, and we'll probably go through that at different points to see how to use different parts of the API, right? So that's just a brief introduction to how we can do some visualizations with NumPy. We're going to do some more visualizations in using Pandas and Keras as well. So stay tuned. NumPy can be used in conjunction with Matplotlib to read, manipulate, and display images. And this is convenient because images are like a 2D array, and each value within the array is a value of a pixel. Of course, that pixel could be grayscale, which in case there's a single value, or it could be color, in which case there's at least an RG, and a B channel. So let's see how this works with some examples. So first what we're going to do is we're going to import from this SK image library the IO module, and that allows us to read images from many different sources. We can also write images from many different sources, so that's a very convenient library. And here I'm going to use that IO module to read an image from a URL. This is the image, and this is going to be returned as a NumPy array. And then I'm going to use Matplotlib to display that image, to show the image. So let me run that cell and see what it looks like. So here we have an image, and you can see the dimensions right here displayed using Matplotlib. And this happens to be an image of a Hughes 500. This was a helicopter that I rented and actually flew in Hawaii many, many years ago. I'm a rated helicopter pilot, so whenever I go out somewhere and I'm going to spend lots of money renting a helicopter, I want to be able to log the time. And it turned out the owner-operator was pretty reasonable with it. He said, well, sure, I'll let you fly it, but I got to start it. And the reason being is that this is a turbine helicopter, and it's very easy to destroy the engine if it is not started carefully. So he said, let me start it. And once he started, he said, all right, you got it, fly it. It's all yours. So it was a lot of fun. Anyway, back to Matplotlib and NumPy. So let's get the shape of this image. And you see the shape is 331 rows by 442 columns. And it also has one more dimension, 4. And that dimension 4 is the number of channels. So this is actually a color image, so you'd think they're RG and B, but there's also an alpha channel as well. And we can inspect that. So let me add another cell here. And let me just look at some of the values in some of the cells. So let me look at the upper left-hand corner. So this is 0, 0 up here. So let me just look at the value of the pixel in that corner. And you see it has these values. It has 4 values, R, G, B, and alpha, right? So the alpha channel happens to be all maximum, or 255. And we can show, let's try and see if we can't pick another pixel somewhere here and see if we can get the colors right. So I'm going to pick something in this region here, which looks like it's mostly red. So that's around 125 and maybe 325. So let me try that. 125 and 325. Let's see what we get. And you see, so it looks like the first channel seems to be the largest. So it's mostly red. It's got a little bit of green and blue in there as well. Of course, the alpha channel is still 255. It's fully saturated. But so this is that pixel right over here. And so it's generally what we would expect. So there's some other things we can do with Matplotlib, with NumPy. And NumPy will allow us to rotate the image in a different dimension. So what this will do is flip the image left to right. So this syntax will flip this image. All right, and you see it's flipped left to right. And this is a useful transformation, because a lot of times when we're training a model with lots of images, we can augment the data set with flipped images. That doesn't work in say the case of handwriting recognition, but it could work in cases of people or animals or scenes or other things that we might see in nature, where a flipped image is the same thing as the normal image. And so that's a way of augmenting our data set with more data, even though we haven't collected more data. Similarly, we can flip the image top to bottom using this syntax right here. And just like we did before, if we wanted to select a subset of the image, we can use the NumPy syntax like this. So let's see what that does. So that selects just a subset of that image right over here. Actually, it's right up here, right? Right? And you can look at the dimensions and convince yourself that is a subset of that image. All right. And this is, of course, years ago when I was young and still had a full head of hair. Don't look exactly like that anymore. So that gives you some examples of how to read images and how to manipulate them and how to inspect the data. And that's an important skill, because sometimes you may want to be sure that what you're looking at is what the model is looking at. So it's important to be able to visualize images and visualize the data. You can also use this to display data that isn't necessarily an image originally. Maybe you generate some data and you can still display it as an image using this plt.im show. All you need is a NumPy array that has the right dimensions. NumPy can be used to reshape data, and this is often important when we have an image and we need to restructure it in some way. So let me create an array here, and this is a two-dimensional or a matrix, two-dimensional array, and you can see I just have 4 values in there, 1, 2, 3, 4. And if I take the shape of that, let's see what we get. I get a 2 by 2 matrix, 2 by 2 matrix. So I can reshape it as a 4 by 1 matrix, and it looks like this. It's still a matrix, but it's now 4 by 1. I could similarly reshape it as a 1 by 4. Right? It's the same thing, it's just oriented the other way. And if I want to get the shape of it, and when I reshape it, you can see it has that shape 4 by 1. So let's look at another example. I'm going to create another two-dimensional array, which is of shape 2 by 3, right? 2 columns, two rows, 3 columns. Right? So I can reshape it the other way as 3 by 2, right? And notice how that works. So it takes the first value 1, 2, then 3, 4, then 5, 6 in that order when it reshapes. All right? So I can do something. I can also use a dimension of 0 because you notice this is 2 dimensions, and even up here when we had just in one row, it was still 2 dimensions like that. So if I want just a single dimensional array, if I want all the values in a single dimensional array, I can use 0 right here like that. Okay, and you notice the difference here, there's only 1 square bracket here, whereas up here there were 2 square brackets because this is a single dimensional array. And I can confirm that if I was to get the shape of that array. You notice it's 6, comma, and it doesn't show the other dimensions. There's only 1 dimension, right? But I can reshape that back into a 2 by 3 if I want. So you'll notice that the shape is very important, getting the right shape. And that's often a common problem whenever working with machine learning models, because different models will expect data in a certain dimension. So debugging these dimensions is really important. So whenever you get stuck, what you want to do is use this shape, get the shape of any array, a NumPy array that you might have, and check the dimensions and make sure they're correct. And if you're not sure what's in it, you can always look at the values and try and understand how it's being organized and reshape it as needed. Welcome to the Foundation section on TensorFlow. In this section, you're going to learn what TensorFlow is, why it's needed, and why it's popular. You're going to learn how to define and train models. And we're going to work on a very simple model that's easy to understand. It won't have any complex data, so it'll be easy to experiment with. You're also going to learn about activation functions, loss functions, and optimizers, and more importantly, how to select the right configuration for your problem. You'll also learn how to save and restore trained models, so you can easily save the knowledge that's learned during training and use it later for prediction. So what exactly is TensorFlow? Well, it's a popular machine learning library. It's open source, developed by Google, it's high level, and it's used for machine learning, more specifically deep learning. TensorFlow is easy to use. You can create a machine learning model with just a few lines of code. And that's because TensorFlow 2 includes Keras, which hides a lot of the complexity of low-level details. In the past, Keras was a separate library that was built on top of TensorFlow to make it easier to use. Since then, with the introduction of TensorFlow 2, Keras is part of TensorFlow, so there's no need to install that separately. The benefit is that you can train a model quickly with high-performance GPUs all in Python. So why do we need TensorFlow? Well, it turns out there are many steps to defining a model. You have to define types of layers, activation functions, hyperparameters. Fortunately, TensorFlow does that for us already. TensorFlow includes a number of training algorithms and optimizers, so you don't have to write your own backpropagation algorithm and debug it to be sure it's working correctly. You can also monitor training and performance, so you can plot, test, and train accuracy easily. And as mentioned, there are easy-to-use APIs to save and restore a trained model, so you can save it later for prediction. All right, let's look at a simple Keras model. And I've already opened up Google Collaboratory here. And let me open up an example. So I'm going to open a notebook, select GitHub, because I have an example in GitHub, and put in my repository. And I'll put a link to that in the resources section. And what I want to look for is this one, Notebooks Keras. Notebooks Keras. And it opens it up. And let me just clear all the output before we go any further. And it gives us a nice description of Keras and what it does. It's a deep learning library for Python. It's the most popular deep learning library because it's so easy to use. It has a number of layers defined, activation functions, optimizers, and you can just define and train a model with just a few lines of Python code. Keras also interoperates with Matplotlib and NumPy, which is very convenient. So in this cell here, we're going to import a number of Keras modules. And we're also going to import Matplotlib and NumPy because we're going to need some of those as well. And of course, we get our warning as usual, which we can ignore. And then what we're going to do here is we're going to learn a mathematical function. This is a very simple example, which is a nice place to start. You always want to start simple. And this is going to create a function, in this case a parabola, and we're going to train a model using, and this is obviously a very straightforward example, but it's convenient because it's not a lot of data, it trains very quickly, it's easy to modify, you can get results very quickly, and you can understand how they work. So here's the function I'm going to use for my training data. I'm going to generate this data, and it's just a parabola. It's 10x squared minus 5x minus 0.5. I could use any numbers I wanted there. I just chose these arbitrarily. For the training data, I'm going to generate a number of random x values. I'm going to generate 10,000 of them, and they're going to range between 0 and 1. That's what the np_random.rand function does. And then I'm going to take those random values and pass that into this function. And NumPy is just going to apply all those values to this function, and I'm going to get a number of y-train values. So I'm going to have 10,000 x-train and y-train values. I'm also going to generate some test values. In that case, I'm going to use a range from 0 to 1 of just 100 test values, right, linearly. And then I'm going to apply that to the function and get my test values. So I'll run that. So let's visualize the data set. I'm going to use Matplotlib to do that, and I'm going to plot this out as a scatter plot. And I'll plot out both the train and the test. So the train values are color blue. So you see these are the training values, and it's a scatter plot, so they're all overlapping dots. If I used a smaller number, you would probably see the individual dots, but it's randomly distributed all over, right? And the test values are these right here, in red, the test values. Okay, so notice the x ranges from 0 to 1, and the y ranges somewhere around -1 to 4.5 or so, depending on our function. So next we're going to define the model, and this is a multi-layer dense model with rectified linear units as the activation function. We'll talk about activation functions a little bit later. And the output layer doesn't have an activation function because we want a continuous output value. So it's going to start out, I define it as a sequential model, and I'm going to add each of the layers. First I'm going to add a dense layer with 200 units, and it has an input dimension of 1 because our input value is a single scalar, an x value. And I'm going to add an activation function, which is a rectified linear unit, another dense layer, which has 20 units, another activation function, which is a rectified linear unit, and a final dense layer, which has 1 output unit because we want 1 y value at the end. So I'll create the model. All right, happens very quickly. So one other thing I can do is get a summary of the model. And I do that with model.summary, like this. So let me run that. And it gives me a summary of the shape of each of the layers, a description of each of the layers, the number of parameters that are going to be trained. And you see these dense layers, there's quite a few parameters that are being trained. So the total number of parameters is 4,441. So those are all the weights and biases that the model is going to learn when we train it. Keras includes a number of common deep learning layers, and there are many different types. And very complex models will use many different types of layers. And you can even develop your own layers if you want, if you're an advanced data scientist. And remember, if you're developing a model, it's an empirical process. There aren't any hard and fast rules for developing models. So the best approach is to find an example of a similar problem and adapt that model for your own use and your own data set. So to add a layer, we can use the sequential model API. What we do is create an instance of the sequential class, like we see here, and then we can add different layers. For example, if we wanted to add a dense layer, we would write the Python statement model.add and the dense layer constructor and specify a number of different parameters. And it turns out the first parameter in this case happens to be the number of units. And if you see over on the right, we happen to have several dense layers. In this first example, the first layer has 3 units, the second layer has 4 units, and the final layer has 2 units. As mentioned, there are many different types of layers. For example, convolutional layers. There are several variations of those. There are 1D convolutional layers, 2D, separable, transpose, upsampling. There are many types of recurrent layers for recurrent neural networks, long short-term memory, and so on. When you look at all these layers, you might get overwhelmed. And the best way to tackle all of this is one step at a time. You don't have to learn the details of every layer right away. Each of these layers solves different kinds of problems. And Keras gives examples for each type of layer. And also, we'll learn about each layer through different examples. So don't assume you have to know everything about every layer right away. It's just take it one step at a time. Deep learning models also include activation functions. And these activation functions are nonlinearities that appear between model layers. And if we didn't have those, a deep learning model would not learn any abstract features. In fact, what would happen is it would all collapse into just a single layer. That's just a consequence of linear algebra because we're multiplying matrices as we go through each of these layers. And if there was no nonlinearity between the layers, it would just collapse into a single matrix, which wouldn't really learn very much. So in Keras, there are a couple of different ways we can specify an activation function. We can specify it as a separate layer. We can add an activation layer and specify the type of nonlinearity or the type of activation function. Or we could add it as a parameter to a layer. So in the final example you see, we have a dense layer and we specify the activation as a parameter. As you might guess, there are many different types of activation functions that serve different purposes. We'll go through a few of them here and when they are used. So the first one we'll use, and perhaps one of the most important, is the rectified linear unit. And it has the shapes as you see on the right there. The first one is a rectified linear unit, which means that for all input values less than 0, the output is 0. And for all values greater than 0, the output is equal to the input. It seems really trivial and doesn't really make a lot of sense, but it turns out that's extremely important because it avoids what's called the vanishing gradient problem. This was a very important problem that many models suffered from in the past, so that's often used between hidden layers of deep learning models. There's also a variation of that called soft plus. That's also used sometimes, and you can experiment with the two and see how that affects your model performance. Another important layer that's used in the output layer is what's called the softmax. And the purpose of softmax is to produce an output for classification. So if we are classifying, let's say, digits, numerical digits, and we have 10 outputs, we want the probability of any one of them being true to be 100%, the total to be 100%. So that's what softmax does. It distributes the output values so they equal 100% or a value of 1.0. And to specify that one, we would use just the string softmax. So that's often used for classification output layers. Another one that's historically important and sometimes used, but not very often, is what's called the tanh or sigmoid. They're similar, they have a similar shape, but behaves a little bit differently. You can see the transfer function on the right. They do suffer from the vanishing gradient problem, so they aren't used as often as ReLU, but occasionally you might use it in hidden layers. And we'll see some examples later. And to specify those, we use either the string tanh or sigmoid. And finally, there's the linear activation or no activation. And the linear activation doesn't do anything. And that's often used in the output layer if we want some kind of a numerical output. Let's say we're trying to estimate housing prices. In that case, we want a linear value. We want a number that could vary between a wide range. So in that case, we would use a linear activation function. As we saw, the model that we defined has a number of parameters that it's going to learn. There are 400 in the first layer, 4020 in the second, and 21 in the final layer. And you can see how this might work because there are 200 dense units in the first layer. So there are weights and biases for both, so that comes out to 400, one for each weight, one for each bias. The activation function doesn't have anything to learn. Now the second dense layer has interconnections to the first layer, so there's a multiplicity between the number of connections to the previous one and the new units that we're adding, so the total number is 4020 there. And the final layer, there's 21 because there's 20 connections to the previous layer plus one more for the final layer, since there's one unit in the final layer, so that's how we come up with this number. So those are all the weights and biases we're going to learn during the training phase. So let's look at how the training works. So this is what it happens in two steps. First, we have to compile the model, and during the compile step, we specify the loss function. Here we're going to use the mean squared error loss function. There are many types of loss functions, which we'll talk about shortly. Similarly, we're going to define an optimizer. Here we're using the Atom optimizer. It's a very good optimizer. There are several, and we'll talk about those. Then we're going to use the model.fit method. We'll give it the training data, the X train and the Y train, the input values and the expected output, a batch size, and we're going to train for 10 epochs, meaning it's going to iterate through the data 10 times. And also we're going to validate against the training data. There's also a verbose flag that defines what's going to be printed out during each training step, which can be convenient if it's a long training job. So let's go ahead and train it. And this goes very quickly because it's a very simple model. We don't even need GPU acceleration. In fact, I think it'll probably take longer if you use GPU acceleration because it has to move data in and out of the GPU. All right. And the nice thing, when we ran this fit function, it returns a history object, which has data about how the training progressed, all these values, the loss and the validation and so on. So the loss is the comparison between the training input and the expected training output. And you see it's pretty high in the beginning, and then it gets really small. So it means that it's getting closer and closer to the expected output. And this is the same thing for the validation set, and that's also getting smaller. So let's plot that, both the training loss and the validation loss, and see what that looks like. And it's pretty good. You see that it trains very quickly. It's a very simple function to learn, a simple model to learn, so it trains very quickly, only in a few epochs. So you can see there's really not a lot of value in training it well beyond maybe 5 or 6 epochs, even though we went all the way to 10. Doesn't really, and we can see that there's not a lot of variation here between the test and train. It might be very close. Let's see, a little bit of variation, not a lot. 6.3 times 10 to the minus 5 to 7.3 10 to the minus 5. So it's actually a fairly well regularized model. So this is a place where you can experiment. We can try different parameters for this model. We can try different optimizers, different loss functions, batch size, and the number of epochs, and so on. And you can experiment with all these values and to see how they impact the training accuracy. To train our model, we also need to specify what's called a loss function. And a loss function measures the output accuracy. And the way it does that, it compares the difference between the actual output value of a model and the expected value. And that value is used to calculate what's called a gradient. And a gradient you can think of as going downhill. The gradient would be like the direction of the hill going downwards. And this gradient is used to compute weights and biases to update the model in what's called the backpropagation algorithm. And the ultimate goal is to minimize the loss or the expected output between the actual output. So if you look at the diagram on the right, we have an input which we know is a 2. The label is a 2, as you see in the lower right. But the model has produced an output of 3. So during training, the loss function will compare the two outputs, 2 and 3, and say, well, there's a difference and we need to update the weights and biases in a direction such that the output will be a 2. So that's what a loss function does. So as you might have guessed, there are several types of loss functions. There aren't that many compared to, say, activation functions. There are really only 2 that we need to worry about. One is called the sparse categorical cross entropy, and the other one is mean squared error. And sparse categorical cross entropy is used for classification tasks, cases where we have multiple outputs and we expect one of them to be true or one of them to be most likely. Let's say in the case of our image recognition task where we're trying to identify different digits, we had 10 outputs and they were what are called one-hot encoded. And one-hot encoded means for any expected value, only one of the outputs will be at a maximum. And if you look at the right over here, we have 10 potential output values, 0 through 9, representing the 9 digits, or the 10 digits, I should say. And the output, there are 10 outputs, and only one of them will be maximum at any one time. In reality, there will be some variation, as we've seen. One of them will be most likely, and that's where we would use sparse categorical cross entropy. And to specify that, when we compile the model, there is a parameter called loss, and we would specify the string sparse categorical cross entropy in that case. The other type, mean squared error, that's used for regression tasks when we have a numerical output, a single numerical output, or we could have multiple numerical outputs. And that might be used if we're, say, computing or estimating housing prices, where the output is going to be some dollar value. So the way we specify that is in the model.compile, we would use the parameter loss, and the value would be mean squared error. Now, there are some other variations to these, like mean absolute error, categorical cross entropy, and so on. You can look into the Keras documentation to understand what those are about. But for the most part, we'll really use just these 2 loss functions. When we're training a model, we can also specify an optimizer. And an optimizer is an algorithm used for training. And during training, the backpropagation algorithm recomputes weights and biases. And it's similar to solving a system of differential equations numerically, if you're familiar with that process. There are a number of variations to the backpropagation algorithm, and some are more efficient than others, depending on the nature of your dataset. Keras includes a number of different optimizers. Several different types have been developed over the years. The traditional one is what's called stochastic gradient descent, and it's probably the simplest, and it dates back to the 1950s. So the way you would specify that is during the compile phase, where you would specify model.compile, where you specify the loss and also an optimizer. So for the stochastic gradient descent, we would specify the SGD constructor. There's another very important optimizer called ADAM, or adaptive moment estimation. This is probably one of the most efficient, and it's probably the best place to start. That's the one that I use most of the time in my initial model, and then try others as needed. And to specify that optimizer, I would just in the optimizer parameter, I would put in ADAM, as you can see there in the second example. There are a number of other optimizers as well, like eta delta, RMS prop, and so on. You can experiment with each of these to determine which one works best for you and your data set. And each of these also includes some tuning parameters, such as learning rate and others, and you can tune those to improve performance. So in general, it's best to start out with a simple optimizer, and ADAM is a good place to start. That one generally works quite well. It's one of the more efficient. And from there, you can tune further. Now that we have a trained model, and the model here looks fairly good, it seems to have trained quite well, we can make some predictions. And to make the predictions, we're going to use the model.predicts method. And we supply it a set of input data. And this predicts an entire set of data. It doesn't necessarily predict just a single value. You can give it a set of values. And in this case, we've given it the set of all X test values. And I believe there were about 100 of them. And we can specify a batch size, and we'll specify just a batch size of 1 in this case. It doesn't really matter because this is a relatively simple model that predicts very quickly. And you can see it takes no time to make the prediction. In general, prediction takes less time than training because we have to only go through the data set once. So now let's make a plot. Let's plot out the X test values and the Y predictions that were produced by the model. And we'll put in some labels and so on. So let's look at it. And so the red is the test data itself, what we expect, the Y test value, that's what we expect. And the predictions are in blue. And just visually looking at it, it's quite close. It looks very good. It seems to have predicted quite well. So, of course, if we were to adjust the parameters, we can visualize how well this works. Maybe we can reduce the number of units to see do we need as many. But you can see in this case, prediction is relatively straightforward and not difficult to perform once we have a trained model. Once we've trained the model and we've evaluated it, made predictions, and we're happy with the model, we probably want to use it in production. And to do that, we don't want to have to retrain the model every time. So what we can do is we can take a trained model and save both the structure and the weights and biases. This avoids retraining so that we can restore the model later when we want to make predictions with it. And this is relatively easy to do with the Keras API. So here, there are two steps. What I want to do is save the model structure, meaning the layers, the type of activations, and so on. And I call this method on the model toJSON. So that'll give me an object which is the structure of the model. And I can just save that to a file using the JSON file write method. And that'll save the model structure. Similarly, if I want to save the weights for the model has a method called saveWeights. And it's going to save that in h.5 format. So let me run that method, or run that cell with both those functions there. And it doesn't take long at all. And if I go over here, let's take a look and see the files. And you see it has created both the model.json and weights files. And if you want, you can look at the model.json file, it's JSON, and then look at the structure and see how it's organized. So later, let's say that we've saved those files. We can copy them to a different machine if we like. And we want to restore the trained model and make some predictions. So what I'm going to do is first restore the structure of the model using this JSON file.read method. That's going to give me the loaded model. And then I'm going to, I'm going to open the file, and then I'm going to read it using model from JSON, right? The loaded model. And then I'm going to load the weights using the loadsWeight method on the restored model. And there I'm going to give it the weights.h5 file. So I execute that, it reads them back, and so now I have a restored model object, which is just like the model that we trained before, just that we just read it from a file. And now that we have those values, that restored model, we can make predictions. So I'm going to make predictions using that model, and in this case I'm going to use the restored model rather than the original model that we trained, and we're going to predict using the test values and see what it looks like. And you can see it looks exactly the same as before. So the model is restored. We've evaluated or made predictions using the test data set, and it works just as it did after it was trained. So you can see it's very easy to save and restore models with Keras, which is very convenient, not hard to do. It's a set of just boilerplate code that you can add to any set of code whenever you train a model. let's review what you've learned in this section. You learned the basics of the TensorFlow API, and as you can imagine, there's a lot more to it, and we're going to learn more about it as we go throughout this course. You've also learned how to build deep learning models and why deep learning models are powerful. You've learned a number of different activation functions and when to use each one. You also learned about loss functions and when to use different types of loss functions. And you also looked at a number of different optimizers and which ones to choose and how to experiment with each one of them. Most importantly, we built a simple deep learning model that learned a mathematical function. And while that doesn't seem all that interesting, it's a great place to start because you can experiment with a simple idea. The problem we solved in this section seems relatively straightforward. All we did was learn a mathematical function. And the purpose was really to learn TensorFlow and a number of optimizers, loss functions, and other details like that. But it turns out everything we've learned in this section can be applied to solve a real-world problem. And I'm going to show you a practical problem, a real-world problem that has been solved today using the same ideas that we used in this section. And this problem is what's called the three-body problem. It's been around for a very long time. And the goal is to predict the path or the position of large gravitational bodies in space, let's say different planets. And the two-body problem, when you have just, say, a planet and its moon or two different planets and how they interact, it can be solved relatively easily, or it's not as difficult. But the three-body problem is very complex. And if you look at this animation here, you can see all the different things that can go on and how different planets can orbit each other and move around. There are a number of details here in this article, and it tells you more about it in this section. And the math can get very complex. So there are numerical approximations you can make, and they're not the most accurate, and they're very time-consuming. So a group has used neural networks to solve this problem many, many times faster. And they trained a neural network model in this much the same way that we trained our model in this section. And apparently it does solve it many times faster. I'm going to provide a link to both of these articles in the resources section so you can learn more about it. Historically, computer vision has been one of the most challenging problems. Even though humans and animals are very good at detecting objects in a scene, it turned out computers were not very good at this at all. Many of the models and algorithms that researchers had developed over the years were very inaccurate, maybe 75% accurate, which was really unacceptable. This is a problem that we do very easily, even children do it without any difficulty at all. So it was quite surprising why computers just couldn't solve this problem. That changed in 2012 when Jeff Hinton's group synthesized a number of different ideas and developed what are called deep learning techniques. They used graphic processing units to train what are called convolutional neural networks, which were similar in structure to what the human brain does. And their model increased accuracy by 10 percentage points above all other models that were developed prior to that. That doesn't seem like a lot, but it was much more than anything anyone else had done up to that point. Soon after, other people improved on these ideas, and now we have computer vision models that can identify human faces, objects, or just about anything in a scene with very high accuracy. In many cases, they can meet or exceed individual human-level accuracy, which is really, really impressive. It turns out these deep learning techniques can be applied to a number of other problems, such as text, audio, and structured data. So these advances in 2012 were very significant in many areas, not just computer vision. So we're going to look at the MNIST image classification task, and this is often called the hello world of deep learning. The MNIST, or modified NIST, which stands for National Institute of Standards and Technology, the MNIST dataset contains 70,000 handwritten digits along with training labels. So you can see some examples here on the right. Typically, 60,000 of these samples are used for training, and the rest of the 10,000 are used to test model accuracy. And this dataset was developed by Jan LeCun, And it was used to test many different models over the years to see which ones were the most accurate. This problem is known as a supervised image classification task. A machine learning model is supposed to classify any of these images into one of 10 classes or categories. And those 10 categories or classes represent the digits 0 through 9, as you see on the right. So this is a great place to get started with machine learning and deep learning, and we'll learn quite a bit about convolutional neural networks, the training process, the testing process, how to improve models. It's a great place to start. Let's go through some data analysis with this MNIST dataset. So I'm going to do this through Google Colab. So I could just go to Google and I'll type Google Colab here. That's probably the easiest way to get to it. And I'll click on this link here. And that takes me to Google Collaboratory, and it gives us this opening page. So the way I'm going to get started is I'm going to open an existing notebook. And I'm going to open this notebook. I'm going to click open, and I'm going to select GitHub because we're going to use an existing notebook that I already have in my GitHub repository. And I'm going to paste that in here, and I'll provide that link in the resources section so you can get to it easily. And there are a number of examples here. Notice I'm in the machine learning repository there in my repo there. And I'm going to select MNIST CNN training. That's the one I'm going to select. It's going to open up this notebook here, right? It has a description of the network model. We'll talk more about that in the next section, but let's go through just a few sections here, and same thing, all these libraries, we'll go through that in a later section. So we'll run that, and it says that, gives us a warning that it wasn't authorized by Google and it came from GitHub, and that's okay. We know it's a safe notebook to run. All right, and we happen to have some hyperparameters that we're going to use and some other values. The size of the image, it happens to be 28 by 28. All the images in the MNIST dataset are 28 by 28. There are some other parameters we'll talk about later, which has to do with training and accuracy. And notice here the number of classes, because there are 10 digits. We'll use that later when we train the model. So the nice thing about Keras, the Keras library, and we'll learn more about this later, is that it has already a built-in data set, the MNIST data set. Since it's so widely used and it's considered the hello world as mentioned, it has it already built in. So we just need to call this MNIST load function, and it's going to load in a training data set, the training labels, the test data set, and the test labels. Let's go ahead and run that. All right. And down here, we're printing out that there are 60,000 training examples and 10,000 test samples. All right. And we can look at a few of these examples. What I have here is a random number. I'm going to generate a random number between 0 and 1,000. I could have gone to 10,000. It doesn't really matter. And what I'm going to do is just look at the original test samples randomly, and I'm going to use the grayscale because these are all grayscale images. I'm going to show that as an image and also print out the title as the label of the image, and the label is going to be used for training, and that's in the Y test vector. All right, so let me run that, and you notice it brings up a random image, and this happens to be the label 1. This happens to be the label 6, and it looks like a 6, and you can see many different people have written these digits, so they all have different handwriting. This is just choosing random values, so we get an idea of what these images look like. Right? We get an idea of what these images look like. So for the next step, let me just choose a particular image. Let me just pick, I don't know, the 1, right, which I think is the second image, right? And this has a label of 2, and it looks like a 2, a handwritten 2. But so let's explore how the data is actually represented. So to do that, what I'm going to do is add another cell here, and I'm going to do a couple of things. So the orig test is a vector, or it's a tensor, and if I use the NumPy method shape, it tells me that there are 10,000 values there, and they're each of 28 by 28. And we'll get back into NumPy and learn a little bit more about it in the foundation section for NumPy. So this gives us the number of samples and the shape for each sample. All right, and let's then just look at the first sample. So this is the image for the first sample, or like say the sample number 1, which is really actually the second sample. Let's look at the raw data and see what it looks like. So if I run that cell, you notice it has a whole bunch of numbers in it. It's a two-dimensional array, as you'd expect. It's a two-dimensional image. And back here, these are all black pixels, right? So they have a value of 0. They have a value of 0. And when we get down to, I don't know, the third row or so, we start to see some value somewhere in the middle, right? And that's what you start to see. So notice the number is 116. You know that a completely white pixel is a value of 255. So this is maybe half white or maybe around gray. So that's about 116, 125, and it starts to get a little brighter. And then finally we get to 255, which is full saturation. And you can see those are those pixels right there, right? The value is 255, right? And then it drops off again, and then it goes to black, right? So each row here is one line of this image, right? One line, and each value is one pixel value, a single pixel value, all right? So the entire size of this image is 28 by 28, so there are 784 values in total, right? 784 values in total, and these happen to be 8-bit integers because that's all we need to represent an 8-bit pixel, 0 to 255. All right, so that gives us a little bit of an idea of what the data set looks like. And of course, there's both a train and test data set. Let's also look at the y-test. All right, so let me do this. Let me say y-test. Let's look at the shape of that one. All right, that gives us the dimensions of the y-test. And it's a single vector of size 10,000. Because we have 10,000 samples, there are 10,000 labels. All right, so what I'm going to do is if I look at the value for the index at 1, which is this sample we're looking at right here, you notice it has a value 2. We knew that, right? That's the label for this one. So let me look at one. If I look at all of them, there's a lot of them, there's 10,000, but I'll just see a subset. You see it's an array, right? And the first one is 7, the second one is 2, the third one is 1, and so on, right? They're all random digits, a wide variety of these digits, and these are the labels. And we're going to use those labels for training, for supervised training. All right, so that gives us an idea of what the data set looks like, and we'll use that to develop our model and train our model. You'll find that there are many different models that exist for image recognition. And they've been developed over a number of years, and they've been tested for this dataset, particularly the MNIST dataset. And these include models like the k-means clustering, support vector machines, boosted stumps, neural networks. And there are papers that have been published describing each of these algorithms and how accurate they are. And I'll provide a link in the resources section so you can look at find references to each of these and learn more about them if you want to know how they actually worked and what their accuracy is. But it turns out, after all this research, that deep learning models generally outperform all other models. And the reason is that they tend to learn abstract features that are necessary for complex tasks like computer vision. And even among deep learning models, there are many different types. There are dense models, convolutional neural network models, recurrent networks, and so on. And they each solve different classes of problems, different kinds of problems. In general, deep learning models, they have several layers. They have an input layer, they may have one or more hidden layers, and also an output layer. If you see the diagram on the right, the input layer takes, let's say, the input pixels from our image, and then the output layer has a number of neurons that represent the number of classes. In our case, there would be 10 classes representing each of the digits 0 through 9. During training, the neural network will learn weights and biases, and these are values that represent the how the network operates. And so that's learned during, they're initially set to random values, but they're learned using a backpropagation algorithm. So knowing that there are deep learning models are better than all others, and there are a number of models, even for deep learning models, well, which one is best? And it turns out that convolutional neural networks, or CNNs, are the best models for the vision problem specifically. They outperform all others, and that's just based on research. And some of it was inspired by the visual cortex of animal brains, because people thought, well, if animal brains work really well or human brains work really well, maybe we should use that similar structure. And the way it works is it has a number of layers, and there are different types of layers. There are convolutional layers, which combine a section of the image into one pixel. And then there are other layers like pooling layers that group these layers together, and they're put in series to get the best model. And it turns out that this is an empirical process. There isn't an exact answer for what the best model is for any given problem. And over the years, people have just tried different structures, different convolutional layers, pooling layers, and so on, and come up with the best models. And it turns out some of the best models that are available in production, like the Google's Inception v3 and so on, are available for anyone to use, and you can use those models for image detection problems in general. So why does this work well? Well, it works because the early layers in a convolutional neural network learn simple features. They learn things like lines and edges, as you see in this diagram over here, in the early layers in the lower levels, right? And in higher levels, what's interesting is it begins to learn more complex features, like, let's say, features of a face, like the eyes, nose, and ears, and so on. And even higher level layers, in the later layers, it'll learn entire faces and then be able to classify perhaps what a person is or what an object is. So we'll use convolutional neural networks in our example. Let's continue with our example, and now we're going to talk about data preparation. This is an important step in any kind of model development, because it turns out the raw data that we have usually requires some amount of preparation. Not a lot, but some amount. We'll see what that is in this case for the MNIST image data set. So as before, we've already loaded our libraries, and we've set some image parameters and hyperparameters, the image rows and columns, the size, and so on. So right here in this cell, this is the part where we're going to load the data. And as we've seen before, there are images of 28 by 28 in size, and each pixel value is between 0 and 255, each representing a grayscale value. I've saved the original data, this X test and this orig test, because we're going to use that for display later. That's its only purpose. Since we're using the Keras library and it supports convolutional neural networks can be used with either grayscale images or RGB or color images with multiple channels, and that's what this is meant here. It says channels. All right, channels represent, say, the number of colors. In our case, we happen to have only one color, or grayscale. Right, so we have only one channel. But it is necessary to know how the data is represented, whether the channels are represented first or they're represented last. And this happens to be a specific Keras detail. There's a method which will determine whether the channel should be first or last. And all we're going to do is restructure the data, or reshape it, reform it, so that it is in the right structure. Okay. So in the case of if the channels are first, we will reshape the data. The training data, we will reshape it to the number of samples, which is the first shape, the first index of the shape, which is, in the case of the training samples, there's 60,000 of them, and the channel number of channels. And here, in this case, we have only one channel because this is grayscale, so that comes first. Then the number of rows, and then the number of columns. We'll do the same thing for the test data set. We will reshape it. All right, and this reshaping we'll learn more about when we, in the section on NumPy, the foundation section on NumPy, right? And the input shape for each of the samples is going to be 1, meaning one channel, the number of rows, and the number of columns. One channel, 28 pixels, a number of rows, and 28 pixels for the number of columns. If it happens that the channels the Keras was configured with channels last, we'll do something a little bit different. We'll reshape the data using the number of samples first, the number of image rows, and then the number of image columns. And notice the number of channels is last. This is just a convention. Some models prefer channels first, some models prefer channels last. So that's just a convention, and there isn't really a standard on which way to go. So the best way to do it is just to ask Keras, well, which format does it want, and just reshape our data into that format. So there's one other step we need to do. It turns out that deep learning models work best when all of their input values are in the range of 0 to 1. And as we saw before, our pixel values range from 0 to 255. That's because they're grayscale values. So in order to scale those all to between 0 and 1, we will divide the xtrain and xtest values by the number 255. And we'll divide that as a floating point number so that the output we get is also a floating point number that ranges between 0 and 1. And that's really all of the data preparation we need to do. And in most image recognition problems, this is typically what happens. We'll reshape it into the right format, and then we'll scale it into values between 0 and 1. So convolutional neural networks have several different types of layers, and there's a lot to learn with convolutional neural networks. We could spend an entire course just learning about just these type of networks. So we're just going to focus on just the basics in this section. So first we have what's called a convolutional layer. And what a convolutional layer does is it multiplies an input image by a number of small images, what are often called kernels or filters. And the purpose is to find features over an entire image. So if we look at this picture over here, I have an input image. It's been redrawn in in 3 dimensions here. And inside I have what's called a kernel that we're going to multiply by all corresponding pixels. And a kernel might look something like this. So here are a couple of different ones, and they're relatively small, let's say 3 by 3 pixels in size. This kernel on the left is going to perhaps identify horizontal lines, and this kernel might find vertical lines. And there may be many of these filters or kernels that identify many different kinds of features. Next, we have what are called pooling layers. And what a pooling layer does is it chooses the maximum or the average of a set of pixels. And the idea is that it might choose the most important features within an image. So in this example, we might have a pooling layer of 2 by 2, and what it will do is select the maximum value in these 4 pixels here. So if we have pixel values 1, 2, 3, and 4, the maximum value is going to be 4. Similarly, if we have pixel values 5, 6, 7, 8, the maximum value will be 8, and so on. Next, we might have a fully connected layer or a dense layer, and that's often used at the output layer to classify an image into one of several classes. So each of these layers have parameters, or what are called hyperparameters. And these are parameters that we will define when creating the model. And these are defined and determined empirically. And we'll look at some more examples, we'll look at more in the examples on how these are determined. There's no hard and fast rule for some of these. They're just sort of some guidelines on what work best. So for convolutional layers, the hyperparameters include, say, the number of filters. Here we've just shown 2 filters, but you can imagine there could be many, many more. There could also be the kernel size, which is the size of each of these filters. And in this case, the filter size is 3 by 3. There's also what's called the padding and strides. And the padding has to do with what do we do at the end, when we get to the end of an image, because the image may not be exactly the same as a multiple of the padding of the kernel size. There's also what are called the strides. Each will take these kernels and step them across this image, and we can step it 1 pixel at a time, or 2 pixels, or more. And during training, the model is going to learn the values or the weights for each of these filters. So here I've just put in the values 1, 1, 1, but the model could actually learn different values. Next, there's the pooling layer, and in the pooling layer, we just define the pool size. And there are no weights that are learned here. We just define the pool size, and here we've defined a pool size of 2. So notice that we have an image that's 4 by 4, and it's once we apply a pooling layer, it's going to turn into an image of 2 by 2. And finally, for the fully connected layer or the dense layer, we'll specify the number of units or neurons. And specifically, the output layer will have the number of output classes. So here we happen to have only shown 2, but in our example where we're recognizing handwritten digits, there are going to be 10 output neurons. And as mentioned, we'll learn more about the details when we look at the example. Now let's look at the definition of the model for this convolutional neural network that we're going to use. This is the model defined here in this cell, and it has multiple layers. It has 2 convolutional layers, a max pooling layer, a dense layer, and a one-hot encoded output layer. So this model can achieve over 99% accuracy, even with a small training set. And this is the way it looks like using the Keras API. And we'll learn more about the Keras API in the foundation section on Keras, but this gives you a rough idea of what it looks like. So the model is defined as what's called a sequential, and sequential is a class in Keras where we can add more layers to it. So here we're adding multiple layers. The first layer we'll add is a convolutional 2D layer. This is the definition of a convolutional layer. And if we look at the Keras, and it has a number of parameters like the number of filters, the kernel size, activation function, and input shape. And I'll just briefly show you over here in the Keras API what these mean. So the first argument is the filters. It's the dimensionality of the output space, or the number of output filters, and so on. It gets into some more detail there. So we have 32 output filters. And this activation function, you notice a number of these layers have what's called a rectified linear unit or a ReLU activation function, which is commonly used in intermediate layers for neural networks, for deep neural networks. So after the first convolutional, we have one more convolutional layer with 64 filters and a kernel size of 3 by 3. And then we have a max pooling layer and a dropout layer, and the dropout layer helps with regularization to avoid overfitting. Then there's a flatten layer, a dense layer, another dropout layer, and a final dense layer. And this final dense layer has an output space of 10 values, or the num classes. And the num classes, as we defined up here in our parameters, is the number 10. So that's the number of outputs we want. And there are 10 digits, so we want 10 outputs. So this is our output classification layer. And notice this one has an activation of softmax. And you'll often see that one-hot encoded output layers have a softmax activation. And softmax means that all the output probabilities will add to 100%. So when this model makes a prediction, it will predict all the output to be a total of all possible 100%, and one of them will be most likely, and we will choose the most likely output as the prediction for our digit. And finally, we'll print out the summary of the model, which is always nice because you can review the parameters of the model. So here's the model summary, and it has the output shape for each layer, and it also has the number of parameters for each layer. And notice the first layer has just 320, the first convolutional layer. Then the second one has 18,000 or more. Then the dense layer has many, many parameters, over 1 million parameters. And this is not uncommon with dense layers because basically every input neuron is connected to every output neuron, so the number of combinations is very large. Then there is a final dense layer, which goes to just 10 output neurons, one for each output class, right? And you can see the shape of each layer. And then down here are the number of parameters, or the trainable parameters. So there are over 1 million parameters that will be trained in this model. And that's what the model is going to learn during the training process. Now that we've defined the model, let's go ahead and train it. And we're going to do that in this cell over here. So there are a number of different steps to training the model. First thing we have to do is compile it. And we're going to compile it with a specific type of loss. And the loss measures how the model determines whether it's right or wrong. And the loss we're going to use is what's called the sparse categorical cross entropy. And this is a useful loss function when we have categorical outputs, meaning we have 1 of 10 output in the output layer, 1 of 10 outputs. And we're going to use the atom optimizer. And there are many different types of loss functions we can use and different types of optimizers. And as mentioned before, we'll go over some of that when we look at the Keras API in detail. We can also capture some metrics or some measurements as the model is being trained. And here we're going to capture the accuracy, or the ACC, or that's for accuracy. And then this model.fit, we're going to specify the train samples, the X train or the images for training, the output labels, the Y train, the batch size, which is just a parameter for how we want to train it, the number of epochs, or how many times we're going to cycle through the data, and how much detail it's going to get printed out when it goes through training, and then the validation test, the validation set, the images for testing the accuracy of the model, and the labels, output labels. And during training, Keras is going to evaluate the model against the test data to measure how well it's doing. And once it's trained, we'll evaluate the model given the train and test set, and we'll print out the loss and the accuracy of the model. And then we'll also plot out the accuracy as a nice graph using Matplotlib. And we'll learn more about Matplotlib in a later section. So let me go ahead and start the training. And if you notice over here, it says it's going to take 2 minutes or more than 2 minutes just for one epoch. So that's taken quite a while. And the reason is that we are not using a GPU here for the runtime. So let me stop that. And let me change my runtime. Let me change the runtime type. And I'm going to change it to use a different hardware accelerator. I'm going to use a GPU accelerator. And I'm going to save that. Okay, it's initializing and then it's connected. So now what I have to do is go back and I'll have to rerun all these cells because we started with a new runtime. All right, I'll just run through these cells again. Now, if I was smart, I would have set the runtime initially, and that's a nice thing to do when you first start out so that you don't have to rerun the cells later. All right, then I'll define the model. All right. And then let's go ahead with the training again. And let's see if it improves. Oops, I forgot to click this cell. I thought I missed it. There we go. All right. So let's train it this time a little bit better. We get some warnings from TensorFlow, and let's see if it is any faster this time. And so you notice now it's training much faster with GPU acceleration. So if you notice that your training is taking a long time, then you want to check if you're using hardware accelerator or not. So it's going to go through 5 epochs. So it went through the first epoch, and that took 16 seconds. And then it gets a little bit faster after that. And you notice over here, it's printing out the validation loss and the validation accuracy. And even at the first epoch, the accuracy is surprisingly good. And that shows you the power of convolutional neural networks. We don't really need to go through many epochs or cycle through the data many times to get really good accuracy. All right, and we're going through the 5th epoch, and there it is. So it plots out the model accuracy. And the ultimate accuracy, we got over 99%, 99.05% given the test data. And probably we could have improved that accuracy even more if we were to use a larger number of epochs or play with some of the other model parameters. And you'll notice also here there's a little bit of variation, that the test, this is the test over here, the test data, and it's a little bit higher than the training accuracy. And this is what's called variation. So that variation is something we need to improve, and we can improve that by tuning the model slightly, and we'll look at that in a later section. So you see, it didn't take a lot of time to train, and we are able to get surprisingly good accuracy out of this relatively simple model. Now that we've trained the model, let's make some predictions. So in this cell right here, I can call the model.predict function, and I'm going to supply the test images. And the model predict, it does a batch prediction. You give it all the predictions we want. In this case, we want to supply all 10,000 test images. We could have taken a subset if we like, but as you'll see, it runs quite quickly. Right? And you'll notice that prediction is much faster than training because it only has to make one forward pass through the network. Then what we're going to do is take the maximum likely value for each prediction. And we can do that using this argmax method as part of the NumPy library, NumPy API. All right? And so we're going to take the argmax and take the most likely value, the first most likely value. And in this cell here, what we're going to do is pick a random image from one of the 10,000 test images, just a random one, and we're going to print out the most likely prediction value from the prediction, and also the label, the expected label for that image, and hopefully it's correct. And we'll also show the image to take a look at what it looks like. So let's run that. And in the first one, it predicted this was a 7, and the label is a 7, and it looks like a 7, so it definitely got that one correct. Here's another one, it predicted a 6, and the label is a 6. That also looks correct. Label 3, that's a pretty easy one. And a label 9. So it's getting them pretty accurate. We don't see many mistakes here. Even that one, even though it's not a great 2 there, it predicts that quite well. All right. Label 5, it predicted, even that one is a little bit peculiar, but it predicted it correctly. So it's doing a pretty good job. And it's going to, because this model is really accurate. It's over 99% accurate. So it's we'd have to go through maybe 100 samples before we find one where it's incorrect. Now let's do some error analysis. And error analysis is an important step in evaluating model performance, because we want to find out when a model makes a mistake, why is it making a mistake? And try and identify the kinds of data that cause the mistake. And maybe we can either use more training data or improve the model. Just gives us a better understanding of why things are going wrong. So what I'm going to do in this cell over here, and we'll look at the model predictions that specifically do not match the known labels. So we're going through a number of 10,000, one of the 10,000 test samples, randomly choosing one of them, and just determining if the most likely output does not match the label. And if it does, we're going to show the image and show the predicted value and the label that goes along with the image. So let's take a look. So here's an example. The model predicted this as a 7, but the label is actually a 2. And you can see that even a human could possibly make this mistake, because it kind of looks like a 7. It's just got a little bit of a tail here. So someone maybe wrote this very quickly, and so it looks a little closer to a 7 than a 2. And if we look at the predicted values, you can see the model predicts with very high accuracy, or very high confidence, I should say, that it is a 7, but it suggests that it's possibly a 2 as well. So it maybe thinks it could be a 2. Let's look at another one. Here's one. The model thinks this is a 5, but the label is a 9. And yeah, it's probably because it's lightly written. And if we look at the predicted value, it says it could be many different values. It says most likely it's a 5. The next most likely is that it's a 9. And maybe it's also due to the fact that it's kind of slanted this way. So maybe what we need is more training data that has slanted numbers, right? That might help. Right? But it also thinks it could be an 8 or it could be a 3. And I think maybe the slanting is probably what's causing trouble. look at this one. The model predicts this is a 5, but the label is a 6. And again, it's probably because it's kind of slanted and kind of drawn in a weird way. And in this case, the model is very confident that this is a 5, and it doesn't really have many other choices. It thinks maybe it's a 3. So I think most of our training examples are written kind of vertically without a lot of slant to them. And that may be what's causing the model to not do very well. Let's look at one last one. So this one, the model says it's a 9, but the label is actually a 4. And you can see it's kind of a big blob. So maybe the model just gets kind of confused because the center, it does have a center to it. And also look at it. I mean, even a human could make this mistake because this is a 9 or a 4 because it has this cross over the top, which a 4 shouldn't have. But the model does think it possibly could be a 4. So some of them, even a human could make these mistakes. So looking at all these error examples or this error analysis, we can determine that a lot of it is caused maybe because we don't have a lot of training data where there are slanted examples, and there are some examples which are just perhaps even a human would make a mistake, so the training data is not very good at all, or the test data itself is not very good at all. So there are many factors that could contribute to this. So once we identify some of the ways to improve it, what we want to do is, in this case, let's say introduce more training data, or maybe even try and improve the model in some other way, maybe the model structure, or use a more sophisticated model. But as you can see, the data has a big impact on the accuracy of the model. Hyperparameter tuning is an important step in improving overall model accuracy. And there are two important criteria that contribute to overall accuracy. One is called bias, and the other one is called variance. And a high-quality model should have low bias and low variance. A model with high bias exhibits a low predictive power and makes a lot of mistakes. So if we look over here at this model on the right, the first graph that we have, which plots accuracy as the number of epochs, we see that the accuracy with the training data is increasing, but it peaks out at a certain point, and it never gets to 100%. This is what's called bias. So the difference between the maximum or the 100% accuracy and the best accuracy we can do with the training data, that's what's called bias. And that is a measure of the overall predictive power of a model. Similarly, a model with high variance is probably overfitting and tends to memorize the training data. It predicts well with training data, but doesn't predict well with test data. So if we look again at this same graph, you see that this model is doing quite well with the training data, but it does poorly with the test data. So this is what's called variance. So the model is not generalizing well, and it's really just memorizing the training data set. Whereas a high quality model down here, it has low bias and low variance. Though in this case, it's possible that this model might have slightly higher bias than the first model with high variance, but really what we're looking for is both the combination of the two, low bias and low variance. So first, when improving a model, we want to reduce bias, and that's going to improve overall predictive power. And there are a number of factors that contribute to high bias. CNN, that could be due to just the model structure, just the number of layers or the types of layers we're using. Model hyperparameters, such as the kernel size, number of filters, pooling size, any number of hyperparameters. And of course, the amount of training data we have, or the distribution of the training data, also influences how well the model can train and its predictive power. So it's best to first start with a model that is known to work well with a similar problem. That's because developing a model from scratch is challenging at best, and it's best to build on the work of others. Many people have developed models that work well with different types of data sets, so it's best to find a model that is close to your problem and build on that. And once you have a model that works well with similar data, you can take that model and carefully adjust hyperparameters one at a time to reduce bias. And you can do this manually, or you can do this with an automated script. to find the best set of hyperparameters. Once we've reduced bias, we want to reduce the variance in a model. And reducing the variance improves the ability of a model to generalize with test data or real-world data. And the way we do that is with what's called regularization. And regularization is the method of reducing variance. And there are a number of different regularization methods that exist. One of them that works well and is relatively simple is what's called dropout regularization. It's very simple and effective. Dropout reduces overfitting by removing some percentage of neurons in the model. And the amount of dropout is another hyperparameter that we can tune to improve the quality of the model. And we'll see how dropout works in the next example. Let's experiment with some hyperparameters and some hyperparameter tuning to try and improve the quality of our model. So to do this, first, what I'm going to do is I'm going to go back to our section where we've defined some of the parameters, configuration parameters, and I'm going to increase the number of epochs to 20. That's a hyperparameter, the amount of training that we're going to do. And I'm going to also change the dropout to 0. And as we saw, dropout is a regularization technique. So let me run that cell, and I'm going to go down here, and I'm going to also redefine the model. And whenever you change hyperparameters or change any structure of the model, it's important to recreate an instance of the model. And that's just the nature of Keras. You can definitely run into problems sometimes if you don't do that. So then now let's train the model. And in this case, I have set this to a GPU instance as the runtime, so it will train a little more quickly than if I did not use GPU acceleration. So let's see how this turns out in terms of accuracy. We want to look at both the accuracy and the variance, actually. All right, we're nearing the end here. And you can see that the model is doing quite well. The accuracy is definitely increasing, and it's surprisingly good, 99.91% accurate. That's really quite impressive. So here we are near the final epoch, and then we'll look at the graph. And so you look at the final accuracy, of the training accuracy is really high. I mean, it's way up there, 99.92. So it's done really, really well. But you look at the test accuracy, it's not as good. There's quite a bit of variation. So there's very little bias. So that suggests the model is of very high quality. It has a lot of predictive power, but there's a lot of variation here. And even still, the variation isn't super high because you see that the test accuracy is 99%. There's almost a 1% difference between the test and train accuracy. So this is what's called variance. And we want to reduce that variance, right? And the way we do that is using regularization. And in this model, we happen to have included dropout. You see there are some dropout layers right here. Here's one dropout layer, and here's another dropout layer. And those dropout layers take a dropout parameter. And that dropout parameter is a number between 0 and 1, which is like a percentage of how many neurons or the number of neurons we want to remove from the model. And it's removed randomly. So up here, the dropout, we define that to be 0. So we're not dropping out any neurons. So what I'm going to do is I'm going to increase that to 0.5. So that means actually it's going to drop out quite a few neurons, as many as 50% of the neurons. So I'll run that cell. That'll change one of the hyperparameters, and I'll go back and redefine the model. Remember, it's very important to redefine the model whenever I've changed any of the parameters. And then I'm going to train it again, and let's see what happens. So before, you remember we had quite a bit of variation right down here, quite a bit of variation. So remember that. Let's see if we train it again and see if it improves. So that's what training is, a little bit time consuming. So a lot of times people write a script to do this and go through some kind of a search where they'll just change parameters automatically in the script and then just measure the accuracy and choose the best value. Here I'm just doing it manually just to illustrate the point, but you can imagine how this could be automated, so we wouldn't have to sit here and wait for the model to train each time. All right, nearing the end of our second training attempt with a little bit of dropout added. And you can see that the accuracy is probably a little bit lower than it was before, the overall accuracy, right? But hopefully we won't have as much variance, and that's what we're really going after. We want both low bias and low variance. And so if we look at the final result, you see that the test accuracy is definitely better than what it was before. And actually the overall accuracy, the bias, is a little bit higher than it was before, but you notice the variance is very low. The difference between the test and train accuracy is very small. So that's what we want. So that means that this model is not overfitting, it's not memorizing the input data set, and it is considered a very high quality model. So if we give it examples that are outside the test set or the train set, it's going to actually do a good job in terms of prediction. So hyperparameters are many ways we can improve models, and dropout is just one of the many hyperparameters that we can work with. There are several others. So if we go back to the model, there are a number of different parameters. Let's say the kernel size. In this case, we use 3x3 kernels. The max pooling size. So there's a number of different parameters we could play with and try to see how that works. The number of filters and so on. Even the activation functions are ones that we can play with as well, right? So this gives you an example of some of the hyperparameters and the process of hyperparameter tuning. And the ultimate goal being is we want to get the best model we can with the lowest variance between test and train. Let's go over a few common questions. There are many, many questions I'm sure that you might have, so I'm just going to go over a few here. So one of the things that people often ask is, how many layers should a deep neural network have, or let's say in the case of image recognition, how many layers do you need? And it turns out that's not an easy question to answer. There's no hard and fast rule. It really depends on the data you have and the number of output classes that you might have. In some cases, let's say the state-of-the-art models, let's say like Google's Inception v3 or so on, they may have 100 layers or more. And you can imagine that training this kind of large model is very time-consuming. They use very large machines to do that. And they tend to overfit because they have so many layers, so it requires quite a bit of tuning. So to get these to work well, it's definitely a lot of work. So in many cases, people prefer to use pre-trained models for some of these big image classification problems. Another common question is, how much training data is required? And again, this depends, and it really depends a lot on your data. So let's think about a simple case of binary classification. Let's say I just had 2 digits, or I just wanted to distinguish between a cat and a dog, or a good and bad, or something like that, just binary classification. And that's a fairly common problem. It turns out that you don't really need a lot of training data in that case. That's simply because even with a random choice, a model will be 50% accurate. So achieving higher accuracy than that doesn't really require a lot of data. Even a few hundred samples can get you to 90% or better. So imagine a more complex problem like 1,000 different classes. Let's say we're trying to identify different animals or different plant species. That's obviously going to require much, much more training data, because we're going to need many examples for each class that we have. So if we had 1,000 different classes, at the minimum, you might want 100 or 1,000 or maybe even 10,000 examples for each image class. So you can imagine that the numbers get very large very quickly. So there's one classic example where someone was trying to classify between just dogs and wolves, and it turned out that the model was really just detecting whether the background had snow in it, and it's because wolves are often found in colder climates where there's a lot of snow. So you definitely need a lot of variance in your training data and to make sure that you are covering all the different kinds of cases that you might have. So the best way to answer a lot of these questions is to just try things out on your own and try it out on your own data set or on your own kind of problem, because every data set is different and it's really hard to tell in general what the best model will be, what the best number of layers or the right amount of data. You really have to do a lot of experimentation. And that's also the best way to learn more about machine learning and deep learning. And of course, I'm always here to help. So if you have any questions at all, just feel free to post a question or send me a private message if you prefer, and I'll get back to you as soon as possible. It's a very interesting subject, and I'm always very happy to answer these kinds of questions. Let's look at the foundation section on pandas. So what exactly is pandas? Well, it's a popular Python library for analyzing and transforming structured data. A lot of data that you'll find may have some tabular structure similar to an Excel spreadsheet, and pandas works really well with data that's structured that way. It's another open source library, and it integrates with Matplotlib, which is very convenient. And it has a flexible data structure called a data frame, and it's kind of like a spreadsheet with Python functions. It can read and write many types of data formats such as CSV or even Excel files or some database formats as well. So why would we want to use it? Well, partly because of the data frame object. It's easy to use, it's fast and efficient for data manipulation. You can handle inconsistent data very well. A lot of times when you find data, you'll find that it's messy. It's not well formed. There may be missing data and you may want to correct that. Pandas has really quick and efficient ways to do that without writing lots of code. Pandas can also select and query data frames. You can select rows, columns, or filter rows based on sophisticated queries. You can also perform aggregations and plotting. You can group rows together and generate high-quality plots with just a few lines of code. In a way, it's kind of like a spreadsheet and maybe a database all in memory. So it's very powerful and easy to use. And we'll see some examples on how it works. Let's look at how we can load and inspect some data using pandas. So first, let me go to Google. I already have my Google Collaboratory page open. And let me click Open Notebook. And I'm going to go to my GitHub repository as usual and type in my repository name. And as usual, I'll supply that in the resources section. And I'm looking for notebooks. What do I want? Notebooks pandas. That's the one I want. Here it is. Pandas example. And the first thing I want to do is let me clear all the output so we can start from scratch. So this gives us a description of pandas and a link to the pandas homepage if you want more information. And we're going to experiment with the automotive data set from the University of California of Irvine. And I'm also going to show you how you can import data into Google Colab, because that's a common operation that you may want to do. So first thing we're going to do is import pandas, and it's customary to import it as PD. And we're also going to import Matplotlib because we're going to do some visualization later. So we'll import those, and as usual, Colab gives us this warning that it's a notebook not authorized by Google, but that's okay. And we're going to load some data. And there are many ways to load the data. We can load it as a CSV file. We can also load it as from an Excel file if we want. There are many different ways to do that. The data, unfortunately, is not local. It's not actually is loaded here. So if I look in the files, it's not here. So I can use some Unix-like commands within Google Colab to load the data. So first thing I'm going to do is create a directory. And first, let me create an extra cell here. And I can use this command, !mkdir data. All right. And exclamation point means execute a shell command. And I'm going to create this directory called data. So if I execute that, let me go back here to Files, and you see now there's a data directory. It's empty. We need to put some data into it. Now to load the data, I'm going to get it from my GitHub repo. And to get the URL, I've listed it here, but to get the URL, I'll show you how to go about it in case you want to do that with a different data set. So here's my repository. So I'm going to go into Notebooks, and notice the Keras notebook is right here, and under the Notebooks directory, there's a data directory. If I click data, there's the imports 85 data, which is a set of car data. And I don't want to use this URL. If I click on this, it shows me the data, but I don't want to use this URL either, because this is going to be the URL for the web page, which is not what I want. I want the URL for the raw data itself. So I'll click this raw button right here. Right? It displays the data, and this is the URL I want to use. I'll copy that URL, then go over and I'm going to type wget, paste that URL, and -p data. And -p data means the directory I want to store that data, where I want to store it. If I don't put -p data, it's going to put it in the same directory, which is not exactly what we want. So I run that, and it says it's resolving. And there it is. It downloaded the data. It's about 25K of data. And if I go back here and look in Files and I expand data, you see my imports 85 data is right there. So that's a convenient way to import data into Google Colab if you ever need to do that. So now that it's loaded, now that it's inside Google Colab, I can load the data. It turns out this data, as we looked at right here, it doesn't have column names. Notice it is comma separated data. It's a bunch of car data. It doesn't have column names. It's often you'll have data with column names. Sometimes you won't. In this case, we do not have column names. So we're going to have to add the column names. So the way we can do that is list the column names here in a Python list. Right? These are all the column names. I happen to know what those were, so I just entered them here. And then what we're going to do is load the data using pd.readcsv, means read a comma separated values file. I'll give it the path, and notice it's inside the data directory. I'm going to specify the separator as a comma, and I'm going to give it the name of all the columns. This is a list of all the column names, so I'm going to provide all those there. And then I'm going to print out the total number of cars, and I can just get the length of this object that's returned, and the object that's returned is a pandas data frame. Right? So that pandas data frame will have all of the data in it. So if I run that, it says the total number of cars is 205. And if we were to look in this list right here, there are probably 205 rows. So as you can see, that's what we have. Okay? So one of the first things we want to do is just inspect the data, just look at it. And probably the easiest way to do that is using cars.head. I could look at all the data if I just printed out the cars, but let me just type cars.head 5, and that's going to show me the first 5 rows. And you can see there's an index here, 0 through 4, which are 5 rows. It has all the column names up here, and it has values for different columns. Notice some columns don't have any values. Right? And we'll deal with that later. It's fairly wide. There's a lot of data here. You can inspect the kind of data that it has for different make and model of different cars, the horsepower, the peak RPM, the city miles per gallon, and so on. A lot of different data. Notice if I don't use cars.head, I can change this course and select a different number. That'll show me more. Right? Now I have 10 rows. If I don't use head, I'll get all the data, and it's a lot, and it's going to truncate some of it because Pandas is smart. It shows us there are 205 rows and 26 columns, but it truncates some of them so we don't fill up all of our screen. So it's relatively easy to load data, as there are many different ways to load it, and it's easy to inspect the data in Pandas. Now that we've loaded data into a data frame, we can select rows and columns from it using the Pandas API. So here's the data frame I have. cars, and if I want the rows from which is really the second row, 1 through 5, it's starting from the second row. Remember, rows are 0 based. I put 1:5 like that, and that gives me 4, right? Up from 1 to 5, not inclusive, right? So this is typical of the way Python works. It includes the first index, but not the last. Now, one thing to be careful about, if I want to select a single row, I have to put both indices. I have to put the first and the last, even if I want a single row. If I put just a single value like this and run that, I'm going to get an error. So that's not going to work. So if I want just say the second row, I would say 1:2, right? That gives me the second row. Notice if I put 1:1, I'm not going to get any rows at all because it's starting from 1 and not including 1. So that's not going to give me anything. So just remember that if I want to select just one row, I do need to use both indices. So that's how I would select different rows. So if I want to select specific columns, there are a couple of different ways to do that. One way is to specify the column names as a list like this. So what I would do is put in a list of column names, one or more column names like that. And I'm also going to specify, this is also going to return another data frame, just like this one did. A subset of the original data creates a new data frame. This will also give me another data frame, but it'll only include those 2 columns. And then head 5 is going to give me the first 5 of those. So now you notice I have just make and body style and only the first 5 rows. And this is yet again a new data frame that I can manipulate. All right. So one thing I can do with any data frame is I can just inspect it. And if I type cars.columns, it gives me the list of columns. Pretty simple. And I can also describe the data frame, and it gives me some useful statistics for any numerical columns. So it'll look through all the columns, determine which ones are numeric, and give me a count, which is of course the same for all of them, or there are 205 rows, the mean for each column, right? The standard deviation, the minimum, and the distribution, 25%, 50%, 75%, and the maximum, right? So that gives you some useful statistics, right? We can also get the data types for each of the columns. Pandas tries to infer what the data types are. And in a number of them, it says they were float 64. They were a 64-bit floating point number. So it figured that out. The others, it's not sure what they are. They're probably strings, so it just treats them as object. Some of them, it knows that they are purely integers. There's no decimal point, so it treats them as integers. In some cases, the price, let's say, there are some missing values. So even though it's probably a float 64, there are some missing values, so it treats that as an object as well. So there's another way to select columns. And if I select just a single column, I can get what's called a series, because each column in a Pandas data frame is what's called a series. So I can refer to each of these columns by the name of the column like this, cars.make. All right? And if I apply the unique operator, it'll give me the unique values for that column. All right? So it says if I get the unique values for the make column, these are all the unique makes for each car. So if I take out the unique, it's going to give me probably all the combinations of all of them, right? So there's 205 of them, but if I type unique, I'll just get the unique values. So this way of selecting, this is a way of I can select columns using just the name of the column, and that sometimes works, but not always, because you can imagine the name of a column could be a Python keyword or other method name, in which case it's going to conflict. So that's not always preferred to do that. Sometimes you can do it, but not always, depending on the column name. Also, let's say if it has a space in the column name, that's not going to work. So in those cases, you may want to use this other syntax where we use the column name inside of quotes like this. right? So that's how we select columns and rows from a pandas data frame. Now let's look at some ways we can sort and transform data in pandas. So here we have our data frame that we've been working with so far, and the data frame has a method called sort values, and we can specify a column, a single column for example, that we want to sort on, and we can also specify we want ascending or descending. So if I say ascending true, it's going to be ascending, and that's usually the default. Let me put in false in this example, and let's see what happens. And then I can take the first 5 columns of that. First 5 rows, rather. And so I think I have to go to the price column, which is all the way over on the right. And you notice that the price has a question mark here because a lot of these prices were not defined. So even though those appear last, they are not. We don't have those values, and we'll look at how to fix that in a second. So let's say I wanted to sort by multiple columns, and in order to do that, I have to specify a list instead of a single string, and I'll do that like this. I'll put in a list here, and I'll put in 2 columns, and let's say I want to use make and price, like that. So if I do that, it's sorted by make and price descending, or because this ascending is false, and notice Volvo comes first, right? And here we do have some valid values for the price, so that worked out okay. But we've got some missing values, which we'll deal with shortly. So I could select just those make and price columns as we've seen before. I want to select both those columns. Oops, let me fix that. So now I just get the make and the price, just those 2 columns in the first 5. If I change the sort order to true, I get Alfa Romeo. Notice that now it's ascending, the price is increasing, like that. So sorting is pretty straightforward, not very difficult. And so now let's deal with this problem of the numeric types that we're missing with the price column. So we can convert some of these types to first determine which ones are not numeric and eliminate those, and then convert them back to numeric. And as you remember, the data types for each of these columns, in the case of price, it was an object because there were some missing values. It was not a floating point number, right? So what we can do is determine if that column has a numeric value, if a row for a particular column has a numeric value or not, by taking the column, converting it to a string, and using this isNumeric function, and that'll determine if it is numeric. And if it is numeric, we're going to select only the rows that are numeric for those columns from this data frame. So, and there's one other detail. We should, in general, make a copy of this using this copy. Otherwise, we'll get this setting with copy warning, which is something we'd like to avoid. All right, and that'll create a new data frame, and that'll give us a new data frame, which we'll call priced cars. So now that we have the priced cars, we've selected only the ones that have a numeric value for price. We want to convert those back to a floating point number because you remember they were not floating point numbers. So what we do is select priced cars.price, and in this case we can use this syntax just referring to price because it doesn't conflict, the name does not conflict with any kind of reserved keywords or other methods. And then convert it to a floating point number using the asType float method. And then we'll reassign that to the price, right? And so this works because we've created a new data frame. And then we can sort the values by the price, sort it descending, and get the first 5 columns. And let's see what we get. So if we scroll all the way to the right, you see we no longer have those values that had those price values that were missing. Those have been now excluded. And they were all converted to a float, and we can confirm they're convert it to a float by using the D types that we did before. And so you notice this is now a float 64. So now that we have that, we can go back to the describe, and it should give us some statistics for the price column. So if we scroll all over to the right, notice that the count is now less. There are 4 less rows because those price columns, those price values with non-numeric values were eliminated. So there are only 201 rows instead of 205. And we have the mean, so it's about $13,000, which I imagine that's the value they have there. That's the unit, and the standard deviation, and so on. All right, and you notice the max. These are old cars, so there's $45,000 was the max. I guess these are all different years. All right, at least in this data set. So that's how you can sort and transform data with pandas. Pandas can group data together by a column or set of columns and then apply an aggregate function. So the aggregate function could be something like count, min, max, mean, and so on. So let's look at an example. I had my priced cars data frame, and I'm going to group all of the rows by the make. So it's going to take every row that has the same make and then apply an aggregate function to all other columns. So in this case, I'm applying the max function and then just taking the first 5 rows of the resulting data frame. So if I do that, notice all the Alfa Romeo cars are grouped together. And if I look at, for example, the price, this tells me the max price of all Alfa Romeos. And it's the same for all of the other car makes as well. So I've only shown 5 here, but let's say if I show all of them, you'll find that the data set is not very large because it's based on the unique combination of all the different makes, and I think we only had about 16 or so different makes of cars. So it applies aggregate functions to all the columns, including the string columns or object columns, including not just the columns that have numeric values. I can apply other functions as well, like min. That's going to show me the minimum of all the values. So if I scroll to the right and look at the price, this is the minimum price. There's also a mean. So this would be the average price, or the average of each of the columns. So this shows me, say, the average length, average width, and so on. So notice the Mercedes has averages larger than most. Makes sense. Luxury car. So I can also group by multiple columns, and to group by multiple columns, I can supply a list of columns like this, and then apply an aggregate function. So it'll be a combination of both the make and the body style. So in the case of, let's say, the Alfa Romeo, there's both a convertible and a hatchback. So if we look at the price, it turns out the maximum is the same for both. Let's pick mean and see if that's any different. So this is the average for the combination of both the make and the body style. And the next one, we have an Audi sedan and a wagon. And so in that case, the price is a little bit different, right? The average price for an Alfa Romeo convertible is slightly less than an Alfa Romeo hatchback. And similarly for an Audi sedan and a wagon. There are many other aggregate functions that we can apply, and if we look at the Pandas documentation, it lists a number of them here. For example, we can apply any number of these aggregate functions. We've seen max, mean, median, min, but there are many, many others here as well. Sum, standard deviation, cumulative max, cumulative count, and so on. Pandas also integrates with Matplotlib, so you can create many types of plots and visualizations, just like you can with NumPy or other libraries. So let's look at some examples. So we add our priced cars data frame, which is a list of all cars and their valid prices. So we can create a histogram, just use from the data frame. It has a histogram method, and we can group by the price and specify the number of bins. So if we plot that out, so given the price, you notice the number of cars that we have in different price bands, and you can clearly see a number of the cars tend to be lower priced. There are more lower priced cars than there are more expensive cars, which makes sense. So we can also make what's called a cumulative distribution. So this shows us all the cars that are greater than a certain price, the number of cars greater than a certain price or less than a certain price. And this depends on how the value we supply for cumulative. And I believe this shows all cars that are less than a certain price. So this shows the list of cars, and as you might expect, there are more cars at lower prices. So here's another one where we're going to select cars that have a horsepower that is numeric. Some of the data we have doesn't have a numeric value for horsepower, similar to what we had for price. So we'll do the same thing and create a HP priced cars data frame that has valid horsepower for each car. And let's plot a scatter plot this time based on horsepower and city miles per gallon and see what that looks like. So we'll see the relationship between the amount of power a car has and the fuel economy. And as you might guess, there's this inverse relationship that cars with a higher horsepower or larger engines generally get lower mileage, as you might expect. And some of the cars that look at this one way out here that has over 250 horsepower, it's really low. City miles per gallon is really low. And some of the cars that have very small engines, clearly they have very high fuel economy right there. So if we do a similar plot with highway mile per gallon, let's see if there's any difference between the two. A little bit. You can see that even some of the cars with bigger engines that produce more power do have slightly higher highway miles per gallon. So they can be more fuel efficient. So let's do something else. This is an interesting, I can make a couple of subplots. So what I'll do here is I'll group all the cars by make and then select just the price. And then I'm going to calculate the mean and the standard deviation from each of these groups. So I'm applying an aggregate function like we did previously, and I'm going to create these two data frames there. And then I can create a number of subplots. Matplotlib has some wonderful ways to create plots on top of plots for interesting visualizations. So what I'm going to do here is create a subplot with the price and then create an error bar with the standard deviation so we can see the variation in price. So here I've grouped together all the cars by make, and so I have all the different makes of cars down here and their prices up here, and in green I have the average price for each car. And in black, these are error bars. So the error bars show the variation in price for each of these cars. So some of them have very small variation, like the Alfa Romeo, not a lot. They have a very narrow price band, whereas a BMW, it has a very wide price band. There are many cars of different prices. And even though Jaguar, it seems to be quite expensive, but the variation price is quite small. And that could just depend either on the type of car or just the amount of data that we have. But it shows that with just a few lines of code, you can produce some really nice visualizations. So if you want to know more visualization, there's a fantastic user guide in Pandas that explains how to make all kinds of visualizations. They show you how to use basic plots, how to create basic plots, how to make multiple plots or subplots, and it goes on and on. Bar charts, multiple plots, horizontal. They have many, many, many examples. I mean, it just goes on and on. Box and whisker plots, many different types of examples, different types of scatter plots, pie charts. You can imagine it's we could spend an entire course just on different visualizations for Pandas, which uses Matplotlib. See, look at some of these. They're really kind of impressive what they can do. So this is a good place to just look for examples on how to produce different kinds of visualizations. In this section, we're going to look at recommendations and how we can use machine learning models to make product recommendations. If you've done any searching on the web or browsing on the web, you're familiar with product recommendations. They're everywhere. Because the internet, there are all kinds of choices in terms of products, movies, music, videos, everything. So given all these choices, it can be very challenging to figure out products and services that we're interested in. Just browsing for different products and services is really not practical. There are just too many options out there. Fortunately, a number of leading companies like Amazon, Netflix, YouTube, and even Udemy for that matter, they understand this problem and they offer high-quality recommendations that are targeted to your specific interests. So if you look on the right, these are some recommendations that are presented to me. The first one you see, those are recommendations from YouTube based on my interests. And I have some interests in building devices, hardware, do-it-yourself, so there's a YouTube recommendation for that. Similarly, I like playing guitar and improvisation, so they recommend YouTube videos that have backing tracks. And there are some others in the case of Netflix and Amazon. So I'm sure you're all familiar with this. So how does this work? So it's all based on user behavior. And user behavior is a fantastic source of data for making recommendations. Each of us has certain browsing or purchasing behaviors, and those behaviors are captured in a number of different ways. It can be done through user ratings, it can be done through your search history, or the products you've purchased over time. And given enough of this data, we can identify individuals that have similar interests, maybe similar interests to yours. And using their purchasing behaviors, make recommendations of products and services that you might be interested in. Of course, your interests might change and new products are always coming out, so it's important to come up with high quality, consistent recommendations over time. So we're going to learn how to develop a machine learning model that makes movie recommendations in this example. Let's go through the data analysis for this example. And I'll start by going to Google Colab, and we can go to the URL colab.research.google.com. And I'm going to click on GitHub to go to my GitHub repo, and as usual, I'll provide a link to the repository. And we go to the mcdiddly, that's my repo, and the machine learning repo is the one we want. And we're going to scroll down and look for, what are we going to look for? Recommendations, movie recommendations. So this is the model we want to work with. And I'm going to do a couple of things. First, I'm going to clear all the output. And the second thing I'm going to do is change my runtime type to GPU. That's good. All right. So this gives an explanation of this movie recommendations, and this is a common machine learning task, and we're going to use collaborative filtering. And there's a link here if you want to learn more about how that works and the details. So let's go ahead and get started. And first we'll run this TensorFlow magic here saying that we're going to use TensorFlow version 1.x. It's going to take a couple of seconds. We'll do a bunch of imports. These are all very much the standard imports that we've used before. Most of them are the same. And we're going to load the data. And the data is available on the Movie Lens website. So if I right-click on that and I go to the Movie Lens website, it has a data set which we can use for recommendations, and you can read more about it here, and explains exactly how it works. There are two different sets, a 1 megabyte set and a 256 megabyte set, and I think we're going to use the smaller one for right now, but you could use the larger one if you wanted to do more accurate predictions. So we'll run this cell to get that data, to download that data. It's freely available, so we can just download it using the wget and this exclamation point. As you know, that means run a shell command, and that's going to download the data set. And if we look over here under the file section, you see it has been downloaded as a zip file. So that's a zip file, but we want all the data inside of it. And we can do that by unzipping the data. And it creates a number of additional files under a subdirectory: links, tags, ratings, and movies. All right, so if we look over here, here's the folder that I created with all of those and a README explaining what's in it. All right. So let's load a couple of these data sets. These are CSV files, so they're very easy to open up in Pandas. So if I load the movies.csv, we see it has 3 columns in it: a movie ID, which looks like an incrementing number, a title, and it also has a genre. And notice the number of these movies fall into multiple genres. Similarly, there's a ratings data set, and the rating has a user ID, a movie ID, and notice that movie ID corresponds to this one, so we could join these 2 data sets, and then a rating, right? So a user has certain ratings for a certain movie. Right? So this is what the data looks like. There are a couple of other files in there, and we could look at those as well. But these are the primary data sets that we're going to use, these 2, the movies and the ratings. Just given only those 2, the movie ID, the title, the user ID, and the rating. Those are all we're going to use. We're not going to use the timestamp or the genre in this case. All these features are here, and we could use that in the model. We're going to allow the model to figure out that feature and many other features that that different movies have. For this example, we're going to use a method known as collaborative filtering. And collaborative filtering is based on user and product similarity. And it's a straightforward and effective technique for making high-quality recommendations. And it's based exclusively on user ratings for any product. It could be movies, it could be anything at all. And given the user ratings, let's say we have on the right, we can observe some user and product similarities. And both of these are used to make recommendations. And the more data we have, the better recommendations will be. So if you look at this data, you'll notice that these 4 movies, Toy Story, Gladiator, Highlander, and Stargate, there are ratings by 4 different users: user 0, 1, 2, 3, and user 0, 1, 2, and 3. And if you notice, Gladiator and Highlander, they have similar ratings by all users. All users have provided similar ratings. User 3 has provided a slightly different rating, but still it's fairly close. And also, if you notice, user 0 and user 2 also have similar ratings for different movies. They differ by a value of just 0.5, 4, 4.5, 3.5, 5, 4.5, 5.5, and 4.5, and 4. So we could argue that user 0 and user 2 have similar behaviors. They rate movies similarly. So let's imagine a new movie is released. Let's say a new Star Wars movie. And let's say that the new Star Wars movie is rated similarly by all users. Let's say it's rated similarly as Gladiator and Highlander. So that would imply that this new Star Wars movie is similar to Gladiator and Highlander. And if we find that user 0 really liked the new Star Wars movie, and we know that user 2 has similar behaviors, we would recommend the new Star Wars movie to user 2 as well. So that's the basic idea. So how do we implement this? So what we would do is train a model to predict ratings. And the way it works is that collaborative filtering tries to optimize the weight factors of both users and products in order to make an accurate prediction. And these weight factors represent features of a movie. So you could imagine features of a movie could be things like the genre, the producer, the director, the actors that are in the movie, and those are maybe features that you might like about a movie, and that's why you rated it highly. It could be the story, lots of different factors. And you can imagine a critic is somebody that understands these features and describes them to you, and if you like those features, you might want to watch that movie. So in the case of this model, we're not going to specify those features directly. We're going to allow the model to learn these features. And it's going to learn these features given all the user ratings by different users for different movies.
And we can use Keras to do all of this because Keras has built-in optimizers to learn these features or the weights in what's called an embedding layer. And we'll learn a little more about embedding layers shortly. And once the model is trained, we can make predictions or which make recommendations for a new user or any user we like. So if we look over here on the right, the way it works is we have a set of users represented by indices, users 0, 1, 2, and 3. And we have a movie index, movies 0, 1, 2, and 3. And we would use that to make a lookup into what's called an embedding layer. An embedding layer is just a lookup table, really. And it converts each of these users into a vector, into what's called a feature vector. And similarly for the movies. And both these vectors have the same length. And what we do with collaborative filtering is multiply those vectors together or use through what's called a dot product. And if you remember, a dot product, we would take two vectors and just multiply each of the values of the vector and add them together. That's what a dot product is. Just multiply all the values, add them together. That gives us a single number, and so that would be our predicted rating. Initially, these embedding layers are initialized to random values, so our prediction will be random. So what a Keras optimizer does is it compares our initial prediction with the actual rating for a given user in a given movie, and then makes an adjustment. It will use the optimizer to make an adjustment to these feature vectors and these embedding layers, and it will iterate over and over until the model predicts an accurate recommendation for every combination of every movie and every user.
Now that we've downloaded the data, we need to do a little bit of data preparation. And it turns out not to be very complex in this case. So the first thing we want to do is join the movie ratings with the movies, or join the ratings data set with the movies. And the way we're going to do that is Pandas has this really nice method called merge, which is really like a join if you're familiar with SQL. So we're going to take the ratings and merge with the movies, and we're going to specify the column we want to merge on, which is the movie ID. Pandas does something very clever. If you don't give it a column to merge on, it'll just look for all the columns with the same names and use that. It's a nice trick, but I like to specify the actual column that we're merging on just to make it explicit. And then once we join those two data sets, we're going to drop a couple of other columns, the genre and the timestamp. We really don't need those, and we're going to drop those two. And then we'll look at just the first few columns using head, and you see we have user ID, movie ID, rating, and the title. We kept the title around just so as convenient so that we can look at it in during the rest of the analysis and the rest of the data set. We're not going to use this for the training itself, but it's convenient if we want to actually look at the movie title instead of just looking at the movie ID, which is not very useful by itself. We need to do one more step. It turns out that the user ID and the movie ID, that's what we're going to use, but unfortunately those are not sequential. If we were to actually do some more detailed analysis, we'll find out one that doesn't start at 0 and they jump around. They're arbitrary numbers. They're consistent, but they're arbitrary. And our model really needs consistent sequential numbers to work properly, because we're going to treat these as vectors, so we need sequential numbers. To generate these sequential numbers, scikit-learn has a convenient class called label encoder, which will do that. So we'll create a label encoder for the user ID, user ENC, and we'll create a new column called user sequence, and we'll use this user ENC fit transform, and we'll use the user ID column values, just the user ID column values. These are these values right here, right? And it will just choose the total number there and create a sequential number and also make them consistent, right? So really what it'll do is translate 1 into 0, 5 will probably become 4 if there's the numbers are sequential, 1, 2, 3, 4, and so on. So it does all of that hard work for us, which is very convenient. We'll do the same thing with the movie sequence number. The movie ID will create a number, then the number we'll call it movie sequence. So let's do that step, add those two columns to our ratings data frame, and then look at the data frame and see what it produces. All right. So we have the user ID, movie ID, those are still there. We have the rating, we have the title, And you notice that this user sequence and the movie sequence, they start from 0. And they more or less correspond. You see 0, it's user sequence 0 goes to user ID 1 and so on. So also, if you look at this data set, you notice that there are many rows. So because it's a combination of the user and the movie, right? Users and the movies, right? So for this one movie, there were many different users, and they all rated them differently. Some people liked it, some people didn't like it, and so on. We're going to do one more step, which is the test train split. And here we're going to do things a little bit differently. Normally what we would do is take the data set and split by 80-20 or 90-10 or something like that, test and train. We're going to do something a little bit different here. We are going to take a section of the data and use it for test, but in this case, we're going to use all of the data for training. And the reason we need to do that is that if we were to remove some of the data and exclude that from training, we may exclude entire movies, or we may exclude entire users. And that's going to cause a problem when we make predictions. So what we're going to do in this case is use all of the data for training, and we're going to use just a subset. We're going to use that just to validate our model and just measure the validation loss, just to measure how well the model is training. And we'll look at this in more detail. All right, so we'll do this test train split, and we're going to split the by 80-20, so 20% we'll use what we call the test data set just for validation purposes. And we'll also set this random state to 0 that is initialized as a random seed, so that way we always get consistent results in terms of the test data set that we're going to use. And we're going to use the training data, we're going to assign that to train unused, because we're not going to use the 80% for training. We're going to use all of the data for training. So I'll take the ratings and assign that to this train variable, and that's what I'll use. The number of unique users and the number of unique movies, notice there's a combination of the two, right? We'll get the length just to see how many users there are and how many movies there are, and also the length of the train and test data sets. So we see here there are 610 users that we have, and about 9,700 odd movies in this data set. So the total number of rows that we have is about 100,000. So if you look at the combination of these two, it's about 100,000. Right? And we have in our test data set about 1/5 of that, or 20,000 or so. So that's the data set we're going to use. The model that we just described uses what's called a Keras embedding layer. And what this embedding layer does is it translates numbers into vectors. And we need that in many different cases, because we might have a set of objects, let's say users, movies, words in a sentence, or any kind of object that we want to somehow use with a machine learning model. In order to use it with a machine learning model, we need to translate these objects or convert them into a suitable set of vectors so that we can train our model. And one way to do that is to convert each object number each object starting from 0, and then translate it into a vector. And Keras has what's called an embedding layer that can do exactly this. An embedding layer is basically a lookup table that has a set of value. For each value that we supply, it translates it into a vector of a given size. So if we look over here on the right, this is what an embedding layer might look like for movies. So let's say over here I have a list of movies: Toy Story, Gladiator, Highlander, and Stargate. And for each of those, I just apply a unique index. It doesn't really matter what the index is, they just have to be unique, and they just have to start from 0, and they have to be sequential. That's all. So the embedding layer would take this index and map that index into a vector. And initially, that embedding layer, the vector would be filled with all random numbers. And through the training process, we'll learn the values for each of these vectors, or these feature vectors. When we create the embedding layer, we have to supply two values. We have to supply the input dimension, which are the number of objects that we have. Here we happen to have 4 movies, so the input dimension would be 4. And then we have to specify an output dimension. And here we happen to have vectors with 3 values, or an output dimension of 3.
This is a number we can choose. The larger the number we choose, then the higher the dimensionality would be, and we can describe more complex features of an object. And this is a hyperparameter we can adjust depending on the kind of problem we're trying to solve. So this is something you might want to experiment with when training your model. A smaller vector output dimension will train much more quickly, but may not train very well because it doesn't represent the output space very well. And of course, we could use a very large output dimension that might train well, but it might just take a longer amount of time to train. So it's really an adjustment that we've got to make as a balance between the amount of training time and the best quality of best accuracy we can get. Now let's look at the model itself, this recommendation model, using this collaborative filtering technique. And what collaborative filtering tries to do is minimize the error between the predicted value and the ground truth. And the ground truth happened to be the ratings for each combination of movie and user. So the way we're going to define this model is a little bit different. We're going to use what's called the Keras functional API. We can do everything we can do with the sequential API and using the functional API. The functional API is slightly different, and there's an explanation if you click on this link here, and it gives you some more details about the functional API. It has a little more flexibility to it, and the reason we want to use that in this case is because we have two inputs, both the user vector and the movie vector, instead of a single vector. We could have combined that and done it a little bit differently, but in this case we happen to have two of them, so we'll use the functional API to input both of those. All right. So we have a couple of hyperparameters here. One is the number of features, and we talked about that a little bit earlier when we described the collaborative filtering model. So the number of features represents ways to describe a movie, and this is arbitrary. So if we just had one feature, maybe the genre, that's one way to describe a movie, but that's not very complex. There are possibly many, many ways we can describe a movie. Mathematically, we can choose an arbitrary number. And here I happen to have chosen 50. You can experiment with this, try smaller numbers, bigger numbers, and see how that affects the training of the model. I also define the dropout. In this case, I have no dropout, but that's another hyperparameter we can experiment with for regularization. So when we create a model using the functional API, we create layers, but we chain the layers together. So I'll show you what I mean. First, we have an input layer. We have to start with an input, and the shape or the input dimension is just one column or one vector, right? The user vector in this case. We have a similar one for the movie vector. It just has, it's one column, one dimension. And right after that, we have an embedding layer, and that embedding layer is a set of factors, right? And the set of factors includes the number of users and times the number of features that we want to have. And here we want to have 50 features, arbitrarily chosen. It's a number we can experiment with. Now the input to that layer is going to be the user input. So you see that this input layer feeds in to this embedding layer. And then I'm going to flatten that just to make it a single vector because we have a combination of the users and the features. So this flattens it out and just makes it one wide vector. I'll add some dropout for regularization. And notice the dropout takes the input of this flat user. So these are all being chained together. The input goes into the embedding layer goes into the flatten layer, and the flatten layer goes to the dropout layer. And then this is our output from the user. All right? Just those three layers in sequence. We'll do the same thing for the movie, exactly the same thing using the same input shape because the movie is also a single vector, an embedding layer, given the number of movies and the number of features, which is also 50 in this case, and the movie input. We'll flatten that, add a dropout there as well. So exactly the same. So we're not treating users or movies any differently. Then we'll use this dot product, and Keras has a convenient layer called dot, where you can give it a list of layers, and it will take those vectors and multiply them together as a dot product. And if you remember your linear algebra, dot product means take all of the elements, multiply them together element-wise, and then add the sum. Take all of the elements of the movie vector and the user vector, multiply those together, and add them up as the sum. Right? So that's the simple model. Now, there's one more detail I'm going to add. These are just weight factors. These embedding layers are just weight factors that the model is going to learn. But to improve the model somewhat, I can add also a bias, a user bias and a movie bias. Reason being is that users may tend to never give a movie a 0. Some users may always offset the movie by 1. They never say a movie is so bad. They say a really bad movie is a 1, not a 0. Similarly, some people may say the best movie is not a 5, it's a 4 or something like that. That might be a bias some people might have. So to account for that, we can add another embedding layer, and we'll call it user bias and movie bias. All right? And we'll add those on top of the input to that will be the user input and the movie input. And then we'll sum those together, add the dot product and the user bias and the movie bias. So we're adding all these values together, adding them all together. All right? So then we'll flatten that again come up with one vector, and add a dropout layer there as well, just for more regularization. And the model will take the user input, the movie input as 2 inputs. So this is the reason we're using the functional API and using this model class. We're giving it 2 inputs, the user input, the movie input, and the output that it's going to optimize is this output right here. All right? So if you go through this, maybe you want to draw it out and look at that diagram we had in the lecture to compare how this works. So most of this looks very much like the diagram we had in the lecture. The only detail I've added is the user bias and the movie bias. All right? And then we can print out a summary of this. So let me run that cell and take a look at what we get. So we have a number of different layers, and we can see the output shape. So the first layer it has a shape of 1, meaning it's just one column or just a single vector, right? And the embedding layer adds 50 more, another dimension of 50, because that was our number of features, right? All right? And then we flatten it. So we multiply those two, and we get an output of 50, a dimension of 50, and the same thing. So then we add dropout and so on, and the dot layer. Then the dot, notice the output is 1. It's just a single number, right? And you can go through all the details here and go through each of the layers and look at all the dimensions of each of these output layers. And that's something it's good to do, so you'll understand how these layers work together and what the values look like, or the shape of the data that comes out. And you notice the number of parameters that are being learned. And here's where we're going to learn what the model is going to learn. It's going to learn this embedding layer, this other embedding layer, and it's also going to learn these 2 embedding layers, which are the biases. So these are the weight factors, and these are the bias factors. You can also name each of these layers if you want. The Keras API has a way to name each of them. So instead of coming up with these names that are not easy to see, you can give it names and relate them back to the model. All right. So the total number of parameters, about 500,000, we're going to learn during the training process. Now it's time for model training. So here's the step here to train the model. We'll compile the model, and the loss in this case, we're going to use mean squared error. And remember, we use mean squared error whenever we have a linear output or a numerical output. In this case, the numerical output happens to be the rating. It's a number that ranges between 0 and 5, so that's why we're going to use mean squared error. And so Keras is going to try and minimize that. And we'll use the Atom optimizer. As you remember, Atom is one of the better optimizers. It converges relatively quickly. It's a good one to start with. And the training process, we're going to use model.fit. And here, remember, we're going to use 2 inputs. In the previous examples, we used a single input, but here we're using 2 inputs, both the user sequence number and the movie sequence number. All right, those numbers that we generated in the data preparation step. And the output, or the Y value that it's going to try and optimize, is the rating number between 0 and 5. Batch size of 32, which is a typical number. We're going to run 10 epochs. Verbose 1 means that's how much of the logging we want to see the progress at each epoch. And the validation set, we're going to use the test user sequence number, the test movie sequence number, and the test rating. And then we'll plot both the
the training loss and the validation loss. All right, let's go ahead and start that. And it's going to take a little bit of time because there's a fair amount of data, and it's got to go through. There are quite a few parameters. There are about 500,000 that we're learning in this model, so it's going to take a little bit of time. All right, we're just about at the final. We're at the final epoch. Almost done, and you can see the loss is pretty good. The train loss 0.27, and the validation loss is even slightly less than that. So there we have the accuracy or the loss, and it seems to be fairly well regularized. They both are converged, but you notice this is the test loss is slightly lower. The test loss is slightly lower than the validation loss is slightly lower than the train loss, or the test loss is slightly lower than the validation loss. So that doesn't mean that this is overfitting. Overfitting would be the other way around. Overfitting means that the validation loss is higher than the test loss. The train loss. So this can't be fixed with regularization. This is not a regularization problem. So why does this happen? So what this effectively means is the model is more accurate with test data than it is with the training data. It's more accurate with data that it hasn't seen than the data that it was trained on, which is a little strange. Why does that occur? And if you read the Keras FAQ, it'll explain this. There are a couple of reasons why this might happen. One reason is just the way that Keras works. The way that Keras computes the train loss is it's computing the train loss as it is training one epoch. As it's going through an epoch, it's averaging the loss, meaning every time it's iterating and it's going through the process, it's averaging the loss. So when it computes the test loss or the validation loss, it does it at the very end. And if you think about it, the model is actually getting better as it's being trained. So at the very end, it's actually slightly better. So that's one of the reasons that you can get a slightly better test loss or validation loss than you would with the train loss. The other reason is if the validation data set that you're using is not representative of the training data set. It just could be that the validation data set or the test data set is a lot easier for the model to predict with, and it just does a better job of predicting. That usually happens if you have a very, very small validation set and it's not representative of the larger training set. In this case, we use 20%, so it's unlikely that's the problem. It's more likely the fact that it's just an artifact of Keras. So when you see that, just be aware of those kind of problems that you might run into, and that it's probably normal. The other thing that might occur is that you might have excessive dropout. If the dropout is too high, that may also contribute to a very high train loss, which is another possibility. In those cases, you may want to reduce the dropout and retrain. Once we've trained the model, we can then make predictions or make recommendations for a given user. So the way we would do that is we would take the trained model and supply it with a list of users, and in this case only one user, so we'll fill the input vector of users with all the same user, and then a list of all movies, because we want to predict the rating for one specific user and all movies. And we would put that through the model, and that's going to make a set of predictions or the recommended ratings, and then we could take those ratings and sort them descending to find the highest rated movies. And from there, we could choose the top 5 movies that we would present to the user as recommendations. Of course, we might want to apply some business rules, such as filter out any movies the user has already seen, because you may not want to present recommendations for a movie that they've already seen. Now that we've trained the model, it's time to make some predictions. And the way we're going to do this is we're going to take all of the movies, all of the unique movies, and create a vector of all the movies. And then we want to choose a specific user, provide all the movies and one user, and predict the rating for that user for all movies. Predict the rating for all movies given one user. Right? That's the idea. And then that'll give us a number, which is what we expect that user would rate each of the movies. And then we would rank them or sort them by the highest rating. And the ones that have the highest rating we would then present to the user and say that's what we recommend as the movies that you might like. Of course, we could add some additional logic there as well, because if that person has already seen that movie, and we would maybe look in a database and say if they've already seen it, we wouldn't want to recommend it. But that's some additional business logic we can add. But the basic process is to use both those inputs, all movies and a specific user. So here's the example. So we're going to choose a specific user, and here we're just going to say user number 0. We could have picked any one of them, but we'll just pick user number 0. And then we're going to take the distinct set of movies, just the unique movies. And the way we'll do that is take the ratings data set, which is the full data set of all movies and all users, drop the duplicates for given just the sequence number, using the sequence number, and remove all the duplicates. Because remember, the entire data set maybe had 100,000 rows in it, but there are only about 9,700 odd movies, so we only want those unique combinations. We don't want all movies. So from that, we'll create the movie vector, which is the unique movies, just the movie sequence number and all the values. So that gives us a NumPy array of those values. Now we need to create a similar sized vector, the same size vector as the movie vector, with just the user number. And the way we'll do that is a clever way to do that with NumPy. NumPy has a method called np.ones, and np.ones, what it does is it gives you a NumPy array of whatever shape you want, and in this case filled all with ones. And in this case we're going to give it a shape of the number of unique movies, which is just a single dimension, and it's going to be all filled with ones. And if we multiply that by the user number, that will be a vector of all user numbers. And it just turns out the user number is 0 in this case, so it'll be all zeros. But if we change this number, it'll work just fine. Then we go ahead and make our prediction. Remember, we put in two inputs, both the user vector and the movie vector. So this is going to give us a set of predictions. And from those predictions, I'll create a Panda series with that, and then create another data frame, taking the unique movies, make a copy of it, and add those predictions as another column, predictions, to this predicted data frame. All right? And then I'll sort by the predictions descending and just show the first 10 of them. Sort by the predictions descending and display the first 10. So here's what we get. So these are all the distinct movies, or the unique movies right here. All right? User sequence number is 0 because we're predicting for only that one user. And these are all the different movies and their predictions. So some movies are rated very high. So the highest rated happens to be Batman. So for this user, we're saying that Batman would be the most likely. Notice this number is actually greater than 5 because it's a prediction. It really should be probably less than that, but since it's making a prediction, it has some variation to it. It's not perfect. But all that matters is that this is the most likely. Right? And it goes down from there. And so these are all the predictions. And you can also compare ratings other people have made. This happens to be other users, for that movie. So in this case, this was rated a 4.0 and so on and so on. So this actually is not too far off. Not too far off. And actually, this happens to be the same user in this particular case. So it seems to work well. Right? It seems to work reasonably well. So as mentioned, you could go through another step, which is kind of some additional logic. If you happen to know this user has seen Batman, then we would not want to display that because they've already seen it, and so on. That's some logic you could add. Let's do a little bit of error analysis and look at some cases where the predictions we make do not compare well with the ground truth, and try and understand why our predictions were poor. So we'll take our predictions that we made, that data frame that had all our predictions in it. We're just going to select the ones that match the user of interest, this user number that we've chosen. We'll make a copy of it, and we'll add one more column to it, and that column we're going to add is the error. And we're going to calculate that error using the rating that user provided, the ground truth, meaning the rating that we know what the user provided, and subtract the prediction, take the difference between the two, and then square it. Just a way of getting the absolute value. We could have used absolute value as well. That would work fine too. Because all we want to do is sort that value, sort the error descending, meaning that we want the ones with the largest error. Look at the ones that didn't predict well at all. So if we look at it, the error here is 16. It's the very high error.
and we predicted that this movie Fargo, this user 0 would not like it at all. That was the prediction. But it turned out the user actually liked it a lot. It really liked it, so that was a big difference. Same thing for Duck Soup and so on. There are a number of others, Monty Python, that had a very high error. It turns out that user liked all these movies, but we predicted they wouldn't like all those movies. So that was incorrect. So let's look at one of these examples. Let's look at Fargo 520. And the way we'll do that is we'll go through the set of all ratings and just look for all movies with ID 120, or that sequence 520. And that's going to give us the ratings for all users for just that movie. So if we look at that, and in this case I happen to have sorted it ascending by rating. And if you look at it, even though this user did like Fargo, user 0 liked Fargo, you notice that there are a lot of people that didn't like it. So it's possible that this is kind of a controversial movie. I don't know, I've never seen Fargo, so I'm not really sure. But it's possible that it's controversial. Some people really liked it, some people really didn't like it. So it has a lot of variation to it. So maybe there are other users that were similar to user 0 that just didn't like Fargo, and that's why it was given a very low predictive score. So those are some ways that you could come up with errors, because there are movies that, even though you may have friends that are very similar and you have similar tastes, you may like a movie and they may completely dislike it. That's just the way things go. And if you think about it, that's not necessarily a bad thing. If we made an incorrect prediction and we recommended a movie to someone that may actually not like the movie, it's not necessarily really bad unless we do that too often. It's possible, because humans are not completely predictable, even if we made a prediction and we showed them a movie and they didn't like it, it's possible they might like it. Or maybe that we think that they wouldn't like this movie and then we showed them the movie anyway, they might like it as a recommendation. So as long as the error isn't too high, we aren't recommending too many movies that they won't like. And you can imagine there's a number of improvements we could make. We could obviously introduce far more data to it. We only have a few hundred users and a few thousand movies. But if we had a much larger data set, we could definitely make better predictions. Let's go through some common questions. Often people ask, are there any other solutions to this problem, to the recommendation problem? And of course there are. There are many solutions. There are Bayesian models, clustering models, latent Dirichlet allocation, lots and lots of models, ways that you can solve this problem. And I'll provide a link where you can read more about it. Interestingly, many years ago, Netflix had offered a $1 million prize to anyone who could improve their collaborative filtering models. And they provided a very large data set similar to the one we used for our training and test to see if anyone could do that. And in 2007, a group did win that prize, and they were able to improve their models, Netflix models, by 10 percentage points, which is a significant achievement. The team that won used an ensemble method, or a technique that used many, many different models together. It was over 100 models, I believe, that they put together to achieve that 10 percentage point improvement. The next team after them was very, very close, but you can imagine to achieve that high level of performance, you do need a very sophisticated model. So next, what are some limitations to this approach? And one of the most common ones, which is a limitation to just about every machine learning model, is lack of data. And in this case, it's particularly acute because you can run into what's called the cold start problem. If there's a new product introduced or a new movie comes out, no one has experience with it, or maybe a new user who hasn't made any purchases, so we don't have any prior history, then there's no way to make an accurate prediction. So things will be wildly incorrect. Fortunately, there is enough volume these days that there's enough social media, there's enough interest that we do get data pretty quickly. So the cold start problem doesn't occur for very long. And of course, the best way to learn about these models is to experiment, just like all the other models and everything else we've talked about in this course. So I encourage you to try out hypotheses, try out different models. There are many examples available. Try it out with different data sets. Come up with your own data set and see how well it does.
And as always, if you have any questions at all, just feel free to ask, post a question, or if you want to send me a private message, that works as well. In this section, we're going to learn how we can use machine learning to understand customer sentiment. Product reviews, customer feedback, or any comment that someone provides about a product or service can give us some idea of how a person feels. For example, if we look at these comments on the right, you see, wow, I love this place, crust is not good, not tasty, and so on. Just by reading that text, you have an idea of what that person feels. They may have a positive or negative sentiment. And collecting a large amount of this customer comment data is known as sentiment analysis. And this sentiment analysis can help us make purchasing decisions or improve customer satisfaction. And like everything else, the more data we have, the better our predictions will be and more accurate our analysis will be. So there are a couple of ways we can collect customer sentiment. We could do it either with structured data or unstructured data. So structured data would be like in a survey. In the case of a survey, a person would have to fill out a form with multiple questions. Maybe they have yes/no answers. They have a scale degree, 1 to 5, or something like that. And unstructured data would be a comment form where someone could just enter in whatever text they like. Now, structured forms and structured data is relatively easy to analyze. We can use traditional statistical techniques to analyze that. But often people don't like to fill out surveys with lots of questions. They don't often have an objective measure of good or bad. What's easier for a lot of people to do is just provide a comment of how they feel. And that's often much easier to collect information. So it's easier to get the data using an unstructured form where people just type in how they feel as a single statement. But of course, analyzing that is a little more involved, and that requires analyzing natural language text. And that area is what's called natural language processing, or NLP. So we're going to learn a little bit about natural language processing in this section because we're going to use customer comments to analyze sentiment. Let's take a look at the data set that we're going to be working with in this example. So I've already opened up Google Colab, and I'm going to open a notebook, and the notebook is going to be in my GitHub repository. I'm going to click on GitHub, and I'll put in the name for my GitHub repo, and I'll provide a link to this in the resources section so you don't have to type it. And the one we're looking for is under text glove sentiment. This is the one we want, text glove sentiment. .ipynb. All right, so I'm going to do a couple of things here. First, I'm going to clear all the outputs, and then I'm going to change my runtime type to use a GPU. All right, let me save that. And let's just go through the notebook. So this explains a little bit about the problem we're trying to solve, the sentiment analysis, and the data set we're going to use is a set of labeled reviews from Yelp, Amazon, and IMDb. And we're going to use the glove vectors or glove embedding vectors for word representation. All right, so this is going to be a TensorFlow 2 notebook, and notice it says it's not authored by Google, but we're going to run it anyway. There's nothing dangerous about this notebook. Okay. And we have a number of imports here. We're going to use pandas to load the data because it is delimited data. Even though it is unstructured, the comment is in one column and the label is in another column. And we're going to use a number of Keras layers here. And we're also going to use Matplotlib for plotting, as we normally do. And scikit-learn, we're going to use just the test train split, which is very convenient. Import all those libraries. And now we're going to download the data set, and the data set is available here in the UCI machine learning repository. If I right click on that and take a look at this, this gives you a nice description of what it is and where it comes from, so you can learn more about it. So let me go back here, and I'm going to download the data. I'll just click on this link, and this does a convenient download. It uses the wget command, and it comes down as a zip file. I'm going to unzip the file and also rename it. It comes in this file name sentiment labeled sentences. I'm going to rename it as data and list that data directory. And you notice it has 3 different files in it, and also a README that has more information about it. And if I go over here and look in the folder view, I can see all the data that's downloaded, the files. All right. So let me load these 3 files in using Pandas, and I'm going to use Pandas read CSV, and there are 2 columns in there, the comment column and the sentiment column, and unfortunately they don't have the column names in the file, so we need to specify the column names, and they're separated by a tab. So I'm going to loop through each of these files, read each one, and append it to this list of data frames, and then concatenate them all together so I have one data frame, and at the end I'm just going to look at the first 10 samples right there. So it says I have a total of 2,748 samples, and notice this is the first column, which has the comment, and the next column has the sentiment, and 1 means positive and 0 means negative. So that gives you a rough idea of what the data set looks like. So we're going to use this for a supervised classification model. We're going to use this as the X input, or the X value, and this is the Y value, what we're going to predict. We're going to predict the category, which is just positive or negative. This category could have had other values as well. We could have had positive, neutral, and negative. For example, it just turns out this data set only has a binary classification, positive or negative. So how does sentiment analysis work? Well, this is what's called a supervised classification model. What we're going to do is use a supervised model to determine what a comment means, or the category of each comment. So given this data set you see on the right, given comments and the associated label or category, we can train a machine learning model to learn the relationship between the two. And in this case, the category is binary, just good or bad, 0 meaning bad and 1 meaning good. We could have multiple categories as well. Once we've trained a machine learning model, we can then give it new input to make a prediction of the category that comment represents. Now, in order to do this, we need to find a way to encode text, because as you know, models understand numbers. They don't really understand text by themselves. So we need a way to turn this text into vectors or numbers of some kind. So there are a couple of broad approaches to doing this. One is what's called the bag of words approach. And the way we do that is just take all words in our vocabulary, in our corpus, and assign an incrementing number to each one. We could maybe alphabetically sort them and assign a number increasing. That's a very simple approach, but it's somewhat arbitrary. It doesn't capture any relationship between words, and given, let's say, the English language, the numbers could there may be 50,000 or more. There's, tens of thousands, maybe even 100,000 words, and the numbers would be very close together, and really we couldn't distinguish each word from each other very well. So another way to do it is what's called using a predefined embedding. We could create a dictionary of words and assign a meaningful vector to each of the words. So if we look over here, I have a set of words, and for each one I've defined an embedding vector. And in this case, the vector is relatively short. It only has 4 values or 4 components to it. In the real world, practical embedding vectors are quite large. They may have 100 elements to each vector. So this is a little more involved, but the nice thing about it is it can capture relationships between words, and also it can represent words more uniquely. So where do we get these word embeddings? How do we compute these vectors? So we know that a number of words are related. Let's say computer and keyboard, or rain and umbrella, and we would intuitively think there should be some kind of a relationship between the two. And we could compute vectors such that the distance between these vectors is closer or similar. So one embedding that's well known is what's called word-to-vec, and it does exactly that. It looks at relationships between words and assigns them. So another approach to doing this is to automatically learn the embedding vectors given a large corpus of text. And this has been done with what's called GLOVE, or Global Vectors for Word Representation. And that uses word co-occurrence. So they looked at a very, very large corpus of text and looked at what words are close together in different sentences. And based on that, they were able to compute vectors. And over here on the right, what you see is just a small snippet of the GLOVE vector table. It has a list of words, all the words, and there are tens of thousands of them, and then the vector that it represents. And there are different sizes for these GLOVE vector data sets, representing more complexity. So this happens to be one of the smaller ones, and the vector happens to be of 100 elements. Each of these words is represented by a number which is 100 elements in length. Now let's look at the data preparation step. And remember, in order to prepare this data, we need to convert the text into vectors. And we're going to use GLOVE embeddings. And these GLOVE embeddings are available in a set of files we can download from the Stanford website. And if we right-click on that link, we can see there's an explanation of global vectors for word representations, and who created it and so on, and how. And there's some code available also that you can use along with this data set. We're just going to use the embeddings themselves. We're not going to use the code that they supply. And there are a number of pre-trained vectors, and they come in different sizes. There's 6 billion and 42 billion and 840 billion. There's some really large data sets. We're going to use the smallest one here, the 6 billion, but you'll see that it's quite large by itself. So let's go ahead and download those GLOVE embeddings. And this is a fairly large file. It's gonna take some time to download. Let's take a look. How big is this file? It's about 822 megabytes. So unfortunately, the network connection from this Google Colab notebook isn't particularly great, so it does take quite a while to download. And once we download it, we're going to unzip the file and then just print out that it's unzipped. So I'll just pause here while it's unzipping. All right, it's just about done with the download, and now it's doing the unzip. And you notice the unzip also takes a little bit of time because this particular file has multiple files. This particular zip file has multiple embedding files in it. And as we'll see once it's completed. All right, so it's all done. And if we look at the files over here, you notice that there are multiple files. There's the original zip file, which is quite large, 822 megabytes. There's also a 50D, 300D, 200D, and 100D. And what each of these represents is the number of dimensions of each of the GLOVE vectors. So this one has a 50-dimension GLOVE vector. So for each word, there are 50 values that represent the vector for that word. And this one similarly has 300, 200, and 100. So what this means is that the 50D, or the 50-dimension GLOVE vector, is the simplest one. It has the least number of values. It's the simplest embedding. And the 300D is the more sophisticated. So this larger embedding vector would potentially contain more information and potentially could lead to a more accurate model. For our use case, we're just going to work with the 50D just to see how this works. All right, so we've unzipped the files, it's all done, and we need to do a little bit of preparation when we load these GLOVE vectors. We're going to use some constants here, the number of words we're going to work with. Even though there's a very large number of words in this GLOVE embedding file, we're only going to work with 20,000 because our data set is quite small. There's also a maximum sequence length that we're going to encode. So this would be the maximum number of words that we're going to work with in each of our sentences. And in this case, we'll limit it to 1,000. It turns out our data set is relatively small, so 1,000 should be sufficient. And any values beyond that, any text that's less than 1,000 will get padded. And we're going to use the 50-dimension GLOVE vector. This is going to be our embedding dimension. So this, let's go ahead and run this cell, and all it does is defines a couple of functions. One to load the glove vectors. When it loads, it's going to open the file and read each line in the file. And that file contains a word, as we saw, and then it has a list of vectors. So it's going to split the line, and the word is going to be the first value in the line, and the rest of them is an array. And we're going to take those values and represent it as a NumPy array. So this will produce a Python map or a dictionary where each word in the dictionary will contain a glove vector. And this is going to create what's called an embedding matrix. Whenever we have for a given word, we're going to encode it using this, and it'll return an embedding matrix. And the way it's going to do that is by loading the glove vectors using this function up here, and it's going to zero it out, given this embedding dimension, this embedding matrix. And for each word in the word index, or the list of words that we're going to get, we're going to look up the word in our glove map, and as long as it's in there, we're going to return the value for that embedding matrix. We're going to fill in that embedding matrix for each word that we see in that embedding matrix. So this is how we're going to create the embedding matrix. All right. So then we're going to actually encode our text. So here's our training data, and we're going to take just the comment for each of the training data and turn it into a string, just as type string, because it's initially it is just an object when we load it in pandas, and convert it to a list. We're also going to take the sentiments out of the sentiment column and use those as the labels. And pandas, or Keras and TensorFlow 2 has this tokenizer where we can take each of the text and use this method fit on text, and it'll perform this this basic operation of taking each input sequence of words and padding it and turning it into a set of sequences. All right, and then we're going to pad them using this pad sequences to make sure that it's padded up to the max sequence length. And remember, this value was 1,000. We're not going to allow more than 1,000 words, so anything beyond the length of each line is going to be filled with zeros. All right, and then finally what we're going to do is split this into a test and train set so we can use it for validation. So let's run that. And then we're going to run this method here, this create embedding matrix, and that calls the method above, which is going to load the glove vectors and create this embedding matrix. So now when we feed our comments into our model, each of the words in those comments are going to be converted into vectors, which will be all assembled together and sent into the model as a matrix. Now that the data has been prepared, we can define the model that we're going to use for classification. And as mentioned, this is going to be a supervised classification model. So we'll define it like this. And in this particular case, we're going to use what's called a 1D convolutional neural network model. And as you remember, convolutional neural network models are often used for images. They work very well for that. But it turns out we can use them for other applications as well. And in this case, we're going to use it in this text classification model. And the reason we're going to use convolutional neural network is because CNNs, they have this ability to encode spatial similarity, meaning it can look over several pixels or words. In this case, we're going to look over several words. So let's take a look at how this works. So this is a standard sequential model, and what makes this different is the first layer is this embedding layer, and the embedding layer is the one that's going to take our sequences of words and convert those into vectors. And remember, we created that embedding matrix that does that translation from words into a matrix. And it has some other parameters as the maximum number of words, and then the maximum sequence size, and this very important argument here, trainable equals false, because this embedding layer is fixed. We created that using the glove embeddings. We already know what the vector value should be, so we don't want this layer to be trained. We want to use the values that are part of the glove vectors. All right, so this trainable false is very important. If we were to leave that out, and what we could do is train this embedding layer and learn our own embeddings. And in fact, that's what's done when glove embeddings are created. We'll add some dropout here for regularization. And here's our convolutional layer, the 1D convolutional layer. We're going to use it's going to have an input size of 128 units. This is a hyperparameter. We can change that to see how it performs, to improve performance. And this is the kernel size, and the kernel size we're going to use is 5, and 5 meaning that we're going to look across 5 different words. And this is another hyperparameter you can experiment with to see if it does any better. The idea is that presumably words that are within 5 other words gives you some kind of context. Right? It's possible that you could have had a longer sequence where there was context in many words away, but we're going to just try 5 for now. And this has a ReLU activation and padding same and strides of 2. These are all hyperparameters we can adjust to experiment with the model accuracy. Then we'll add a global max pooling 1D. That's going to reduce the dimensions from 2 dimensions down to 1. Add another dropout layer, and finally a dense layer and a final dense layer, which is going to have 2 outputs. The num classes we defined was the 2 classes we want to have, meaning positive or negative. So we could have had classified it into 3 or more, in which case the num classes would have been more than 2, right? And the output is going to be a softmax layer because we want it to be represent the probability that it is one or the other. And finally, we'll print out the summary. So if I run this cell, it's going to give me a summary of this model. And you see the size of each layer. Notice the first layer, the output shape is 1,000 by 50 because this was the number of words. Maximum number of words we're going to allow is 1,000, and each dimension is a 50, the vector representing the glove embedding, which is we chose 50 dimensions. So this is what the first output layer is going to look like. Then we had dropout, the convolutional 1D, which has an 128 units output, and the global max pooling is going to remove that, is going to pool all those together. So now we reduce that to a single dimension of 128. We'll add one more dense layer just to group all those together. And finally, and there's one more dropout layer for regularization. And finally, we'll have the dense layer, which has 2 outputs in it representing positive or negative. Positive or negative. So that's our model that we're going to train. So you'll notice the total number of parameters in this model, 312,000 or so, 313 and 312,000 roughly. And the trainable parameters, there are 48,000 of them that are trainable, meaning all of these layers down here, those are trainable. And there are a number of non-trainable parameters, or 263,000 of them. And those come from this embedding layer, which we are using the glove embedding. So those are not going to be trained. We're going to use the fixed values. Now that the model is defined, let's go ahead and train our model. And I'll go ahead and get it started because it might take a little bit of time. And what we're going to do here is first compile the model, and we're going to use this kind of loss, this sparse categorical cross entropy. And we're going to use the atom optimizer, and we're going to collect the accuracy as one of the metrics. We use model.fit, as we've seen before, the xtrain and ytrain, and we'll start with a batch size of 128, another hyperparameter we can modify. And we're going to just run 40 epochs. We're going to iterate through the data 40 times. And we have some validation data as well. And finally, we'll evaluate the model after it has been trained and look at the test loss and accuracy. And also plot out the accuracy as the number of epochs. And since we were using GPU to train this, it trained relatively quickly. And you notice that the accuracy is not fantastic. We get maybe an accuracy of 83%, something like that. And you notice that there is a little bit of variation. We could probably adjust the dropout or retrain it a little bit and try and get the variation minimized. But you notice it's not 90% or better. It's maybe in the 80s, and then the low 80s. That's about as good as we can do. And you can experiment with this model further to try and see how well you can improve it. So one thing about these embedding layers, so the reason we use those glove embeddings is to try and improve the accuracy somewhat. And using those pre-trained embeddings does help a little bit. It'll give just a few % improvement. So if we didn't use those pre-trained glove vectors and we learned the embeddings ourselves, you'll find that the accuracy will be a little bit lower. So that's what the glove vectors do for us. They improve the accuracy a little bit more by knowing that there's some context in these words and some similarity in these words. So let's try and do some prediction and see how it works. In this case, I'm just going to predict all the comments and select the most likely prediction for each comment. And then here I'm going to pick a number of random values, random comments, and print out the predicted value and the label and see how they compare. So here's one. But another that the movie that seemed to drag on, and the drag and the heroes didn't really work for their freedom. So it says the prediction was positive, but the label was negative. And maybe because it's hard to tell, even a human reading it, it seems like drag and the heroes didn't really work for me. Maybe it's negative, and it probably is negative, but the model predicted it as positive. I guess it didn't fully understand what was meant there. So here's another one. Also, it's slim enough to fit in my alarm clock docking station without removing the case. So yeah, that seems positive. And even though it says without removing the case, maybe that without is why it predicted that incorrectly and thought it was negative. So this one it got correct. The food was excellent and service was very good. Right? So that's a relatively simple one, and notice it predicted correctly in that case. Just really good. So far, probably the best BT headset I've ever had. So again, good, maybe because of those words, it's very positive, it predicts those quite well. Here's a negative one. I've never been treated so bad, and that's clearly negative, and it predicted that one correctly. Let's do some error analysis and try and understand some cases where it doesn't match the label doesn't match the predicted value, and try and understand why it's incorrect. So here's one. It was a pale color instead of nice and char and has no flavor. Not really sure what they're trying to say there. But the label is 0, meaning it is quite negative, but it's predicted as positive. And maybe because it says it was a pale color, maybe it thought it was positive for that reason. But instead of nice, and maybe it says nice and clear, I don't know. It has no flavor, so that's really kind of negative. And maybe also these uppercase letters. And of course, this model doesn't take into consideration uppercase letters, so that's probably why it got that wrong. Here's another one where it's kind of close, right? In both cases, it could have gone either way. My boyfriend and I came here for the first time on a recent trip to Vegas and could not have been more pleased with the quality of food and service. So notice this ends up positive and could not have been more pleased. So this is a negative there, and that's what makes it positive, right? But the prediction is negative because it probably, the model gets confused and says not have been more pleased, right? So maybe it doesn't really understand this not part. And also it's a very long sequence. We could probably analyze specifically longer sequences versus shorter sequences and see if it does better in those cases. And here's another one, also a relatively long sequence. It's like a really sexy party in your mouth where you're outrageously flirting with the hottest person at the party. That's an interesting one. So that's a positive one. But for whatever reason, it's maybe the word outrageously or something is what throws off the prediction. Right? So here's one, a short sentence. The black-eyed peas and sweet potatoes, unreal. All right. And that was predicted with negative sentiment, and it could have gone either way. It's kind of close. In both cases, it could have been predicted in either direction. And it might have been maybe because of unreal, right? Because unreal could be a negative, right? So you can see this model kind of works, but it's not super. It's not a fantastic model, but it does generally work. It does generally work. And in theory, if we had more data and we trained with a larger set of glove embeddings, we could improve this model. Our previous sentiment analysis model wasn't great. It had only an 80% accuracy. And we could ask, why did that happen? Why is the accuracy so poor? And there are a couple of reasons. One, we had a relatively small training data set, only 2,000 or so, or less than 3,000 samples. So that's not a very large training data set. If you compare that to, say, the MNIST training data set that has over 60,000 samples, so it can definitely do a lot better. The other important feature is that the model has to learn two things. It has to learn both sentiment, meaning which comments are positive or negative, but it also has to learn the English language itself. So that's a tall order. If you think about the complexities of the English language, it takes humans a year or two to learn that. As a child, you may, I'm sure it took you a year or two to learn the English language, and you had to listen to lots and lots of English language before you could speak. So how can we make an improvement? Well, think about this. What if we had a model that already understood English? Then, to solve the sentiment analysis problem, all we'd have to do is learn sentiment of good and bad comments. So in order to do something like this, we need what's called a language model, or a model for the English language. And formally, what a language model is, it's a probability distribution of words in a sentence based on all the other words you see in the sentence. Let's look at some examples. It's like a fill-in-the-blanks problem. So look at the first sentence on the right. It's raining outside. Unfortunately, I left my blank at home. You know intuitively the missing word is probably umbrella or something similar. The next one, the moon is much closer to blank than the sun. And you know by context that that's probably the earth. And finally, once you learn to ride a bicycle, it's not hard to learn to ride maybe a motorcycle or some other two-wheeled vehicle. And if you think about that last example, you've heard that saying, once it's just like it's just like riding a bicycle. Once you've learned a specific skill, let's say like riding a bicycle, you can transfer that knowledge to other domains. Riding a motorcycle is not that much different. It's mostly the same skill of balance, but you just need to learn a few more skills of how to operate the throttle and the brakes and so on, and maybe change gears. But the basic skill you learned previously of how to balance is transferred. So that idea of transfer learning is one way we can improve models. We can build on skills that were learned previously. So in 2018, the Google AI team developed a model called BERT. It's a pre-trained language model that knows a lot about the English language. And in a way, it understands the English language. And the way these BERT models were trained was they were given a vast corpus of the English language. I mean, a huge amount of the English language. And they were told to solve this masking problem that we saw earlier. A few words would be masked out of a sentence, and given the context, it would have to learn to predict what the missing word should be. Now, there are some other improvements they made. They also use what's called a transformer model, which is a more advanced model that has been developed a few years ago that uses what's called the attention. It's a very powerful technique, and these two combined make BERT an extremely powerful model. And it turns out BERT models can be used for many different language tasks, and one of them could be classification. So if we look at this example on the right, what I could do is use a pre-trained BERT model that already understands English. And to use that for sentiment classification, I would add just one more layer with 2 units, a dense layer effectively, that has a positive and negative output. And then I would train this same model with my sentiment data that I have and just train that last layer. I would freeze the BERT layers so they're not trained. There's also a fine-tuning step you can do after the final layer has been trained to also improve the model even further. And the results you get are quite surprising. And we'll see an example exactly how this works, and you'll see how well the accuracy can be improved. Now let's see transfer learning in action. So I'm here in Google Colab. I've already opened that. And I'm going to go to the GitHub tab and load go to my GitHub repo right here, and I'm going to open a model that uses BERT. And I'll provide a link to the repo for easy access. So I'm going to look for text sentiment BERT. Text sentiment BERT. And this model solves the same problem as we saw before. It uses the same data set, but it's going to use BERT pre-trained model, pre-trained layers to improve accuracy. So I'm going to do a couple of things. First, I'm going to clear all outputs, and I'm going to change the runtime type to use GPU. Okay, I've got that. So up here, it explains a little bit about how the BERT model works, and this is a link to the original BERT paper. So if I right-click on that, it will take me to this paper that explains exactly what BERT is and how it works, and it shows how it improved a number of different tasks, including question and answer tasks and a number of other natural language tasks. All right. BERT is what they consider it bidirectional, because it looks at context from before a word and after a word, right? That's why they consider it bidirectional. All right, so let's go through this. So, of course, it gives us a warning, which we can ignore. And in order to use this, we need the pre-trained BERT model. And we can install that using pip. And we need BERT for TensorFlow 2, and also we need this other package called Sentence Piece. So if we click those, we use these magic commands that will install these additional libraries. And since Google developed these BERT models, they make them available for us to use in TensorFlow, with TensorFlow or Google Colab or a number of other. All right, so now we're going to import a number of libraries, and specifically we're going to import TensorFlow Hub, because TensorFlow Hub contains pre-trained layers for the BERT model, and most of the other libraries we're already familiar with. So we'll download the training data set, and this is exactly the same training data set that we used before from the UCI machine learning repository. It's a number of movie sentiments, the same data set that we used in our previous example. And we're going to load those using pandas the same way we did before, and we see we have 2,743 examples, and they look exactly the same. And we use the comment to train with, and the sentiment. Now, in the case of the data preparation, this is a little bit different than what we've done before. We're going to collect the comments and the sentiment and turn the labels into a NumPy array, and then split them, test and train, using a 20% split, like that. And then what we're going to do is load this BERT layer from this website right here. And this hub library that we use, this TensorFlow Hub, it has a method to load this pre-trained model. And it also loads what's called this tokenizer. It's similar to what we did before, converting words into vectors, or words into vectors. They have a special tokenizer that's made specifically for BERT. So we don't have to write any of that code. So that's loaded. We do need to do a little bit of work to encode the text in a specific way, because BERT can be used for many different tasks. One called the close task, which was similar to that fill in the blanks problem, that we saw earlier. It can also be used for classification or question answer and so on. We're going to use it for classification. In order to use it that way, we have to do a couple of things. Every sentence that we give it, we have to add a pad at the end, this pad token at the end, to fill out the entire sequence. And we have to add this CLS and SEP tokens in the beginning and the end. It's a little bit of boilerplate. I'm not sure why they just didn't give us a method to do that, but that's just what we have to do. So we'll create this method to encode the text. It's a little bit of transformation, not very complicated. We're going to use the tokenizer that comes with the BERT library. All right. So here's our model, and the model has several inputs. It has input word IDs, it has a mask, and it has segment IDs. And these different inputs are used for different tasks. Since we're only using the classification task, we only need one of them, and we'll see how that actually works. And what we're going to do is use this BERT layer with these 3 inputs like this, and it's going to produce 2 outputs. The BERT layer, the pre-trained BERT model produced 2 outputs, a pooled output and a sequence output. We're only going to use the sequence output. We could use the pooled output for other purposes. All right? And we're going to take a piece of it, this sequence, we're going to just take one part of it using this lambda layer. All right? And we're going to add to that layer, that BERT layer, we're going to add to it a dense layer that has 2 units. And these 2 units are for our outputs. Remember, we're doing binary classification. We need a positive output and a negative output. And this is going to use a softmax layer. All right? Then we'll create a model, putting all these layers together like this. And then we'll compile it and print out a summary of what that model looks like. And you will use categorical cross entropy because we're making a classification model, and we'll use the atom optimizer and accuracy, very similar to what we did before. Now, you notice we have these 3 input layers. That's how we supply input to the model. Then there's a BERT layer that has an output shape of 768, and it has a huge number of parameters, something like 109 million parameters. These were all pre-trained parameters. It's been trained on a massive corpus of English language text. All right? And then we have finally a dense output layer where we take our outputs. And in this case, we've set the BERT layer to be non-trainable. We're not going to train the BERT layer. It's already been pre-trained. We're only going to train the final layer. So there are about 1,500 parameters to train there. All right? So here's how we're going to train the model. We're going to encode the text using that method from above, using the xtrain data. And we're only going to train it for 5 epochs. You'll find out we don't need to train it for very long. And we'll use this batch size of 3. And we use a relatively small batch size because it turns out that BERT model takes a lot of memory. It's really a large model because it has so much knowledge about the English language. We can't really use a larger batch size. If we wanted to use a larger batch size, we'd have to use a bigger GPU, and right now we're just using the free GPUs that are available in Google Colab, and it will only support up to a batch size of 3. And while it's going, we'll also validate it using the test data that we have before. So let's let this go and see how it does. All right, the transfer learning step completed, and we look at, after 5 epochs, look at the accuracy. We get 92% accuracy, and the validation accuracy was 90%. That's pretty amazing. Just after 5 epochs, it's still far better than our previous model. Remember, our previous model, maybe it got to 80%. This is already over 90% accurate, just with 5 epochs. So you see the power of this pre-trained BERT model, the fact that it has all this knowledge and this context of the English language. So we can improve this further with what's called fine-tuning. And in the previous training step, what we did is we froze the BERT layers. We didn't train those. We trained only the final layer that we added. So here what we can do is fine-tune the BERT layers by unfreezing the BERT layers. What we'll do is we'll say BERT layer.trainable equals true, and the output, we will not train that. That one has already been trained. We're not going to train that any further. And we'll create another model using the same inputs as we did, but we just need to create another model because we're going to train these parameters. The other detail the other small detail here is we're going to specify a lower learning rate, reduce the learning rate just to get it to adjust a little more carefully, a little more accurately. Right? So this model looks exactly the same, but notice the number of trainable parameters here is very large. Right? We're training a lot of parameters. Right? And non-trainable, there's only 1. So let's go ahead and start this training. And we'll also train this for 5 epochs. And let's see how it does. All right, looks like the training is done, the fine-tuning is done. And you look at the accuracy, it went up even more. It started around 92%, 90% for validation accuracy. And the accuracy itself was up to 100%. It just predicted perfectly. But the validation accuracy was a little bit less, about 96%. And that's really just probably due to a little bit of overfitting. But you look at it, we're up to 96% in accuracy. And if we plot out this chart here, you can see it started out pretty low, but it increased by another 5% or so in terms of validation accuracy, getting almost to 96%. So this is almost a 16 percentage point increase over our previous model using the same data set, a very small data set, only 2,000 or 2,700 examples or so, and even less for training. So this is a remarkable achievement, and that's why there's a lot of excitement around these transformer models and BERT models and natural language processing in general, because now we have the ability to learn from vast amounts of data that already exists. And we don't need to have a lot of label data. In fact, BERT is trained using what's called a self-supervised method. There's no human labeling necessary for that. It reads a vast amount of text, masks out a small percentage of the text, maybe 15%, and tries to predict that. So it's a very powerful idea, and it works extremely well. And this actually probably is not the best BERT model that we're using. There are some very large-scale BERT models that do even better. So let's make some predictions with this model. And this final model that we've created, what we need to do is encode our input text, our X test, and make our prediction and take the most likely outputs like we did before. And since this is a very large model, it does take a little bit longer to make the predictions, and we can just choose a random sample and then compare it with the label. Service was fantastic. Of course, it predicts accurately as expected. It's a simple. Here's one that it gets wrong. You get extra minutes so that you can carry out the call and not get cut off. So that is positive, I guess, because you get extra minutes, but I guess it did get a little confused because of this not cut off. So it did make a mistake in that case. Let's look at another one. This is a really long one. I hate writing bad reviews about films, especially those in which I really like the star, but this film is so bad, I don't believe for 1 second that anyone could be proud of it. So there is sort of some positive stuff. Usually I like the star, but the film was bad, and so it predicted that correctly, a long sentence in it, and it predicted correctly. Here's another one. The Monster Chicken Fried Steak and Eggs is my all-time favorite. All right, not too hard. Let's look at one more. I've only had my Bluetooth for a few weeks, but I really like it. All right, so it does pretty well. As we saw, it gets at least 96% accuracy. So let's go and perform some error analysis. All right. So let's pick some samples where it predicts incorrectly. So here's one. This place deserves 1 star and 90% has to do with the food. So this is definitely negative, and 90% has to do with the food. So I guess it somehow totally got confused with that one. So it predicts that as a positive comment because it says 90%. I'm not sure. And it seems to be quite confident about that. So it got it totally wrong. It definitely was not as good as my S11. Well, that's definitely negative, and definitely got that one wrong as well. And it seemed to be quite confident about that. So anyone near you will hear part of your conversation. So is that good or bad? Well, I guess it is bad, but maybe there's a little more context in that. Someone overhearing a conversation is considered a negative in general, but in some contexts, maybe it's really sensitive. So it could go either way. But you notice it was in between in this case. But still, you can see that this BERT model makes a tremendous improvement in terms of classification accuracy, even with a small training data set. So this is an exciting improvement in natural language processing, and it's really the tip of the iceberg. There are many other ways to use the BERT model, and this is just one of them. All right, let's look at a fraud detection example. This is another use of machine learning. So in this example, we're going to detect credit card fraud. And as you can imagine, credit card fraud is a very serious problem because a small but very significant percentage of credit card transactions are fraudulent, meaning that the credit card charge was not authorized by the cardholder. And this often happens because someone either gets your credit card number or finds it in some other way, and then they just make charges without your knowledge. And that fraud results in billions of dollars of losses every year. And the consequence is higher fees that you and I have to pay because those costs cannot often be recovered. And finding these credit card thieves is a very challenging problem because they may do it in very subtle ways. They make purchases in very subtle ways that are hard to find. And often the thieves are never identified. They may be anywhere in the world. So it's best to try and detect this fraud before it actually occurs, or at the time before the charges are actually made. So let's see how machine learning can solve this problem. So one way to do this is through what's called anomaly detection, or finding irregularities in purchasing patterns. Because it turns out that examples of fraud are highly imbalanced, meaning that there are very few cases of actual fraud. Maybe 1 in 1,000 transactions are fraudulent, so we don't have many examples of fraud, and even if we do, they are not represented well over the entire data set. So for that reason, a supervised learning solution is not possible, or it's just not practical. A more effective way to do this is what's called anomaly detection. It turns out each of us has certain purchasing patterns, meaning what we buy on a regular basis, where we buy things, or how much we spend. And a machine learning model can learn those purchasing patterns and flag anything that might appear anomalous or irregular. So I'll give you an example. Years ago, we had traveled to France, and I usually use credit cards whenever I travel. I rarely carry cash. And it turned out I tried to make some purchases and my credit card was blocked. I just couldn't make any purchases with one of my credit cards. And it turned out that I hadn't notified my credit card company that I was traveling, and they looked at my transactions and they thought this might be fraudulent because I was making purchases in another country which was totally irregular to my normal behavior. All right, let's analyze this data set, and I'm going to go to Google Colab as usual. I'll just go to Google and search for Google Colab, and it comes up as the first link, and I'll click on that. That's one of the easiest ways to get there. And then I'll click on GitHub, and I'm going to select my GitHub repo as we've done before, and I'll provide a link in the resource section as before. And the one we're looking for is Anomalies Credit Card Fraud. Anomalies/credit card fraud. That's the notebook that we want. So let me click on that, and let me go over here and let me clear all output. There we go. I've cleared all output. And this data set comes to us from Kaggle, and the dataset contains transactions made by credit card in September 2013 by European cardholders. And it occurred over 2 days, but even over those 2 days, there were 28,000 odd transactions, and a very small percentage, only 492, are known to be fraudulent. That's about 0.172% of all transactions. So it's very imbalanced, a highly imbalanced data set. So the positive class, meaning the ones that are fraud, are a very small fraction of the overall set of transactions. And we're going to use an autoencoder to use this for unsupervised training. And the data set, it comes from Kaggle, and here's the Kaggle site, and that link is available in the notebook. And it's quite large. The data set is about 144 megabytes uncompressed. Maybe it's about 70 megabytes compressed. So since Kaggle, you have to log in to get that data set. One of the most convenient ways, or one way to get this into the Google Colab notebook, is to download this data set locally into your machine using your Kaggle login, and then upload it into the Colab runtime. And in this case, I'm not going to change this runtime to be to use a GPU instance. This is a relatively simple model, and surprisingly, it actually runs faster without GPU acceleration.
So first I'm going to run this TensorFlow magic to say that we're going to use TensorFlow 1.x. We'll import our libraries, and we're going to read in the data. So this data, it arrives as a zip file, and Pandas can read the zip file. Let me go ahead and upload it, and I'll go over here to the Files tab right here and click Upload. I've already downloaded this data earlier, so I'll just select that data and start the upload. And depending on your network bandwidth, this could take a little bit of time, because it is a relatively large data set. Even compressed 70 megabytes could take a few minutes. All right, we're just about done with the upload. And this circle will go away when it's completed, and there it is. It's finally done. All right, so let me close that tab there. And I'm going to read the data, and Pandas can read this as a zip file, so I don't have to unzip it. And I'm going to just select the first 30,000 samples, just the first 30,000. Because this is a large data set and it could take a long time to train, I'm just going to use the first 30,000 for training and tests here. You could use a larger, the full data set if you want, and you can experiment with that. But just for the purposes of getting this done quickly, I'm going to just select 30,000. All right. And let's take a look at what this data looks like. So there are many columns. There are 30,000 samples, and there are 31 columns. So that's the shape of the data. And you see the first column here is a timestamp, and that's seems to be just an index. It doesn't give us an actual date and time. It just seems to be some time index. It doesn't give us any specific information. And the vast majority of the columns you see are anonymized. We don't have detailed information like the name of the cardholder, or the place where the transaction occurred, what was purchased, or anything like that. These have all been anonymized, and they describe how they anonymize this data in the Kaggle webpage. In addition, there's an amount column. This one, they do not anonymize, or this is the actual value of what was the transaction amount, right? And there's also a class here, which is a label, which tells us whether this was fraud or not. And you see the vast majority are not fraud, or they're normal. So 0 means normal, and 1 would mean fraud. All right. So all this data here, we don't know who did it, but we can assume that that is representative of the original data set. So let's do a little bit of analysis here to find out how many of these are fraud and how many of these are normal transactions. So we'll just group by the class and get a count, right? So if we group that data, we have 30,000 total, and about 29,906 of these samples are not fraud, or they're normal transactions. The class is 0. And the class 1, meaning the fraudulent, there are only 94 of those. So a highly imbalanced data set, a very small fraction is fraud. So for this reason, we're not going to use supervised learning. We just don't have enough samples here to use supervised learning. We can't use those as labels. We're going to use an unsupervised technique. As mentioned, we're going to use an unsupervised learning style for this example. And unsupervised learning means that we're going to learn without labels. And that's useful when labels are not available or they're just too few labels. And this is more challenging than supervised learning because the model doesn't know exactly what to look for. If we look at the picture on the right, what does that look like to you? Obviously, it looks like a bunch of lockers, and they're all very similar. And you might notice that one of the lockers is of a different color. That might be interesting. Or you might notice that one of the lockers has a sticker on it. And if we were to look even more closely, we might find lockers with different locks on them. We might find that the numbers are in sequence and maybe one of the sequences is wrong. We didn't, in this case, I didn't tell you what to look for in this image. And you might find different things interesting in that image. It's similar for a machine learning model. If a machine learning model was to look at this image, it's not clear what exactly it would find that's different or interesting. There are many techniques for unsupervised learning, cluster analysis, principal component analysis, or autoencoders. This is an open area of research. Because supervised learning is well established, it works quite well. In the case of unsupervised learning, it's still an area that people are trying to develop, so you can't expect to get the same level of
accuracy you would get with a supervised learning style. So for this example, we're going to use something called an autoencoder. An autoencoder is a type of unsupervised neural network, and some people might call it self-supervised. And the way it works is we use the input as the expected output. The input and the expected output are the same. And what the autoencoder tries to do is attempts to recreate the input. And if you look at the example on the right, I have a dense network, and it has an input image that looks like a 9, and I would supply the output as also a 9, the same exact image for training. And hopefully, if we provide many, many examples, the autoencoder would try and find similarity between these different images. So how does this become useful? Well, because obviously if we put in a 9, it's going to come out with something that looks like a 9. And that will normally happen if it sees an image that is similar to what it has seen before, or some input that it has seen before. And the difference between the input and output is what's called the reconstruction error. Now, if the reconstruction error or the input and output during prediction are very similar, that would mean that that's probably not anomalous. It means that the autoencoder has seen something that it recognizes. Now, if the reconstruction error is high, that suggests that possibly it's an anomaly, because the autoencoder is not able to reproduce its input, then it doesn't really know how to do that. It doesn't really understand what it has seen. So if you look at the example on the right, in the prediction case, the input image is also a 9, but notice the output image is not exactly the same as a 9. It's very close. It is also a 9, but notice it doesn't look exactly the same. And that's what it has reconstructed, looking at many, many different 9s and identifying their similarities. So it turns out any symmetric structure can be used as long as it has what's called a bottleneck structure. It looks like a bottleneck. The middle layers are generally smaller than the outer layers. That's a kind of dimensionality reduction. So the model is trying to generalize as much as possible. So you could use dense layers, you could use convolutional layers. You could also use autoencoders. In addition to anomaly detection, you could use it for denoising or a dimensionality reduction as mentioned. Let's go back to our notebook and go through the data preparation or data engineering step. So as we looked at the data before, we noticed it has a time column, and that's not really useful for us. In fact, we're not going to use that column for any of our prediction because it doesn't really mean anything. Similarly, since we want to use unsupervised learning, we're not going to use the class column or this label that's here. We're just going to use that for validation. We're not going to use that for training. And the amount we've got to normalize. All the other values here, you notice that they are normalized. They're generally between -1 and 1, or their values are not significantly, they don't vary significantly. So we're going to leave those alone. So here's our cell where we're going to do the data engineering. So first thing we're going to do is drop the time column. And when it says axis equals 1, that means just drop that as a column. And then the amount, we're going to scale that, and we're going to use the standard scaler, which is part of scikit-learn. And we'll just take the amount, and we want the values to range between -1 and 1. All right, go through that step. And the next what we're going to do is split the train and test, as we've done before, and we're going to split it by 20%. So 20% will be used for test, and 80% is going to be used for training. In addition, for the training data set, we're going to drop the class column, meaning the label. We're going to drop that because we don't want to use that during training. And for then we're going to create a y-test data frame, and in that case, we're going to just use the class column. That's all we want for y-test. And the x-test, we're going to drop the class column also. Notice we saved the class column in y-test, and for the x-test, we're going to drop the class column. Right? And then we're going to use just the values from xtrain and xtest for our train and test values. Right? We're reusing these variables. Because XTrain originally was a pandas data frame, and all we want is to get the values out of it, which is going to turn it into a NumPy array. And then we're just going to print out the shape of the XTrain. Right? So we see we have 24,000 training samples, and we have only 29 columns for training because we dropped the time column and we also dropped the class column. So that's all the data engineering that we're going to do. Not very complicated. It's relatively simple. Next, we're going to define the autoencoder model, and we have it right here in this cell. And you look at it, and it's relatively simple. It's a 4-layer model. It's all made of all dense layers, and it looks a lot like some of the other models we've seen. First, we start out with defining a sequential instance of a sequential class, and we're going to add each of these dense layers. And the first dense layer, where the size of it, or the number of units, is going to be this encoding dimension. And I've defined that right here, this encoding dimension. And this is a hyperparameter. This is a number that I've chosen arbitrarily, really. And this is something we can play with. So that's just the number of input units that we're going to use here. And that's going to have an activation function of tan h, a hyperbolic tangent. This is another hyperparameter that we can experiment with. But in this case, it turns out that tan h tends to work reasonably well in autoencoders. And we also need to specify the input shape, and the input shape is going to be the input dimension. And the input dimension is the first dimension of the XTrain, and there were 29 columns, as we see up here, so that's going to be the input dimension. Right? There are 29 inputs. Then we're going to add another dense layer, and that dense layer, it's going to be half the size of the input layer. This is that bottleneck structure. So the first layer was 14, so this layer is going to have 7 units in it. And that's going to have a slightly different activation function, a ReLU activation function. And that's something also we can experiment with. We'll add another dense layer that looks exactly the same, that also has 7 units. And this one's going to have a tan h activation function. And then the output layer is going to be exactly the same as the encoding dimension, right? Or the input dimension. So notice the input was of this dimension and it had this size, but the output layer is going to have this same input dimension. And the activation is going to be a rectified linear unit. And then we're going to print out the summary. And if we look at the summary, notice that notice the way that the summary is printed out, it gives you the output shape. So the output shape has 14 units, as we've seen here, 14. The input is actually the input dimension. That we specify that over there. And the input dimension was 29. And Keras doesn't actually show you the size of the input, but we know that because that's what we specified. So the output dimension, the output shape of the second layer is 7 because it's half the input, half this encoding dimension. And then we have a third layer, which is also has an output layer of 7. The final one has the size of the input shape, and the input shape, well, remember, it had 29 inputs in it, so that's going to be the same. So the input is 29, has 29 inputs, and the output has 29 units. And in the middle, it's going to have this bottleneck shape, meaning that the size is going to be slightly smaller. So we just happen to use 4 layers here. We could have used a different number of layers. We could have used different activation functions. We could use different encoding dimensions. So those are all different parameters that we can experiment with. And you notice the total number of parameters is relatively small. This is a very simple model. It has only a total of 813 parameters to learn. So it's going to learn quite quickly, as we will see when we train this model. Now that we've defined the model, let's go through the training step. So here we have this cell which defines the model train, and we're going to use 40 epochs for training in this example. And this is another hyperparameter we can experiment with to see how we can improve this model. And this is a nice starting point. And we're going to use a batch size of 32. That'll make the model train relatively quickly. And when we compile it, we're going to choose the Atom optimizer. And the Atom optimizer is a good optimizer to start with. It's one of the better optimizers, so it's a good starting point. And for the loss function, we're going to use mean squared error. And this is going to compare the input and the output. And the way it's going to do that is take the difference of every value from the input and the output, take the difference, and each value is going to be squared, and then it's going to sum them all up. That's what's called the mean squared error. So if you're familiar with statistics, standard deviation, it's a similar concept. So you would take all the inputs and outputs, take the difference between them, square those differences, and add up all those values, and it gives you a single number. And that's the number we're trying to optimize, to minimize the difference between the input and the output. We're also going to collect the metrics, which is the accuracy, and the accuracy, of course, is the difference between the input and output, and we want that to be at minimum, as small as possible. So it's going to try and reproduce the input as much as possible. So when we do the training step in this fit function, when we call the model.fit, we're going to supply the input values, which are the training samples for the input, and notice the expected output are also the training samples. That's what makes this an autoencoder. The input and the expected output are both the same values. You could think of this as the labels. In fact, you could look at this as if the labels are the input. All right? Then we specify the number of epochs and the batch size. And for the validation data, we're going to do something very similar. We're going to use xtest as the input for the validation data set, and we're going to use xtest as the expected output for the validation set as well. All right? And we'll use verbose equals 1, which means display what the training progress. And finally, I'm just going to save the model as this variable autoencoder just for convenience. So let me go ahead and get that started. And it trains pretty quickly. Each epoch is only taking about a second or so. In this case, I'm not using GPU acceleration because this is not computationally intensive. We don't have a large number of parameters to learn. There are only 813 odd parameters to learn. And so it actually works better if we use the CPU to do the training. If we were to use a GPU, it's computationally performs better, but there's some overhead moving data in and out of the GPU. And if that overhead is greater than the amount of computation, then really there's no benefit to using the GPU. So in this case, there's not a lot to do, and it finishes relatively quickly. So in about 40 seconds or so, it's done. So let's take a look at what the plot looks like if we plot the model performance. All right. So here it is. The accuracy is about 70%. So it's not as good as you might expect with a supervised model, but it's not too bad. And you look at the shape; it's about what we'd expect. It's generally increasing. Maybe we could use increase the number of epochs to train it even more, and maybe improve the accuracy a little bit further. But this is probably a reasonable starting point. And you notice that the test and train accuracies are very close, so there's very little variance, and that's what we want. So it's a relatively well regularized model. So this looks like a good starting point, and we'll see how it performs when we make some predictions. Now that we've trained the model, let's make some predictions and plot the results and see what we get. So here's our model autoencoder, and we're going to make predictions, and we're going to make predictions just using the test data, and that's going to produce a set of predictions. And with those predictions, remember the autoencoder is trying to reproduce its input. So just making predictions by itself doesn't tell us a whole lot, because in theory, any correct prediction will just be the same as the input. What we really want to do is compare the input with the output. And the way we're going to do that is using the mean squared error. And the way we're going to calculate that is using a number of NumPy functions. So we'll take the difference between the xtest, the input that we put in, and the predictions that it made, take the difference between those two, and square those differences using np.power in this value 2. So that's going to square the difference, and we're going to take the average, which is just going to add up all the values and divide by the number of values. So that's kind of like standard deviation, very similar to that. So this is a mean squared error, right? And we're going to turn that into a pandas data frame for plotting. It's a convenient way to do that. So We'll have the reconstruction error as the mean squared error, and we'll add one more column, which is the true class. And remember our y-test values? Our y-test values was the class column that we got from our original data. So this is just going to be a value of 0 or 1, whether it's fraud or not. So we'll call this the error data frame. So let's go ahead and make those predictions. Happens very quickly because we know predictions are relatively fast. And if we look at that error df, let's just take a look. Error df dot head, like that. And if I run that cell, you see what I have is reconstruction error, which is a relatively a number that varies, right? So a small reconstruction error means that there's probably not a lot of difference between the input and output. And this class variable tells us whether it's fraud or not. And it turns out the first 5 samples, there isn't any fraud. All right. So then let's plot this out, and we have some a fairly nice a plot that we're going to do here. We're going to group these this error df by the true class, meaning whether it's fraud or not. Right. And we're going to create a couple of subplots, and we're going to go through these groups and label each of them fraud or not fraud based on the color. So let's go ahead and plot that. And we get this nice plot like this. So you notice that this is plotting reconstruction error up here, right? And the number of samples down here, right? The data points, right? And you notice that there are some red, which are the fraud cases, right? Those are fraud. And then the normal are the non-fraud. In addition, I've drawn a line here. This line is what I'm going to call the threshold, right? And I've chosen that arbitrarily as 6. I could have chosen any value for the threshold. So what that means is that anything above this threshold, I'm going to consider as fraud. Anything above the threshold is considered fraud. And anything below the threshold we'll consider as normal. And you see the vast majority is normal. It's not considered fraud. And we do have quite a few samples that are fraud that are above that line. Notice there are also some normal samples that are also above the threshold. So those will be misclassified as fraud. And we'll see. Unfortunately, it's not too many, but we'll go through this analysis and see how well that works. Notice that there are a few of the true fraud that are known to be fraud that are below the threshold as well. Right? So there are some false positives and false negatives. Right? So in adjusting this threshold changes the level of false positives and false negatives. So let's go through a little bit of analysis here. So we'll separate out the normal and fraud cases based on the true class. Whether if the true class is 0, that's considered normal. And if the true class is 1, then that means it's fraud. Right? Okay, so let's run that. So there are 5,985 normal transactions and only 15 fraud transactions in this sample that I happen to have used. All right? And I can separate the true positives and the false positives, the true negatives and the false negatives based on this logic. All right? And you can go through this in detail and confirm that this is the correct logic. So if the reconstruction error is greater than this threshold that I've defined, then that's considered a true positive. And that's for the samples that are considered fraud, that we know are fraud, and for the samples that we know that are normal, and if the reconstruction error is greater than the threshold, that's considered a false positive, meaning that the autoencoder thinks that there is a high reconstruction error, even though we know that this is not a fraudulent case. Similar with the true negatives and false negatives. So let's do that calculation and print them out. And what we see is that there are 8 true positives, meaning that we recognized 8 of the sample, 8 of the 15 that we know are fraud as fraud, and the true negatives are 5,920. So the vast majority, which we know are not fraud, were classified correctly. Now notice that the false positives, there are quite a few false positives. So that means that 65 of the transactions were flagged as anomalous or fraud. All right? So that seems high. That seems higher than, say, the true positives. But if you think about it, that's not that bad, because the vast majority of the time we classified them correctly. Remember, this is a highly imbalanced data set. So for the most part, the vast majority of transactions will not be flagged as fraudulent, and the transactions would go through normally. But some small percentage would be treated as false positives as fraud. Say that you're at home and you make a normal transaction, some small percentage, a very small percentage, could be flagged as fraud, which is a little bit of an inconvenience to the cardholder, but for the most part, that's probably okay because we're trying to catch as much fraud as possible. If we didn't have this machine learning model, we wouldn't have caught any fraud at all, so which is not a good thing. So there are some false negatives as well. So these are fraud cases that we didn't catch. And so ideally, we'd want 0 false negatives, meaning we catch every fraud case, but we didn't catch all of them. We caught at least 50% of them, all right, which is an improvement. And we could change that by adjusting the threshold. Right? So this is kind of a trade-off. So the way this trade-off has worked is that the vast majority of transactions, they go through and they're okay. Some small percentage of transactions that are normal are flagged as fraudulent, but hopefully the cardholder would just see this as a nuisance, right? And they would say, okay, why does that transaction not go through? They could call their credit card company and says, hey, why is this transaction blocked? So it's considered a small nuisance, but at least we are catching some of the fraud cases. So it's not perfect. There are some trade-offs to it, and there is a threshold we can adjust. And this is something, if you were the credit card company, you would adjust that threshold so that we would want to minimize the nuisance cases and try and catch as much fraud as possible. So now that you've seen this autoencoder in action and how it can be used for fraud detection, let's go over some common questions that you might have. So one common question is the size of the bottleneck and the size of the number of input units. Well, it turns out there's no strict rule for that. It depends on your data, so you really have to experiment with that. And same thing goes for the number of layers. So it really depends on the data, and it's empirical, like so many things that are done in deep learning. So one way to start is with a simple model. It's always best to start with something simple, something like the example, we only had 4 layers, and then try different parameters and see how they affect the model. As you remember, it didn't take long to train the model and to evaluate its performance. So we could go through many experiments in a day and come up with a reasonably accurate model. Of course, you can improve that over time. You might want to put something into production first, see how that works, and then maybe adjust it over time and see if you can improve. So some other use cases that could be applied with this same technique, autoencoders can also be used to remove noise from a data set. And I'll provide some links to some examples on how that's done. So if we had an image that was really noisy and we had many images that are similar, then we can use an autoencoder to remove that noise because it's going to try and find similarities between images or between other types of data sets. Another use case is intrusion detection. So if somebody's trying to hack into a system, that would probably look like some anomalous behavior. So this is commonly done by looking at network traffic in an organization. There's a lot of normal network traffic. The vast majority is normal, but somebody that's trying to hack in would probably do something that's irregular, and it doesn't look normal network traffic. And that's one of the ways that intrusion detection systems operate. Another use case is maybe estimating failure of some kind of industrial process or industrial machinery. If you can imagine, you might have something like a large industrial pump or some kind of motor or a conveyor system or something like that. And eventually those systems may fail, and it may fail due to some kind of a bearing failure or lack of lubrication, something like that. And the one way to detect that is just to measure the difference between normal behavior. The vast majority of the time it's operating normally, so we would use that as the training set. And at some point, the operation may deviate from normal. Maybe there's excessive vibration or there's different kind of sounds that come up. And we can't necessarily predict what that sound's going to be. All we know is it's different. And if you can imagine, that's what humans do in most cases. Someone that's an experienced engineer might listen to a pump or a conveyor system and just know by listening to it, it doesn't sound right. It doesn't sound normal. And that's really the way an autoencoder is working. So it's an effective technique. Of course, you want to experiment, and autocoders are kind of fun to experiment with in different kinds of data sets. So try out different hypotheses on your own. There are many different hyperparameters that you can experiment with, and we mentioned a few of them during the past few lectures. And that's really the best way to learn. Just try things out. I cannot emphasize that enough. To become a good data scientist or a machine learning practitioner or a data engineer or any of those, you really have to experiment and just come up with your own feel and get an understanding of how these things work. And of course, I'm always here to help. If you have any questions at all, just post the question, or if you want to send me a private message, that works too. And I'm just here to help. We're almost done, so let's talk about a few next steps. First, I want to congratulate you on a job well done. You have learned a lot in this course. You now know how to build machine learning models using Keras, NumPy, Pandas, and Matplotlib. These are the most popular Python libraries in use today, so your skills are in high demand. You've also learned how to use Google Colab notebooks in the cloud. So one thing you want to do to promote your work and to demonstrate your skills is to create a portfolio. And one way to do that is on GitHub. Like any great artist, you should demonstrate your skills by creating a portfolio of your work. And GitHub is kind of like a free public art gallery where you can present your machine learning and data science skills. You can promote your repo on social media and on your resume, and this is how you can stand out from the crowd. And I'll tell you, many employers will often look at your GitHub repo to see what you've done. So a high quality repository with a good README describing everything that you've done, high quality code that's well commented, easily readable, that you can walk through and you can explain what you've done, goes a long way. And finally, you want to keep going. You don't want to stop learning. Machine learning is a constantly changing field, so you want to be sure to keep up to date on the latest developments. You want to continue to experiment with different models and data sets. And one of the best ways to do that is find a problem that interests you and try to build a model to solve that problem. Your passion goes a long way. Finally, I want to thank you for enrolling in this course and taking this journey. Remember that you have lifetime access. So if you have any questions or you're curious about any topic at all, send me a message. I'm always happy to answer any questions that you might have. Or if you have an idea for other lectures or other topics, let me know. Thanks again.